The possibility of life existing in the subsurface oceans of icy moons has captivated scientists and space enthusiasts alike. Moons such as Europa, Enceladus, and Ganymede, orbiting the gas giants of our outer solar system, are thought to harbor vast, hidden oceans beneath their thick, frozen crusts, raising intriguing and profound questions about the potential for life in these dark, cold, and distant worlds. Europa, one of Jupiter's Galilean moons, is a particularly fascinating candidate. Beneath its fractured and chaotic icy surface, scientists believe there is a global, salty ocean of liquid water, an ocean that may contain more water than all of Earth's oceans combined. This ocean is kept from freezing solid not by the faint, distant sunlight, but by the immense gravitational pull of Jupiter. As Europa orbits its parent planet, it is constantly being flexed and stretched by tidal forces, a process that generates a significant amount of internal heat through friction. This tidal heating is thought to be powerful enough to maintain a liquid water ocean and could even power hydrothermal vents on the ocean floor, similar to the black smokers found in the deep, dark abyss of Earth's own oceans. These vents, on Earth, are oases of life, supporting entire ecosystems that are completely independent of sunlight, their energy derived from the rich chemical soup that spews from the planet's interior. The presence of such vents on Europa, combined with the essential chemical ingredients for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which are thought to be present from the moon's initial formation and from subsequent impacts of comets and asteroids, could create the perfect, protected cradle for life to arise and to thrive. Enceladus, a small, glittering moon of Saturn, has moved from a theoretical possibility to one of the most compelling targets in the search for life, thanks to the stunning discoveries of the Cassini spacecraft. Cassini observed a series of dramatic geysers, plumes of water vapor and ice particles, erupting from a series of long fissures, nicknamed tiger stripes, near the moon's south pole. These plumes shoot hundreds of miles into space, providing a direct and tantalizing sample of the subsurface ocean from which they are thought to originate. And when Cassini flew through these plumes, its instruments detected not just water, but also salts, silica nanoparticles, and a rich cocktail of complex organic molecules, including methane, propane, and formaldehyde. This is a discovery of profound significance. It is direct, empirical evidence of a salty, organic-rich, and geologically active ocean, an environment that contains all the known, essential ingredients for life as we know it: liquid water, the necessary chemical building blocks, and a source of energy. The concept of extremophiles, organisms that have been discovered on Earth in some of the most extreme and seemingly inhospitable environments imaginable, from the boiling, acidic waters of hot springs to the crushing pressures and absolute darkness of the deep sea floor. And even to the dry, frozen valleys of Antarctica, has completely revolutionized our understanding of the resilience and the adaptability of life. The existence of these hardy organisms on our own planet makes it seem not just possible, but perhaps even probable, that similar microbial life forms could have evolved to thrive in the dark, chemical-rich waters of Enceladus or Europa. The list of potentially habitable ocean worlds does not end there. Ganymede, another of Jupiter's moons and the largest moon in our entire solar system, also shows strong evidence of a subsurface ocean. Uniquely, Ganymede is the only moon known to have its own intrinsic magnetic field, a phenomenon that is usually associated with a molten metallic core. The interaction of this magnetic field with Jupiter's larger magnetosphere suggests the presence of a conductive layer beneath the surface, most likely a vast, salty ocean. This ocean is thought to be even larger than Europa's, and it may be a complex, multi-layered structure, with liquid water sandwiched between different layers of ice. while the potential for active geology and hydrothermal vents is perhaps less certain on Ganymede than on Europa. Its sheer size and the presence of this vast, hidden ocean make it a target of immense scientific interest. The ongoing debate and research in the field of astrobiology is no longer just about whether these moons could have the right conditions for life, but about what kind of life they could support and how we might be able to detect it. The exploration of these icy ocean worlds is one of the great and most exciting frontiers of modern science. Missions like NASA's Europa Clipper, which is set to launch in the mid-2020s, will perform a detailed reconnaissance of Europa, using a suite of powerful instruments to map its ice shell, to confirm the presence and the properties of its ocean, and to search for the chemical biosignatures that could be the first, tantalizing hints of life beyond Earth. And the European Space Agency's JUICE mission will perform a similar detailed study of Ganymede and the other Jovian moons. These missions are not just about exploration. They are about answering one of the deepest and most fundamental questions that humanity has ever asked: are we alone? The faint, ghostly plumes of Enceladus and the fractured, icy plains of Europa may hold the answer, a secret that is just waiting to be discovered in the dark, cold, and beautiful depths of our own solar system. The icy moons of our outer solar system, particularly the Galilean moons of Jupiter and the enigmatic moons of Saturn, have become the focal points in our search for extraterrestrial life. Each one a unique and compelling world with its own set of tantalizing possibilities. Europa, a moon slightly smaller than our own, is perhaps the archetypal ocean world. Its surface is a geologically young and active landscape of smooth plains, long, linear cracks, and chaotic, jumbled terrain. All signs that the thick outer shell of water ice is not a static, frozen block, but is a dynamic, and perhaps relatively thin, lid that is floating on a vast, global ocean of liquid, salty water. This ocean is kept from freezing by the powerful tidal forces exerted by Jupiter's immense gravity. As Europa follows its slightly elliptical orbit, it is constantly being squeezed and stretched, a process that generates a tremendous amount of internal frictional heat. This tidal heating is the engine that drives Europa's geology and maintains its hidden ocean, creating an environment that could be remarkably similar to the deep oceans of our own planet. The presence of a rocky sea floor at the bottom of this ocean is a crucial element in its potential habitability. The interaction between the warm, circulating ocean water and this rocky mantle could create a network of hydrothermal vents, spewing a rich cocktail of chemical nutrients and energy into the dark, sunless depths, providing the perfect conditions for a chemosynthetic-based ecosystem to arise. Ganymede, Jupiter's giant moon, presents a different, and in some ways, even grander, vision of an ocean world. As the largest moon in the solar system, it is a world of planetary proportions, a world with its own complex internal structure and a unique, intrinsic magnetic field. The evidence for its subsurface ocean is strong, derived from the way its own small magnetosphere interacts with the much larger magnetosphere of Jupiter. This ocean is thought to be immense, potentially containing more water than all of Earth's oceans combined. But unlike Europa's ocean, which is thought to be in direct contact with a rocky mantle, Ganymede's ocean may be a more complex, layered structure, a vast liquid water layer sandwiched between an upper and a lower layer of high-pressure ice. This could have significant implications for its habitability. The lack of a direct water-rock interface might make the formation of hydrothermal vents and the chemical energy they provide less likely. However, the sheer volume of this ocean and the complex, and as yet poorly understood, chemical and thermal dynamics that must be at play within it mean that we cannot rule out the possibility of life. Ganymede is a world of secrets, a giant, icy enigma that is one of the primary targets for the European Space Agency's JUICE mission. And then there is Callisto, the outermost of the Galilean moons. Its surface is the oldest and most heavily cratered in the solar system, a sign that it has been geologically inactive for billions of years. At first glance, it seems like a poor candidate for life. But even here, there are hints of a hidden ocean. The subtle magnetic field data from the Galileo spacecraft suggested the presence of a conductive, salty layer deep beneath the surface. While Callisto likely has much less tidal heating than Europa or Ganymede, the slow, steady heat from the decay of radioactive elements in its rocky core might be just enough to maintain a deep, cold, and perhaps, just barely, habitable subsurface ocean. Moving out to the Saturnian system, we find two of the most exotic and compelling worlds in our entire solar system. Enceladus, a tiny jewel-like moon, has, as we have seen, revealed itself to be a world of astonishing and unexpected activity. Its dramatic south polar geysers, which are spewing water, ice, and complex organic molecules into space, are a direct and beautiful manifestation of a deep and potentially life-bearing subsurface ocean. The analysis of these plumes by the Cassini spacecraft has provided us with a free sample of this alien ocean, and what we have found is a list of all the essential ingredients for life as we know it. The discovery of silica nanoparticles, in particular, is a smoking gun for the existence of active, high-temperature hydrothermal vents on the ocean floor, making Enceladus, in the minds of many astrobiologists, the single most promising place in our solar system to search for extant extraterrestrial life. And finally, there is Titan, Saturn's largest moon, a world that is unique in the solar system. Titan has a thick, nitrogen-rich atmosphere, even denser than Earth's, with clouds, rain, rivers, and lakes. But on Titan, at a frigid -179 degrees Celsius, the liquid is not water, but methane and ethane. It is a strange, hydrocarbon world, a twisted mirror of our own planet. While its surface is likely too cold for water-based life, there is strong evidence that Titan, too, has a deep subsurface ocean of liquid water, buried beneath its icy crust. The combination of a water ocean below and a rich organic chemistry on the surface makes Titan a fascinating and deeply complex astrobiological target. Could life have arisen in its subsurface ocean, or could a completely different and truly alien form of life have evolved on its surface, a life that uses liquid methane as its solvent? And that is based on a different, non-water-based biochemistry. These are questions that push the very boundaries of our definition of life, from the tidally heated oceans of Europa and Enceladus to the giant, multi-layered ocean of Ganymede and the exotic hydrocarbon world of Titan. The icy moons of our outer solar system have transformed our understanding of where and how life might exist. They have shown us that the habitable zone is not just a simple circular ring around a star, but is a concept that must be expanded to include these dark, distant, and beautiful worlds. Worlds that are warmed not by the light of a sun, but by the deep gravitational heart of their own. Giant parent planets, the challenge of detecting a hidden ocean buried beneath kilometers of solid ice, on a moon that is hundreds of millions of miles away, is a formidable one. It is a challenge that has required the development of a suite of clever and often indirect remote sensing techniques, a form of cosmic detective work that allows us to infer the presence of these vast, unseen bodies of water. The first line of evidence often comes from the moon's surface itself. High-resolution images, captured by spacecraft like the Galileo and Cassini missions, can reveal a wealth of geological clues. The surface of Europa, for example, is not a static, heavily cratered landscape like our own moon. It is a geologically young and dynamic surface, covered in a complex network of long, linear cracks, ridges, and bands. It also features regions of chaotic terrain, where the ice crust appears to have been broken up, rotated, and then frozen back into place, like icebergs in a frozen sea. These features are all strong, circumstantial evidence for the existence of a liquid water ocean beneath the ice. The cracks and ridges are thought to be caused by the tidal stresses that are constantly flexing and fracturing the ice shell. And the chaotic terrain is thought to be the result of a process where large plumes of warm, buoyant ice, or perhaps even pockets of liquid water, rise up from the ocean below, disrupting and melting the surface crust. The measurement of a moon's gravitational field provides another and more direct line of evidence. As a spacecraft flies by a moon, its trajectory is subtly altered by the moon's gravity. By precisely tracking the spacecraft's motion using the Doppler shift of its radio signal, scientists can create a detailed map of the moon's gravity field, which in turn reveals its internal density structure. This technique was used to great effect at Enceladus, where the Cassini spacecraft detected a significant negative gravity anomaly at the South Pole, a region where the density was lower than expected. This was the smoking gun, the definitive evidence that there is a large, regional sea, or perhaps even a global ocean, of liquid water, which is less dense than the surrounding ice and rock, hidden beneath the South Polar ice shell. Thermal imaging provides another crucial piece of the puzzle. By measuring the infrared radiation, the heat that is being emitted from a moon's surface, we can create a thermal map and search for hotspots, regions that are warmer than they should be if they were only heated by the sun. The Cassini spacecraft's instruments detected a series of long, linear hotspots at Enceladus's south pole, which corresponded exactly with the tiger-striped fissures from which the plumes were erupting. This was direct evidence of a significant internal heat source, a source that is powerful enough to keep the subsurface ocean in a liquid state and to drive the spectacular geysers. The analysis of a moon's magnetic field is another powerful, and often surprising, tool. Ganymede's unique, intrinsic magnetic field is a puzzle in itself, but it is the induced magnetic field at Europa that provides the strongest evidence for its ocean. Europa does not have its own internal magnetic field, but as it orbits through Jupiter's immense and powerful magnetosphere, a secondary, induced magnetic field is generated within the moon. The properties of this induced field, as measured by the Galileo spacecraft, can only be explained if there is a global, conductive layer beneath the surface, and the best, and really the only, plausible candidate for such a layer is a global ocean of salty, liquid water. And finally, there is the most direct evidence of all the plumes themselves. The discovery of the geysers on Enceladus, and the more tentative evidence for similar plumes on Europa, is a game-changer. These plumes are a natural and free sample of the subsurface ocean, a gift from the cosmos that is being spewed out into space, just waiting to be analyzed. By flying a spacecraft through these plumes and using a mass spectrometer to measure their chemical composition, we can directly probe the chemistry of these hidden oceans and assess their potential for life, without ever having to face the immense, and perhaps insurmountable, challenge of drilling through kilometers of solid cryogenic ice. It is through the clever and often beautiful synthesis of all these different and complementary lines of evidence, the geology of the surface, the pull of gravity, the glow of heat, the signature of magnetism, and the direct taste of the plumes that we have been able to build such a compelling and scientifically robust case for the existence of these vast, hidden, and wonderfully promising ocean worlds in our own solar system. The icy crust that encloses a subsurface ocean is not just a passive, insulating blanket. It is a dynamic and critically important part of the overall planetary system, a geological and chemical interface that plays a crucial role in shaping the potential habitability of the ocean that lies beneath it. The thickness of this ice shell is one of its most important properties, and it is a property that is still a matter of intense scientific debate. A thick ice shell, perhaps tens of kilometers thick, would provide a powerful shield, protecting the ocean from the harsh radiation environment of space and from the bombardment of micrometeoroids. This could create a very stable and long-lived environment, a protected cradle where life, if it were to arise, could evolve in relative peace for billions of years. But a thick ice shell would also create a profound sense of isolation. It would make it much more difficult for any chemical nutrients or organic materials from the surface, delivered by comets or asteroids, to reach the ocean below. And it would make it much more difficult for any of the chemical byproducts of life, the potential biosignatures, to make their way to the surface where they could be detected by a future space mission. A thin ice shell, on the other hand, perhaps only a few kilometers thick in some places, would create a much more dynamic and interconnected system. A thin shell would be more easily fractured and disrupted by the powerful tidal forces, leading to a much more active geology of cracks, ridges, and chaotic terrain. This could create a direct pathway for the exchange of materials between the surface and the ocean. The chemical oxidants that are created on the surface by the constant bombardment of radiation from Jupiter's magnetosphere, for example, could be transported down into the ocean through these cracks, providing a potential non-geothermal source of chemical energy for life. And the biosignatures from the ocean could be brought up to the surface, where they would be much easier for a lander or an orbiter to detect. The plumes of Enceladus are a dramatic example of this kind of surface-ocean connection, a connection that is only possible because the ice shell, at least in the South Polar region, is relatively thin and fractured. The thickness of the ice is not just a single, uniform number. It likely varies significantly from place to place. The tidal heating that warms the ocean is not distributed evenly throughout the moon's interior. There could be hot spots on the ocean floor, regions of intense hydrothermal activity, that would create a localized thinning of the ice shell above them. The search for these thin spots, these windows into the ocean, is one of the primary goals of future missions like the Europa Clipper. The spacecraft will use a powerful ice-penetrating radar to map the thickness of the ice shell and to search for the telltale signatures of subsurface lakes or pockets of liquid water that may be trapped within the ice itself. These could be fascinating and potentially habitable environments in their own right, a kind of perched biosphere that is separate from the main, deep ocean. The ice itself is also a rich and complex chemical environment. The constant influx of material from space, combined with the radiation processing on the surface, can create a complex and diverse inventory of organic and inorganic molecules that are trapped within the ice. The slow convective churning of the ice shell, a process similar to the plate tectonics of the Earth's mantle, could be a mechanism for transporting these surface materials down into the ocean over geological timescales. The ice shell is not just a barrier, it is a filter, a conveyor belt, and a chemical reactor. It is a dynamic and integral part of the moon's overall astrobiological potential, and understanding its properties, its thickness, its dynamics, its chemistry, is absolutely essential if we are ever to truly understand the nature of the hidden and wonderfully promising ocean that it protects. The icy moons of our outer solar system have, in the last few decades, emerged as some of the most compelling and scientifically exciting targets in our search for life beyond Earth. And among these, two worlds in particular stand out as the prime candidates: Jupiter's enigmatic moon, Europa, and Saturn's tiny, but astonishingly active, moon, Enceladus. Europa is the classic, and in many ways, the archetypal ocean world. The evidence for its vast, global, and salty subsurface ocean is now overwhelming. And the powerful tidal heating from Jupiter provides a reliable and long-lived source of energy that could keep this ocean in a liquid state for billions of years. The key to Europa's potential habitability, and what makes it such a tantalizing target for astrobiology, is the likelihood of a direct and ongoing interaction between this ocean and a rocky silicate mantle. This water-rock interface is where the action is. It is where we would expect to find hydrothermal vents, similar to those in our own deep oceans, that could be spewing a rich chemical soup of nutrients and energy into the water. These vents could provide the perfect, protected, and energy-rich environment for a chemosynthetic-based ecosystem to arise and to thrive, completely independent of sunlight. Europa is, in a sense, a beautiful, natural experiment. It is a world that has all the known, essential ingredients for life-liquid water, the necessary chemical elements, and a source of energy. The question is, has the spark of life been ignited in its dark, hidden depths? The upcoming Europa Clipper mission is designed to take the next crucial step in answering this question by performing a detailed, remote reconnaissance of the Moon and its ocean, and by searching for the chemical signs of its habitability, and perhaps even its inhabitants. Enceladus, on the other hand, is the beautiful, unexpected surprise. It is a tiny moon, so small that it could fit comfortably within the state of Arizona. Before the Cassini mission, it was thought to be a cold, dead, and uninteresting ball of ice. But Cassini's discovery of the dramatic south polar plumes has transformed it into one of the most exciting places in the entire solar system. These plumes are a direct and breathtakingly beautiful gift to science. They are a free sample of the Moon's subsurface ocean, an ocean that the plume's own chemistry tells us is salty, is organic rich, and is in direct contact with a hot, rocky core that is powering a network of hydrothermal vents. Enceladus has, in a sense, shown us its hand. It has all the same promising ingredients as Europa, but it has one crucial advantage. It is actively spewing its ocean out into space, making it much, much easier for us to study. A future mission to Enceladus would not have to drill through kilometers of ice. It could simply fly through the plumes and collect a sample. This makes Enceladus, in the minds of many astrobiologists, the most promising and most technologically accessible place to search for extant extraterrestrial life in our solar system. The discovery of complex organic molecules in these plumes is a particularly exciting clue, a hint that the chemistry of this hidden ocean may have already progressed a significant way down the long and complex road that leads to life. But the list of potential abodes for life does not end there. Titan, Saturn's giant, smog-shrouded moon, is a world of a completely different and truly alien character. Its surface, with its rivers and lakes of liquid methane, is likely too cold for water-based life. But the combination of a deep subsurface water ocean and a rich and incredibly complex organic chemistry on its surface makes it a fascinating, multi-layered astrobiological target. Could a strange and completely different form of life have evolved on its surface? A life that uses methane as its solvent? Or could the ingredients from the surface be transported down to the warmer liquid water ocean below, creating the conditions for a more familiar water-based life? And then there is Ganymede, the giant of the solar system, with its own intrinsic magnetic field and its vast and possibly multi-layered subsurface ocean. While perhaps less geologically active than Europa or Enceladus, its sheer size and complexity make it a world of immense scientific interest. The search for life in the outer solar system is a search that is full of promise, of mystery, and of a deep, and profound sense of wonder. These distant, icy worlds have challenged our old, sun-centric view of habitability and have opened our minds to a new, more expansive, and more beautiful vision of a universe that may be far more alive and far more creative than we ever dared to imagine. The engine that powers the potential habitability of the icy moons, the force that keeps their hidden oceans from freezing solid, is a beautiful and powerful phenomenon known as tidal heating. It is a process that is driven by the relentless and ever-changing gravitational dance between a moon and its giant parent planet. If a moon were in a perfectly circular orbit around its planet, the gravitational pull it feels would be constant and there would be no tidal heating. But the orbits of the icy moons, particularly the Galilean moons of Jupiter, are not perfectly circular. They are slightly elliptical, and they are constantly being perturbed by the gravitational influence of the other nearby moons. This is a phenomenon known as orbital resonance. The three inner Galilean moons Io, Europa, and Ganymede are locked in a special 4:2:1 resonance. For every 4 orbits that Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This regular periodic alignment means that the moons are constantly giving each other a small gravitational tug, a tug that prevents their orbits from ever becoming perfectly circular. As a moon, like Europa, moves along its elliptical orbit, the strength of Jupiter's gravitational pull on it is constantly changing. It is strongest at its point of closest approach, and weakest at its farthest point. This varying gravitational pull causes the moon to be constantly squeezed and stretched, to be flexed and deformed. This constant internal flexing generates a tremendous amount of heat through friction, in the same way that repeatedly bending a metal coat hanger will cause it to heat up. This is tidal heating. And for a moon like Europa, this internal heat source is thought to be powerful enough to maintain a global liquid water ocean beneath its icy crust. This process is even more dramatic on the innermost Galilean moon, Io, which is subject to the strongest tidal forces. The tidal heating on Io is so intense that it has turned the moon into the most volcanically active body in the entire solar system, a hellish world of constantly erupting volcanoes and vast molten lava flows. But the tidal heating is not the only geological process at play on these icy worlds. The combination of an internal heat source and a liquid water ocean can also drive other important geological phenomena. The heat from the moon's core or from hydrothermal vents on the ocean floor can create plumes of warm, buoyant ice that can rise up through the colder, more rigid ice shell, a process similar to the mantle convection that drives plate tectonics on Earth. This could be the mechanism that creates the chaotic terrain on Europa. And in some cases, the pressure from the ocean below can be so great that it can fracture the ice shell, leading to the eruption of water and ice into space, a phenomenon known as cryovolcanism. The plumes of Enceladus are the most spectacular example of this. The combination of all these different and interconnected geological and tidal processes is what makes these icy worlds so dynamic, so complex, and so astrobiologically compelling. They are not just cold, dead balls of ice. They are active, evolving, and geologically living worlds. Worlds where the constant gravitational heartbeat of their parent planet is providing the energy that could, in the dark, silent depths of their hidden oceans, be powering the beautiful, and perhaps even universal, miracle of life. The search for life beyond Earth is, in many ways, a search for ourselves, a quest to understand the fundamental nature of life and the full range of its potential expression. And the discovery of extremophiles on our own planet has been one of the most profound and revolutionary developments in this quest. Extremophiles are organisms that do not just survive, but actively thrive in environments that we once considered to be completely inhospitable to life. They have been found in the boiling, acidic waters of hot springs, in the super salty brines of evaporation ponds, in the crushing pressures and absolute darkness of the deep sea floor, in the dry, frozen valleys of Antarctica, and even in the radioactive cores of nuclear reactors. The existence of these hardy and often bizarre organisms has completely shattered our old, narrow, and terrestrial-centric definition of habitability. They have shown us that life is far more resilient, far more adaptable, and far more creative than we ever imagined. And they provide us with a powerful and deeply inspiring set of analog environments for thinking about the potential for life on other worlds, particularly on the icy moons of our outer solar system. The deep-sea hydrothermal vents, for example, are perhaps our best analog for the potential habitats on the seafloor of Europa or Enceladus. These are ecosystems that are completely independent of sunlight. Their primary producers are not photosynthetic plants, but chemosynthetic bacteria, microbes that have evolved the remarkable ability to derive their energy from the chemical reactions between the hot, mineral-rich water of the vents and the cold, surrounding seawater. These bacteria form the base of a rich and complex food web, supporting a host of strange and beautiful creatures, like giant tube worms, blind white crabs, and ghostly pale fish. The discovery of these ecosystems in the 1970s was a profound revolution in biology. It showed us that life does not need the sun. It showed us that life can thrive in the most extreme conditions of pressure and temperature. And it provided us with a powerful and plausible model for how life could exist in the dark, sunless oceans of the icy moons. The microbes that have been found living in the subglacial lakes of Antarctica, like Lake Vostok, are another compelling analog. These are organisms that have been isolated from the outside world for millions of years, living in a cold, dark, and low-nutrient environment under kilometers of solid ice. They have evolved unique, slow-motion metabolisms that allow them to survive in this state of extreme energy conservation. These are exactly the kind of adaptations we might expect to find in the cold, dark oceans of a world like Ganymede or Callisto. The study of extremophiles is not just about finding interesting creatures in strange places. It is about understanding the fundamental, biochemical, and genetic mechanisms of adaptation. By studying the unique enzymes that allow a thermophile to function at boiling temperatures, or the antifreeze proteins that allow a psychrophile to survive in sub-zero conditions, we can learn about the fundamental limits of life's chemistry. And by studying the unique metabolic pathways that allow a chemotroph to live off of sulfur or iron, we can expand our vision of the possible chemical foundations for life. The extremophiles on Earth are a message of hope. They are a testament to the incredible tenacity and creativity of life. And they are a powerful and deeply scientific reason to believe that if life can find a way to thrive in the most extreme and unlikely of niches on our own planet, then it has almost certainly found a way to do the same on the countless other strange, beautiful, and potentially habitable worlds that are scattered throughout the vast and wonderful darkness of the cosmos. The chemical composition of a subsurface ocean is the key that can unlock its potential for life. The simple presence of liquid water is a necessary but not a sufficient condition for habitability. A truly life-bearing ocean must also be a rich and chemically dynamic environment. An environment that contains not just a solvent, but also the necessary elemental building blocks and a source of usable chemical energy. The salts that are dissolved in these oceans are one of the first and most important of these chemical clues. The presence of salts, like sodium chloride or magnesium sulfate, which have been inferred from the magnetic field data at Europa and have been directly detected in the plumes of Enceladus, is significant for several reasons. Firstly, as we have seen, salts act as a natural antifreeze, lowering the freezing point of water and helping to maintain the ocean in a liquid state, but they also play a crucial and often overlooked role in biological chemistry. The ions that are formed when these salts dissolve in water, like sodium, potassium, and chloride, are essential for a host of fundamental cellular processes, from maintaining the electrical potential across a cell membrane to regulating the flow of water in and out of the cell. An ocean that is too fresh or too salty would be a challenging environment for life as we know it. The interaction between the ocean water and the rocky, silicate seafloor is another critical factor. This process, known as serpentinization, is a chemical reaction between water and the minerals in the rock, a reaction that can release a number of important and life-sustaining chemical compounds. One of the most important of these is hydrogen gas. Hydrogen is a powerful source of chemical energy, and on Earth, there are entire ecosystems of microbes in the deep, subsurface biosphere that make their living by eating hydrogen. The detection of molecular hydrogen in the plumes of Enceladus is one of the most exciting and astrobiologically significant discoveries of the Cassini mission. It is a smoking gun for ongoing water-rock interactions on the seafloor, and a strong indication that there is a source of chemical energy available to power a potential chemosynthetic biosphere. The presence of organic molecules, the carbon-based building blocks of life, is another crucial piece of the puzzle. The discovery of a rich and complex suite of organic compounds in the plumes of Enceladus was a major breakthrough. It showed that the ocean of this tiny moon is not just a simple, salty water body, but is a complex chemical reactor, a place where the fundamental ingredients for life are not just present, but are actively being processed and cycled. The acidity, or pH, of the ocean is another critical parameter. The chemistry of life, as we know it, works best in an environment that is not too acidic and not too alkaline. And here, too, the news from Enceladus is incredibly promising. The analysis of the plume data suggests that its ocean is slightly alkaline, with a pH that is very similar to that of Earth's own oceans, a perfect environment for the complex organic chemistry that could lead to life. The chemical composition of a subsurface ocean is a complex and beautiful tapestry, a story that is woven from threads of geology, of chemistry, of tidal physics, and perhaps even of biology. And by carefully and patiently deciphering the chemical clues that are written in the faint, ghostly plumes of Enceladus, or in the subtle, magnetic whispers of Europa, we are beginning to read this story, a story that may, one day, lead us to the profound and deeply hoped for discovery that we are not the only living story in the vast and beautiful book of the cosmos. The presence of liquid water is the one non-negotiable requirement for life as we know it. It is the universal solvent, the medium in which the complex biochemical reactions of life take place. It is the matrix, the stage, the very cradle of life on our own planet, and it is the primary guiding principle in our search for life elsewhere. The icy moons of our outer solar system have, in the last few decades, emerged as some of the most compelling targets in this search, precisely because of the strong and growing evidence that they harbor vast and potentially long-lived oceans of liquid water beneath their frozen surfaces. This has led to a major and profound shift in our understanding of the habitable zone. The traditional, classical habitable zone is a relatively narrow, circular ring around a star, a Goldilocks zone where the temperatures are just right, not too hot, not too cold for liquid water to exist on a planet's surface. But the icy moons have shown us that this is a far too narrow and far too sun-centric view of habitability. A world can be far outside the classical habitable zone, in the cold, dark depths of the outer solar system, and still have a vast and potentially life-bearing liquid water ocean. as long as it has a strong internal heat source, like the tidal heating that is driven by the gravitational pull of a giant parent planet. This has dramatically expanded the real estate for potential life in our own solar system, and in the countless other planetary systems that are scattered throughout our galaxy. But the role of water is not just about providing a liquid medium. The interaction between liquid water and rock, as we have seen, is a powerful engine of chemical energy, a process that can support a thriving chemosynthetic biosphere in the complete absence of sunlight. The very presence of a liquid water ocean also has a profound, and often dramatic, impact on the geology and the climate of a world. The movement of water, in its liquid, solid, and gaseous forms, is a powerful driver of geological change. The geysers of Enceladus, or the fractured, icy tectonics of Europa. These are all manifestations of the power of water to shape a world. The presence of water ice on the surface of a moon also has a major impact on its thermal properties, its albedo, and its ability to retain an atmosphere. Water is not just an ingredient for life. It is a powerful planetary scale, geological and climatic agent. And the search for water, in all its forms, is one of the central and most exciting themes of modern planetary exploration. The upcoming missions to the icy moon, like the Europa Clipper and JUICE, are at their heart water-seeking missions. They are designed to confirm the presence of these hidden oceans, to characterize their properties, and to assess their potential for life. And they are part of a larger and even more ambitious human endeavor, the quest to understand the full cosmic story of water, a story that begins in the cold, dark, interstellar clouds where water ice is first formed, that continues in the protoplanetary disks where it is incorporated into comets and asteroids, and that culminates on worlds like our own, and perhaps on many others, in the formation of the vast, beautiful, and life-giving oceans that are the true and ultimate cradle of all that we know and all that we are. The study of extremophiles on Earth is not just a fascinating and often bizarre corner of biology. It is a profound and essential tool for astrobiology, a source of both inspiration and of concrete scientific models for how life might be able to survive and even thrive in the extreme and alien environments of other worlds. These remarkable organisms, from the microbes that live in the boiling, acidic waters of a Yellowstone hot spring to the bacteria that have been found dormant but still viable in 500,000-year-old Siberian permafrost, are a testament to the incredible resilience, adaptability, and chemical ingenuity of life. They have pushed the known physical and chemical limits of life on Earth far beyond what we once thought was possible. And in doing so, they have dramatically expanded our definition of a habitable environment. For the icy moons of our outer solar system, like Europa and Enceladus, the lessons from Earth's extremophiles are particularly compelling. The dark, cold, and high-pressure environments of their subsurface oceans, which at first glance seem so hostile, are in fact remarkably similar to the environments of our own. Deep-sea hydrothermal vents, the chemosynthetic bacteria that form the base of these vent ecosystems, which derive their energy not from sunlight, but from the chemical reactions of sulfur and hydrogen compounds, provide us with a powerful and plausible analog for the kind of life we might find in these distant, sunless oceans. The discovery of these organisms on our own planet has transformed the search for life on the icy moons from a purely speculative exercise into a scientifically grounded and deeply compelling quest. The extremophiles that have been found living within the solid ice of Antarctic glaciers and subglacial lakes are another powerful analog. These psychrophiles have evolved a host of remarkable biochemical adaptations to survive in their frozen world. including the production of antifreeze proteins that prevent the formation of damaging ice crystals within their cells, and a slow, patient metabolism that allows them to eke out a living in a state of near-permanent hibernation. These are exactly the kind of adaptations we might expect to find in any life that might exist within the icy shells or the cold, deep oceans of the outer solar system moons. The study of extremophiles is not just about finding interesting biological curiosities. It is about understanding the fundamental molecular machinery of life's resilience. By studying the unique enzymes, the specialized cell membranes, and the novel metabolic pathways of these organisms, we can begin to understand the universal chemical and physical principles of how life adapts to its environment. This is a knowledge that is not just useful for astrobiology. It also has a host of practical applications here on Earth, from the development of new industrial enzymes that can work at high temperatures to the search for new, life-saving antibiotics from previously unexplored microbial ecosystems. The extremophiles of Earth are a profound and beautiful message from our own planet. They are a message of hope, of resilience, of the incredible, and perhaps universal, creative power of the evolutionary process. They are the living proof that life is not a fragile, delicate flower that can only bloom in the most benign and garden-like of conditions. They are a tough, tenacious, and wonderfully stubborn weed, a life force that can take root and flourish in the most unlikely and most extreme of cosmic crevices. And that is, perhaps, the most powerful and the most inspiring reason of all to continue our search for our cosmic companions in the vast and beautiful wilderness of space. The exploration of the surfaces and the subsurfaces of the moons of our solar system is a grand technological and scientific challenge, a quest that requires the development of a host of new and often ingenious methods for probing these distant and alien worlds. Radar imaging is one of our most powerful tools for peering beneath the obscuring, icy crusts of moons like Europa. A powerful, ice-penetrating radar, mounted on an orbiting spacecraft like the upcoming Europa Clipper, can send radio waves down through the ice. These waves will bounce off of any internal boundaries, like the boundary between the ice and a liquid water ocean, or the boundary of a pocket of water that may be trapped within the ice shell itself. By carefully timing the return of these radar echoes, and by analyzing their strength and their properties, we can create a three-dimensional map of the subsurface, to measure the thickness of the ice, and to search for the telltale, bright reflection of a hidden liquid water ocean. Infrared spectroscopy is another crucial tool. By measuring the spectrum of the infrared light, the heat, that is being reflected or emitted from a moon's surface, we can determine its chemical composition. Different minerals and ices have unique spectral fingerprints in the infrared. This technique has been used to map the distribution of water ice, of salts, and of complex organic molecules on the surfaces of the icy moons, providing crucial clues about the composition of the oceans that may lie beneath. For a more direct, ground truth analysis, we will need to send landers and rovers. A future mission to Europa might include a stationary lander that could use a suite of sophisticated instruments to analyze the chemistry of the surface ice in incredible detail, searching for the preserved biosignatures of any life that may have been brought up from the ocean below. A more ambitious mission might include a rover that could traverse the fractured icy landscape, or even a cryobot, a robotic probe that could use a heated tip to slowly melt its way down through the kilometers of solid ice to reach the ocean itself. And once in the ocean, a small, autonomous, underwater vehicle, a hydrobot, could be released to explore this dark, alien, and wonderfully promising world. The plumes of Enceladus offer a more direct and technologically less challenging path to its hidden ocean. A spacecraft, like the proposed Enceladus Lifefinder mission, could simply fly through the geysers, collecting samples of the water vapor and the ice particles with a suite of sensitive mass spectrometers and other instruments. This would allow for a direct and incredibly detailed analysis of the ocean's chemistry, a search for the complex, organic molecules that could be a sign of life, without ever having to land on the moon or to drill through its ice. And for a world like Titan, with its thick, obscuring atmosphere, a different set of tools is required. The Cassini mission used a powerful cloud-penetrating radar to map the lakes, the rivers, and the dunes of its hidden hydrocarbon surface. And the upcoming Dragonfly mission will take this exploration to a whole new level. Dragonfly is a revolutionary concept, a nuclear-powered dual quadcopter, a robotic drone that will be able to fly through Titan's thick atmosphere, landing in multiple different locations to collect and to analyze samples. It will be a mobile, aerial, and astrobiological laboratory, a mission that will allow us to explore the complex, organic chemistry, and the potential for a different kind of life on this strange and beautiful alien world. The future of planetary exploration is a future of a rich and diverse toolkit of technologies, a future where we will use a combination of remote sensing from orbit, of in situ analysis from landers and rovers, and of direct sample collection from plumes and one day from the hidden oceans themselves, to piece together the complex and beautiful stories of these distant and wonderfully promising worlds. The potential ecosystems that might exist in the dark, cold, and high-pressure subsurface oceans of the icy moons are a source of endless and deeply fascinating scientific speculation. They would be worlds that are fundamentally different from our own. Sun-drenched biosphere, worlds where the rules of life and the very definition of an ecosystem might need to be rewritten. On Earth, the vast majority of life is ultimately powered by sunlight through the process of photosynthesis. But in the sunless depths of a European or an Enceladus ocean, this would not be possible. Life, if it exists there, must be powered by a different source of energy, the chemical energy that is being released from the moon's own geologically active interior. The primary model for such an ecosystem is our own deep-sea hydrothermal vents. But the ecosystems of the icy moons could be even more exotic. The high pressure of these deep oceans could lead to the formation of strange, high-pressure forms of ice, and the chemistry of the water could be very different from our own, perhaps with high concentrations of ammonia or methane, which could be used by a different kind of biochemistry. The life forms themselves would likely be microbial, but it is not impossible to imagine that. Over billions of years of evolution in a stable environment, more complex, multicellular life could have evolved. These would be creatures that are adapted to a world of absolute darkness, of crushing pressure, and of a slow, patient, and chemically driven metabolism. They might have evolved a form of bioluminescence, using their own internal light to communicate, to hunt, and to navigate in the dark. They might have evolved strange, soft, and flexible bodies to withstand the immense pressure. And their sensory world would be completely different from our own, a world that is dominated not by sight, but by the senses of touch, of pressure, and of chemistry. The food webs in these oceans would be simple, but potentially robust. The primary producers would be the chemosynthetic microbes at the base of the food chain. These would then be consumed by a second level of grazers, and perhaps even a third level of predators. But the overall biomass of such an ecosystem would likely be much lower than that of Earth's oceans, limited by the total amount of chemical energy that is available from the hydrothermal vents. The isolation of these subsurface oceans also has profound evolutionary implications. Each of these oceans would be a separate and completely isolated Genesis experiment. If life has arisen independently in the oceans of Europa, of Enceladus and of Ganymede, then we would have three independent examples of the origin of life in our own solar system, and a comparison of the biochemistry and the genetics of these three. Different life forms would be a scientific revolution of almost unimaginable proportions. It would allow us to begin to distinguish the universal, and perhaps necessary, features of life from the contingent and purely historical accidents of our own terrestrial evolution. Is DNA the only possible molecule for storing genetic information? Is the 20 amino acid-based protein chemistry the only way to build the machinery of a cell? The discovery of a second genesis of life in our own solar system would be the key that could unlock the answers to these deepest and most profound of all biological questions. The exploration of the potential ecosystems of the icy moons is a journey into a new and completely unknown biological frontier. It is a journey that is not just about searching for life, but about expanding our very definition of what life is and of what it can be. The hydrothermal vents that are scattered across the floor of Earth's deep oceans are one of the most profound and most astrobiologically significant discoveries of the 20th century. They are oases of life in a world of absolute darkness. Ecosystems that are powered not by the light of the sun, but by the heat and the chemistry of the Earth's own molten interior. These vents are found along the mid-ocean ridges, the vast underwater mountain chains where the Earth's tectonic plates are spreading apart. Here, cold, dense seawater seeps down into the fractured, volcanic rock of the ocean crust, where it is heated to extreme temperatures, up to 400 degrees Celsius, by the underlying magma. This superheated water then reacts with the surrounding rock, dissolving a rich cocktail of minerals and chemical compounds, like sulfur, iron, manganese, and hydrogen. This hot, chemical-rich fluid is then shot back up into the cold, deep ocean, creating the spectacular, chimney-like structures of the black smokers and the white smokers. And it is this chemical-rich fluid that is the lifeblood of the vent ecosystem. The primary producers here are not plants, but chemosynthetic bacteria and archaea. These remarkable microbes have evolved the ability to harness the chemical energy that is stored in the reduced compounds of the vent fluid, particularly hydrogen sulfide. In a process that is analogous to photosynthesis, they use this chemical energy to convert carbon dioxide into organic matter, forming the very base of the vent food web. And this food web is a rich and a surprisingly diverse one. It is populated by a host of strange and beautiful creatures that are found nowhere else on Earth. There are the giant tube worms, some of which can grow to be over 2 meters long, which have no mouth and no digestive tract, but which live in a symbiotic relationship with the chemosynthetic bacteria that they house in a specialized organ. There are the ghostly white crabs, the blind shrimp, the strange, stalked barnacles. All of these animals are ultimately dependent on the constant life-giving flow of chemical energy from the Earth's interior. The study of these hydrothermal vent ecosystems has had a profound impact on our thinking about the origin and the evolution of life. They have shown us that life can thrive in the most extreme conditions of temperature, of pressure, and of darkness. And they have provided us with a powerful and deeply plausible model for where and how life might have first arisen on the early Earth, in the protected, energy-rich, and chemically dynamic environment of a primordial, deep-sea vent. And, of course, they are our best and most compelling analog for the potential habitats for life on other worlds, particularly on the icy moons of Europa and Enceladus. The discovery of evidence for active hydrothermal vents on the seafloor of Enceladus's subsurface ocean has transformed this small, distant moon into one of the most exciting targets in our search for extraterrestrial life. It suggests that the same chemosynthetic-based ecosystems that we have found in the deepest, darkest corners of our own oceans could be thriving right now in the hidden, watery depths of a small, icy moon, 500 million miles away. The hydrothermal vents of Earth are a profound and beautiful reminder that life is not just a surface phenomenon, a creature of the sun. It is a planetary phenomenon, a process that is deeply and intimately intertwined with the geological and the chemical life of the planet itself. And it is a process that may be far more common and far more adaptable than we ever dared to imagine. The discovery of life in the extreme environments of our own planet would be a discovery of profound and paradigm-shifting significance. It would be a moment that would force us to fundamentally reevaluate our understanding of biology, of our place in the universe, and of the very definition of life itself. The first and most immediate consequence would be a radical expansion of our concept of the habitable zone. We would be forced to abandon our old, narrow, and sun-centric view of habitability and to embrace a much broader, more inclusive, and more astrobiologically optimistic perspective. The discovery of a thriving chemosynthetic ecosystem in the dark, cold, and high-pressure ocean of Europa, for example, would prove that life does not require sunlight, that it does not require a terrestrial-like surface environment, that it can arise and flourish in conditions that we once considered to be completely and utterly hostile. This would dramatically expand the real estate for potential life in our own solar system and in the countless other planetary systems that are scattered throughout our galaxy. The focus of our search would shift from the exclusive study of Earth-like planets in the classical habitable zone to a much broader and more exciting exploration of the diverse and often hidden niches where life might be able to gain a foothold. The discovery of a second genesis of life, a life that has an independent origin from our own, would also be a revolution in the field of biology. For all of its incredible diversity, all of the life on Earth is, at a fundamental biochemical level, the same. We all use the same DNA-based genetic code. We all use the same 20 amino acid-based protein chemistry. We are all, in a very real sense, members of a single, extended family, the descendants of a single, last universal common ancestor. But if we were to find life on Europa, and if we were to discover that it uses a different genetic code, a different set of amino acids, a different fundamental biochemistry, it would be a discovery of almost unimaginable importance. It would be our first glimpse of a truly alien biology. It would allow us to begin to distinguish the universal, and perhaps necessary, features of life from the contingent and purely historical accidents of our own terrestrial evolution. It would be the birth of a truly universal biology, a science that is not just about the study of life on Earth, but about the study of life in all its potential forms, as a fundamental phenomenon of the cosmos. And the philosophical and cultural implications of such a discovery would be immense. It would be a definitive end to our long and often lonely sense of cosmic solitude. It would be a profound and deeply humbling reminder that we are not the pinnacle of creation, not the single, special, and miraculous endpoint of a cosmic story. We would be just one of a potentially vast and wonderfully diverse galactic community of life. This would be a discovery that would resonate through every aspect of our culture, of our art, of our religions, of our philosophy. It would be a discovery that would change forever what it means to be a human being, living a life of conscious awareness in a universe that is not just full of stars, but is also, perhaps, full of life. The challenge of sending a mission to explore the icy moons of our outer solar system is one of the most difficult and most ambitious in the history of planetary exploration. It is a journey that pushes the very limits of our technology, our ingenuity, and our patience. The first great challenge is the environment itself. The outer solar system is a cold, dark, and hostile place, and the moons of Jupiter, in particular, are bathed in an incredibly intense and damaging radiation field, a product of Jupiter's immense and powerful magnetosphere. A spacecraft that is designed to orbit Europa for an extended period of time must be a veritable flying fortress. Its sensitive electronics hardened and shielded against this constant and lethal bombardment of high-energy particles. The temperatures are also extreme, requiring a sophisticated and robust thermal control system to keep the spacecraft's instruments at their optimal operating temperatures. The second great challenge is the distance. A journey to Jupiter takes years, and once there, the communication with the spacecraft is subject to a long and unavoidable delay. This means that our robotic explorers must be given a high degree of autonomy, the ability to make their own intelligent decisions in real time, without the constant guidance of a human operator back on Earth. The third, and perhaps greatest, challenge is the ice itself. The subsurface oceans of these moons are hidden beneath a thick, and as yet poorly understood, shell of solid cryogenic ice. To directly explore these oceans, to search for the signs of life in their hidden depths, we will one day need to develop the technology to land on this icy surface, and then to drill or to melt our way down through kilometers of ice. This is an engineering challenge of almost unimaginable difficulty. It will require the development of new and highly autonomous robotic systems that can operate for years in a cold, dark, and completely inaccessible environment, millions of miles from home. But the scientific prize is so great that we are, slowly but surely, beginning to develop the technologies and the missions that will be needed to meet these challenges. The Europa Clipper mission is the first, crucial step in this long journey. It is not a lander or a driller, but a sophisticated orbital reconnaissance mission. It will use a suite of powerful remote sensing instruments, a high-resolution camera to map the surface, an infrared spectrometer to determine its chemical composition, and a powerful ice-penetrating radar to measure the thickness of the ice shell and to search for the signature of the ocean below to perform a detailed global characterization of Europa and its potential for life. And the JUICE mission will perform a similar and complementary investigation of Ganymede. These are the missions that will lay the groundwork, that will provide the maps, that will allow us to select the most promising and most technologically accessible landing sites for the more ambitious and even more exciting missions that will follow. The journey to the icy moons is a multi-generational one. It is a journey that will require a long-term and sustained commitment of resources, of creativity, and of our collective human will to explore. But it is a journey that is driven by one of the most profound and most deeply human of all questions. And it is a journey that may, one day, lead us to one of the most profound and most beautiful of all discoveries. The science of spectroscopy is our cosmic Rosetta Stone. It is the tool that allows us to decipher the chemical language of the universe, to read the stories that are written in the faint, ancient light of the distant stars and the reflected, ghostly glow of the planets and the moons. The basic principle is a simple and a beautiful one. Every atom and every molecule has a unique and characteristic set of energy levels that its electrons can occupy. When light passes through a gas of these atoms or molecules, the electrons will absorb photons of specific and very precise wavelengths, corresponding to the energy differences between these levels. This creates a unique and beautiful pattern of dark absorption lines in the spectrum of the light. Conversely, when a gas is heated, its electrons will be excited to higher energy levels, and as they fall back down, they will emit photons of specific and very precise wavelengths, creating a bright pattern of emission lines. This unique spectral fingerprint is the key that allows us to determine the chemical composition of a distant celestial object without ever having to leave the Earth. In the context of the icy moons, Spectroscopy is one of our most powerful tools. By analyzing the spectrum of the sunlight that is reflected from the surface of a moon like Europa, we can identify the chemical composition of its surface ice. This is how we know that Europa's surface is not just pure water ice, but is also contaminated with a host of other materials, including salts, like magnesium sulfate, and simple organic molecules. These non-ice materials are thought to be the frozen remnants of the ocean water that has been brought up to the surface through geological activity, and they provide us with crucial, indirect clues about the chemical composition and the potential habitability of the hidden ocean below. We can also use spectroscopy to analyze the plumes of Enceladus. As the Cassini spacecraft flew through these geysers, its mass spectrometer and its infrared spectrometer were able to directly taste and see the chemical composition of the water vapor and the ice particles. This is how we discovered the presence of salts, of silica, and of a rich and complex suite of organic molecules. The definitive evidence for a habitable and geologically active subsurface ocean, and we can use spectroscopy to study the atmospheres of these worlds. Titan, with its thick nitrogen and methane-rich atmosphere, is a prime target. By analyzing the spectrum of the sunlight that filters through its atmosphere, we can measure the abundances of different gases and search for the complex organic molecules that are being created by the interaction of sunlight and methane in its upper atmosphere, a process that is thought to be similar to the prebiotic chemistry that may have occurred on the early Earth. Spectroscopy is a science of incredible subtlety and precision. It is a science that allows us to take the faint, and often featureless, light from a distant world and to transform it into a rich and detailed story of its chemistry, its geology, and its potential for life. It is a testament to the power of the human mind to find the deep and often hidden, order and meaning in the beautiful and wonderfully complex light of the cosmos. The presence of organic molecules, the carbon-based building blocks of life, in the subsurface oceans of the icy moons is one of the most exciting and most astrobiologically significant discoveries of the modern era of planetary exploration. It is a discovery that has transformed these distant, frozen worlds from simple geological curiosities into some of the most compelling and most promising places in our solar system to search for extraterrestrial life. Organic molecules are the fundamental Lego bricks of biology as we know it. They are the monomers, the amino acids, the nucleotides, the sugars, the fatty acids that are linked together to form the great polymers of life, the proteins, the DNA, the RNA, the cell membranes. The discovery of a rich and complex suite of these organic molecules in the plumes of Enceladus is a profound and a beautiful one. It tells us that the ocean of this tiny moon is not a sterile, inorganic brine. It is a living chemical reactor, a place where the fundamental ingredients for life are not just present, but are being actively synthesized and cycled. The source of these organic molecules is still a matter of scientific debate. Some of them may have been delivered to the moon by the constant rain of comets and carbon-rich asteroids over the history of the solar system. But the sheer abundance and complexity of the molecules detected by Cassini suggests that many of them are likely being created in situ, in the moon's own internal chemical laboratory. The hydrothermal vents that are thought to exist on the seafloor of Enceladus's ocean are the prime candidate for this kind of prebiotic synthesis. The hot, mineral-rich water of these vents, combined with the dissolved carbon dioxide and other simple molecules in the ocean, creates the perfect, energy-rich environment for the formation of more complex organic compounds, a process that is very similar to the one that is thought to have led to the origin of life on the early Earth. The discovery of organic molecules on the surface of Europa, while more indirect, is no less tantalizing. The spectroscopic data from the Galileo mission and from ground-based telescopes has revealed the presence of a number of simple, organic compounds that are mixed in with the surface ice. particularly in the regions of recent geological activity. These are thought to be the frozen remnants of the ocean water that has been brought to the surface, and they provide a strong, albeit circumstantial, piece of evidence that Europa's hidden ocean, like Enceladus's, is also a chemically rich and organic-bearing environment. The presence of organic molecules in these subsurface oceans is a crucial and deeply hopeful piece of the astrobiological puzzle. It tells us that two of the three essential ingredients for life as we know it, liquid water and the necessary organic building blocks, are present on these distant worlds. The final and most crucial ingredient is a source of usable chemical energy. And here, too, the evidence from the plumes of Enceladus, with their telltale signatures of hydrogen gas and silica nanoparticles, is pointing strongly towards the existence of the very same hydrothermal vent-based energy sources that power the deep, dark ecosystems of our own planet. The story that is emerging from the icy moons is a story of incredible and deeply hopeful convergence. It is a story that suggests that the conditions and the chemistry that led to the origin of life on our own small rocky planet may not be a rare or a miraculous exception, but may be a common and perhaps even an inevitable outcome of the laws of physics and chemistry, playing out on the countless watery worlds that are likely scattered throughout our galaxy and throughout the universe. The radiation environment of the outer solar system, particularly in the vicinity of the giant planet Jupiter, is one of the most extreme and most hostile in our entire solar system. And it is a factor that has a profound and often complex impact on the potential for life on the icy moons that orbit within it. Jupiter has an immense and incredibly powerful magnetic field, a magnetosphere that is thousands of times stronger than the Earth's. This magnetic field acts like a giant, cosmic particle accelerator, trapping and accelerating charged particles, electrons, protons, and ions from the solar wind and from the volcanic eruptions of its moon, Io, to incredible relativistic energies. The result is a series of intense and deeply lethal radiation belts that surround the planet, Europa, which orbits deep within this magnetosphere, is subject to a constant and ferocious bombardment of this high-energy radiation. The surface of Europa is one of the most radioactive places in our entire solar system. Any unprotected human astronaut on its surface would receive a lethal dose of radiation in a matter of hours, and any complex organic molecules that might be brought to the surface from the ocean below would be rapidly destroyed by this constant, chemical bond-breaking rain of energetic particles. In this sense, the radiation environment of Europa is a profound and deeply challenging obstacle to the existence of life, at least on its surface. But this same destructive force can also be a creative one. The radiation that bombards the surface ice of Europa is a powerful engine of chemistry. It can break apart the simple water-ice molecules, creating a host of highly reactive and chemically powerful oxidant molecules like hydrogen peroxide and sulfuric acid. These oxidants, if they could be transported down into the subsurface ocean through the cracks and the convective churning of the ice shell, could provide a powerful and non-geothermal source of chemical energy for a potential biosphere. This is a fascinating and deeply paradoxical idea that the same life-destroying radiation on the surface could be the ultimate, life-giving source of energy for an ocean that is hidden deep below. The other icy moons, which orbit further away from their parent planets, are in a much more benign radiation environment. The surface of Enceladus, for example, is much less radioactive than the surface of Europa, which could make it a much more hospitable environment for any organic molecules that are brought to the surface in its plumes. Ganymede, with its own intrinsic magnetic field, has a small, protective magnetobubble that shields it from some of the harshest radiation from Jupiter. The radiation environment of the icy moons is a complex and often double-edged sword. It is both a profound threat and a potential source of creative chemical energy. And understanding this complex interplay between the destructive and the creative power of radiation is a crucial part of assessing the true and ultimate astrobiological potential of these strange, beautiful, and wonderfully promising worlds. The existence of a source of usable chemical energy is the third and final essential ingredient for life as we know it, alongside liquid water and the necessary organic building blocks. And in the dark, sunless depths of the subsurface oceans of the icy moons. The search for this energy is a search for the geological and the chemical processes that can power a biosphere in the complete absence of sunlight. The primary and most promising of these potential energy sources is the process of serpentinization. This is a chemical reaction that occurs when water interacts with certain kinds of iron and magnesium-rich minerals in a rocky seafloor. Minerals that are common in the kind of rocks that are thought to make up the mantles of the icy moons. This reaction produces a number of important and life-sustaining chemical byproducts, including heat, a variety of simple organic molecules, and, most importantly, molecular hydrogen. Hydrogen is a powerful chemical fuel. On Earth, there are entire ecosystems of microbes, particularly in the deep subsurface biosphere, that make their living by eating hydrogen, combining it with carbon dioxide in a process called methanogenesis to produce methane and to generate the energy they need to live. The detection of a significant amount of molecular hydrogen in the plumes of Enceladus is one of the most exciting and most astrobiologically significant discoveries of the Cassini mission. It is a smoking gun, a direct and powerful piece of evidence for ongoing water-rock interactions, for serpentinization, and for the existence of a rich chemical energy source on the seafloor of this tiny, distant moon. This is the very same chemical fuel that powers the chemosynthetic ecosystems of our own. Deep-sea hydrothermal vents, geothermal energy, the heat that is flowing out from the moon's own rocky core, is another potential energy source. This heat can be generated by the decay of radioactive elements in the core, and, more significantly, by the tidal heating that is driven by the gravitational pull of the parent planet. This heat can not only keep the ocean in a liquid state, but it can also drive a vigorous hydrothermal circulation, creating a network of hot, chemical-rich vents on the seafloor. These vents would be oases of energy and of nutrients, the perfect, and perhaps even the ideal, location for life to arise and to thrive. And as we have seen, the radiation that bombards the surfaces of these moons can also be an indirect and powerful source of chemical energy. The reactive oxidant molecules that are created in the surface ice can, if they are transported down into the ocean, provide the other half of the chemical redox battery that a biosphere would need to survive, the hydrogen and the other reduced compounds that are being produced at the seafloor are the food. The oxidants from the surface are the oxygen, the chemical that is needed to burn the food and to release its energy. The combination of all these different potential energy sources, the chemical energy from serpentinization, the geothermal energy from the core, and the radiolytic energy from the surface paints a picture of the subsurface oceans of the icy moons as being remarkably rich and potentially very habitable environments. They are not just cold, dark, and static bodies of water. They are dynamic, evolving, and geochemically active worlds where the fundamental energy-generating processes that are necessary for life may not just be present, but may even be abundant. The potential for microbial life to survive, and even to thrive, in the extreme and alien environments of the subsurface oceans of the icy moons is a question that pushes our understanding of biology to its very limits. These would be ecosystems that are fundamentally different from our own. Sun-drenched biosphere. Ecosystems that are governed by a different set of rules, and that may be populated by a different, and truly alien, kind of life. The first, and most fundamental, challenge for any life in these oceans would be the complete absence of sunlight. This means that photosynthesis, the process that powers almost all of life on Earth, would be impossible. Life, if it exists there, must be chemosynthetic, deriving its energy not from the light of a star, but from the chemical reactions of the minerals and the gases that are being released from the Moon's own geologically active interior. The microbes at the base of this food web would be the chemotrophs, the rock eaters, the organisms that have evolved the remarkable ability to make a living from the strange and often toxic chemical soup of a hydrothermal vent. The second great challenge would be the extreme physical conditions of these oceans. They would be worlds of intense, crushing pressure, of near-freezing temperatures, and of a chemistry that could be very different from our own. Life in these environments would need to be extremophilic in the truest sense of the word. It would need to have evolved a host of remarkable biochemical adaptations to survive. It would need specialized cell membranes that can remain fluid at low temperatures. It would need piezophilic proteins that can function under high pressure. And it might need to have evolved a completely different, and perhaps more robust, biochemistry. One that is better adapted to the specific chemical conditions of its own, unique, watery world. The ecosystems themselves would likely be simple, but they could be surprisingly diverse. There would be a range of different metabolic niches for the microbes to exploit, depending on the specific chemical gradients that are present in different parts of the ocean, and it is not impossible to imagine that. Over the billions of years that these oceans have likely existed, a more complex, multicellular life could have evolved. These would not be fish or whales, but they could be strange and beautiful. Creatures that have evolved to graze on the microbial mats that would likely cover the hydrothermal vents, or perhaps even to become the first alien predators in these dark, hidden worlds. The discovery of such a second genesis of life, a life that has an independent origin from our own, would be a discovery of almost unimaginable significance. It would be our first glimpse of a truly universal biology. It would allow us to begin to understand which of the features of our own terrestrial life are universal and perhaps necessary, features of life everywhere, and which are just the frozen, historical accidents of our own particular evolutionary path. Is DNA the only possible molecule for life? Is water the only possible solvent? The discovery of a thriving microbial ecosystem in the dark, cold ocean of a distant icy moon would be the key that could unlock the answers to these deepest and most profound of all biological questions. The discovery of even microbial life on a world like Europa or Enceladus would be a moment of profound and paradigm-shifting significance for all of humanity. It would be a discovery that would resonate far beyond the narrow confines of the scientific community. A discovery that would touch upon our deepest philosophical, cultural, and even spiritual assumptions about our place in the universe. The first and most immediate consequence would be the definitive end of our cosmic solitude, the knowledge that we are not alone, that the phenomenon of life is not a unique and perhaps miraculous accident of our own small planet, but is a more common and perhaps even an inevitable feature of the cosmos, would be a profound and deeply humbling realization. It would be the final and most powerful of all the Copernican revolutions, the ultimate decentering of humanity from a privileged position in the grand scheme of things. This would have a deep and transformative impact on our collective human worldview. It could foster a new sense of global unity, a recognition that we are all, in the end, Earthlings, members of one particular branch of a much larger and much more diverse cosmic family of life. It could also inspire a new and more profound sense of our own ecological responsibility. The discovery of another, and perhaps very fragile, biosphere in our own solar system would be a powerful and deeply poignant reminder of the preciousness and the fragility of our own. But the implications would go even deeper. The discovery of a second genesis of life, a life that is biochemically and genetically distinct from our own, would be a scientific revolution of almost unimaginable proportions. It would be the birth of a truly universal biology, a science that is no longer just the study of a single terrestrial example of life, but is the study of the fundamental, and perhaps universal, principles that govern the emergence and the evolution of living systems everywhere. It would allow us to begin to answer some of the deepest and most profound of all scientific questions. What is life? Is it a rare and improbable fluke, or is it a natural and emergent property of a complex chemical universe? The discovery of an independent origin of life in our own solar system would be a powerful argument for the latter. It would suggest that the universe is not a dead, sterile, and meaningless void that happens to contain a few rare pockets of life. It would suggest that the universe is, in some deep and fundamental way, bio-friendly, a cosmos that is pregnant with the potential for life, a universe that is, in a sense, destined to wake up and to become aware of itself. This would be a discovery that would have a profound impact on our philosophical and even our spiritual understanding of the cosmos. It would provide a new and deeply scientific context for some of the oldest and most enduring of all human questions. The questions of meaning, of purpose, and of our ultimate connection to the vast and beautiful universe that has given us birth. The search for life on the icy moons is more than just a scientific quest. It is a human quest, a journey into the heart of one of our oldest and most deeply held of all human dreams. The geological activity of the icy moons, from the volcanic fireworks of Io to the subtle, icy tectonics of Europa, is a beautiful and powerful testament to the dynamic, and often violent, nature of our solar system. And it is a story that is, for the most part, written in the language of gravity. The primary engine of this geological activity is the phenomenon of tidal heating, the constant frictional flexing of a moon's interior that is driven by the gravitational pull of its giant parent planet. This is a process that is most dramatic on the innermost of Jupiter's Galilean moons. Io, locked in a tight and slightly elliptical orbit. Io is constantly being squeezed and stretched by Jupiter's immense gravity, a process that generates so much internal heat that it has turned the moon into a veritable solar system-scale pizza, a world of constant and often spectacular volcanic eruptions, with vast molten sulfur lakes and plumes of sulfur dioxide that shoot hundreds of kilometers into space. Io is a world that is, in a very real sense, being turned inside out by the power of gravity. On the next moon out, Europa, the tidal heating is less intense, but it is still powerful enough to maintain a vast and potentially life-bearing liquid water ocean beneath its icy crust. And it is this tidal flexing that is thought to be the driving force behind the moon's strange and beautiful surface geology. The long, linear cracks and ridges that crisscross its surface are thought to be the result of the constant tidal stress that is fracturing and deforming the ice shell. And the regions of chaotic terrain are thought to be the result of the convective churning of the ice, or perhaps even the direct disruptive influence of the ocean below. Europa is a world whose surface is a direct and dynamic expression of the powerful tidal heartbeat of its hidden ocean. Further out in the solar system, in the realm of Saturn, we find another and equally spectacular example of this tidally driven geology, the south polar plumes of Enceladus. Here, the tidal flexing of the moon's small, icy body is thought to be concentrated in a series of long, parallel fissures, the tiger stripes, creating a network of hotspots that can keep the subsurface ocean in a liquid state and that can power the dramatic, geyser-like eruptions of water and ice into space. But the geological story of the moons is not just about tides. It is also a story of a complex interplay between internal heat, of surface composition, and of the history of impacts from the early solar system. The surface of Ganymede, for example, is a tale of two different geological epochs. It has ancient, dark, and heavily cratered regions that have been preserved for billions of years, and it has younger, brighter, and more geologically active regions that are covered in a complex network of grooves and ridges, a sign of a period of intense tectonic activity in the moon's past, a period that was likely driven by a combination of tidal forces and the internal convective heat of its own large and differentiating interior. The gravitational interactions between the moons themselves also play a crucial, and often subtle, role in shaping their geology. The orbital resonance between Europa and Ganymede is what keeps their orbits elliptical and is therefore the ultimate and sustaining cause of their tidal heating. The gravitational dance of the moons is a complex and beautiful piece of celestial choreography, a dance that has shaped their geology, their evolution, and their ultimate potential for life. The study of the geology of the moons is a journey into the deep, and often hidden, history of our solar system. It is a story that is written in the language of craters, of cracks, of volcanoes, of plumes. And it is a story that is telling us that these are not just cold, dead, and static worlds. They are active, dynamic, and geologically living places. Worlds that are constantly being reshaped and reinvented by the powerful and often beautiful forces of gravity. The prospect of sending a mission to directly explore the subsurface oceans of the icy moons is one of the most exciting, and also one of the most technologically challenging goals in all of modern planetary science. It is a journey that will require a new generation of sophisticated and highly autonomous robotic explorers. And it is a journey that is being actively planned and developed by space agencies around the world. The first, and most crucial, step in this long journey is a detailed orbital reconnaissance. This is the goal of NASA's Europa Clipper mission and the European Space Agency's JUICE mission. These are large, sophisticated, and powerfully instrumented spacecraft that will perform a series of close flybys of Europa and Ganymede. Their primary goal is to confirm the existence of the subsurface oceans, to measure their depth and their salinity, and to map the thickness of the overlying ice shell. They will do this using a suite of powerful, remote sensing instruments, including a high-resolution camera, a thermal imager, a magnetometer, and, most importantly, a powerful ice-penetrating radar. This radar will be able to see through the ice, to search for the bright, telltale reflection of a liquid water ocean below, and to map out the internal structure of the ice shell itself, searching for the potential thin spots or the trapped subsurface lakes that could be the prime targets for a future lander. These orbital missions will be the scouts, the cartographers, the ones who will provide us with the detailed maps that we will need to plan the next and even more ambitious step. A landing. A future lander mission to Europa would be a technological tour de force. It would have to autonomously navigate its way to a safe and scientifically interesting landing site on the moon's fractured and potentially hazardous icy surface. And once there, it would use a suite of sophisticated instruments to perform the first direct in situ analysis of the surface ice. It could use a mass spectrometer to measure its chemical composition, a microscope to search for the frozen remnants of any microbial life, and a seismometer to listen for the faint, telltale rumbles of the ocean that may be sloshing and churning just a few kilometers below. But the ultimate dream, the holy grail of icy moon exploration, is to go one step further, to directly access and explore the oceans themselves. This would require the development of a cryobot, a robotic probe that could use a combination of heat and mechanical drilling to melt its way down through the kilometers of solid, cryogenic ice. This is an immense, and perhaps a multi-decade, engineering challenge. The cryobot would have to be completely autonomous, able to navigate its way through the unknown and potentially complex structure of the ice shell. And it would have to be able to maintain a communication link with the surface lander, perhaps by unreeling a long fiber optic cable as it descends. And then, after a journey that could take years, it would finally break through into the dark, hidden, and completely unknown world of the subsurface ocean. At that moment, it would release a small, autonomous, underwater vehicle, a hydrobot. This robotic submarine, equipped with its own lights, cameras, and scientific instruments, would be our first true emissary to this alien and wonderfully promising new world. It would be a moment of almost unimaginable scientific and human significance, a moment that would be remembered for all of history. The moment when we, for the first time, dipped our toes into the vast, dark, and potentially life-bearing waters of another world. The simulation of the extreme, and often alien, conditions of the subsurface oceans of the icy moons in a laboratory setting here on Earth is a crucial and often overlooked part of our quest to understand these distant worlds. While our space missions can provide us with invaluable remote sensing data, it is in the laboratory that we can perform the controlled, repeatable experiments that are necessary to truly understand the complex physical and chemical processes that may be at play in these hidden, watery realms. To do this, scientists have had to become a kind of cosmic experimental chef, carefully creating a recipe that can mimic the conditions of a European or an Enceladus ocean. The first ingredient is pressure. The oceans of the icy moons are likely to be tens or even hundreds of kilometers deep, which means that the pressure at the seafloor could be hundreds or even thousands of times greater than the atmospheric pressure at sea level on Earth. To simulate this, scientists use high-pressure chambers, robust steel vessels that can be pressurized to these extreme levels. The second ingredient is temperature. These oceans are likely to be very cold, close to the freezing point of water, but they are also likely to have thermal gradients, with warmer water near the hydrothermal vents on the seafloor and colder water near the ice shell above. To simulate this, the laboratory chambers are equipped with sophisticated cooling and heating systems, allowing scientists to precisely control the temperature and to create the kind of thermal gradients that could drive a vigorous ocean circulation. The third and most crucial ingredient is the chemistry. We know from the plume data of Enceladus that these oceans are not pure water, but are a complex, salty brine, rich in dissolved minerals and organic molecules. To simulate this, scientists create their own alien ocean recipes in the lab, carefully mixing different salts, gases, and organic compounds to match the chemical compositions that have been inferred from our spacecraft observations. And once this simulated alien ocean has been created, the real experiments can begin. Scientists can study how different terrestrial microbes, particularly the extremophiles that have been found in our own deep oceans and subglacial lakes, are able to survive and even to thrive in these simulated extraterrestrial conditions. This can give us crucial insights into the potential biochemical and genetic adaptations that any life on these moons might need to have evolved. They can also study the abiotic chemical processes that can occur in these environments. They can simulate the conditions of a hydrothermal vent, for example, and study the complex organic chemistry that can arise from the interaction of hot, mineral-rich water with the dissolved gases in the ocean. This is a crucial part of the search for life, as it allows us to understand the background chemistry of these worlds to distinguish the potential biological signals from the purely geological and chemical ones. These laboratory simulations are a vital and often unsung part of the process of planetary exploration. They are the bridge that connects the abstract, and often sparse, data from our space missions with a more concrete and more tangible understanding of the physical and chemical realities of these distant and wonderfully mysterious worlds. The salts that are dissolved in the subsurface oceans of the icy moons are more than just a chemical curiosity. They are a crucial and multifaceted player in the astrobiological story of these worlds. Their presence, which has been inferred at Europa and directly detected at Enceladus, has a profound impact on the physical, the chemical, and the potential biological properties of these hidden watery environments. The most fundamental role of these salts is as a natural and very effective antifreeze. The addition of a dissolved salt to water lowers its freezing point, a phenomenon that is familiar to anyone who has ever salted an icy sidewalk in the winter. In the cold, dark depths of the outer solar system, where the ambient temperatures are far below the normal freezing point of water, this effect is absolutely critical. It is the presence of a salty brine, not just pure water, that makes it much easier for these subsurface oceans to remain in a liquid state, even with a relatively modest internal heat source. But the salts are not just a physical agent, they are also a chemical one. The specific types of salts that are present and their concentrations can have a major impact on the ocean's chemistry and on its potential for life. The ions that are formed when these salts dissolve sodium, potassium, chloride, magnesium, sulfate are essential bioavailable nutrients that are required for a host of fundamental cellular processes. A purely freshwater ocean would be a much more challenging environment for life to arise and to thrive in. The salts can also influence the acidity, or pH, of the ocean, another critical parameter for habitability, and they are a key player in the process of water-rock interaction at the seafloor, the process that is thought to be the primary source of chemical energy for these dark, sunless ecosystems. The salts are also a powerful and very useful tracer for our remote sensing exploration of these worlds. A salty ocean is a conductive one, and as we have seen, it is the detection of the induced magnetic field that is generated as Europa moves through Jupiter's magnetosphere that provides the strongest and most direct evidence for the existence of its global salty ocean. The salts that are brought to the surface and are frozen into the ice of Europa, or are spewed out into space in the plumes of Enceladus, also provide us with a direct chemical fingerprint of the ocean below. By analyzing the specific spectral signatures of these salts with our remote sensing instruments, we can begin to deduce the detailed chemical composition of the hidden oceans themselves. The story of the salts in the oceans of the icy moons is a story that is written on all scales, from the microscopic biochemical processes of a hypothetical alien cell to the global scale electromagnetic interactions of an entire moon. And it is a story that is a beautiful testament to the deep, and often surprising, interconnectedness of the physical, the chemical, the geological, and the potential biological processes that are at play in these strange, beautiful, and wonderfully promising watery worlds. The potential life that might exist in the deep, dark, and isolated oceans of the icy moons would be a life that is truly and profoundly alien. It would have evolved in an environment that is completely different from any on the surface of the Earth, an environment of absolute darkness, of crushing pressure, and of a slow, patient, and chemically driven metabolism. The evolution of life in these worlds would have followed a different and perhaps a deeply strange path. The absence of sunlight would mean that the very concept of a day or a night of a season would be meaningless. Life in these oceans would be adapted to a world of eternal, unchanging darkness, a world whose only rhythms are the slow, geological rhythms of the hydrothermal vents and the gentle and almost imperceptible ebb and flow of the tides. The sensory world of these alien organisms would be completely different from our own. Vision, our most dominant sense, would be useless. Instead, life in these oceans would have evolved to sense its world through other modalities, through the sense of touch, of pressure, of chemical gradients, of sound. These would be creatures that see the world through their sense of smell, that talk to each other through the language of chemistry, that feel the presence of a predator or a prey through the subtle pressure waves in the water around them. They might have evolved a form of bioluminescence, not as a way to see, but as a way to communicate, to attract a mate, or to startle a predator, creating a world of silent and beautiful, ghostly light in the eternal darkness. The ecosystems themselves would be built on a foundation that is completely different from our own. Instead of the vast green forests and the sun-drenched, plankton-filled oceans of the Earth, the primary producers in these worlds would be the humble and almost invisible chemosynthetic microbes that cluster around the life-giving warmth and the chemical energy of the hydrothermal vents. And from this microbial base, a more complex, and perhaps a deeply strange, food web could have evolved. There could be alien grazers, creatures that have evolved to feed on the microbial mats. And there could be alien predators, sleek and perhaps terrifying, hunters of the deep. But the evolution of life in these isolated oceans would not just be a matter of adaptation to a different environment. It would also be a matter of a different and completely independent history. The life on Europa, if it exists, would be a second Genesis, a life that has a completely different origin and a completely different biochemical and genetic makeup from the life on Earth. A comparison of these two independent biologies would be a scientific revolution of almost unimaginable proportions. It would be our first glimpse of a truly universal biology. It would be a journey into a new and completely unknown biological frontier. A journey that would force us to confront the deepest and most profound of all questions: what is life? And what, in the vast and beautiful diversity of the cosmos, is it truly capable of becoming? The search for biosignatures, the telltale chemical and physical fingerprints of life, is the central and most challenging task of modern astrobiology. It is a quest that requires us to think deeply and creatively about what the universal and detectable signs of life might be, especially in an environment that is as alien and as inaccessible as a subsurface ocean on a distant, icy moon. The most sought after, and perhaps the most definitive, of all biosignatures would be the detection of complex organic molecules that have a clear and unambiguous biological origin. This could be the discovery of a specific and complex biomolecule, like a protein or a nucleic acid, that is unlikely to be formed by purely abiotic chemical processes. Or it could be the discovery of a strange and statistically unlikely distribution of smaller organic molecules. Life, as we know it, is very picky. It tends to use only a small subset of all the possible chemical building blocks. For example, all of the proteins on Earth are made from the same 20 specific amino acids, and all of these amino acids are of a single left-handed chirality or mirror image form. The discovery of a similar and highly selective chemical pattern in the organic molecules of an alien ocean would be a powerful and deeply compelling sign of a biological and not a geological origin. Another powerful class of biosignatures is the detection of a chemical disequilibrium in the environment. Life is a process that is constantly fighting against the second law of thermodynamics. It is a process that creates and maintains a state of high chemical order and disequilibrium. The atmosphere of the Earth, with its strange and highly reactive mixture of oxygen and methane, is a planet-scale biosignature. In the same way, the detection of a similar and thermodynamically unlikely mixture of gases dissolved in the water of a European ocean or in the plumes of an Enceladus geyser would be a strong indication that some kind of active metabolic process is at work. We can also search for the isotopic fingerprints of life. As we have seen, life has a subtle but measurable preference for the lighter isotopes of certain elements, like carbon. The detection of a significant enrichment of carbon-12 in the organic molecules of an alien ocean would be another powerful piece of circumstantial evidence for a biological process. And finally, we can search for the morphological evidence of life, the fossilized, physical remnants of the organisms themselves. This is a much more challenging task, as it would likely require a lander mission that could collect a sample of the surface ice and examine it with a powerful microscope. But the discovery of a single, fossilized, alien microbe in a sample of ice from Europa or Enceladus would be a discovery of almost unimaginable significance, a definitive and deeply beautiful answer to one of the oldest and most profound of all human questions. The search for biosignatures is a complex, multifaceted, and deeply interdisciplinary endeavor. It is a search that requires us to use all of our scientific ingenuity, from the subtle chemical analysis of a mass spectrometer to the high-resolution imaging of a powerful microscope. And it is a search that is, at its heart, a search for a pattern, a signal in the noise, a faint, and perhaps a very strange whisper of life in the vast and beautiful silence of the cosmos. The discovery of the subsurface oceans of the icy moons has been a profound and deeply welcome revolution in our understanding of the habitable zone. It has forced us to abandon our old and far too simple sun-centric view of habitability and to embrace a much richer, more complex, and more astrobiologically optimistic vision of the cosmos. The traditional, classical habitable zone is a concept that is based on a single and seemingly simple idea: the presence of liquid water on a planet's surface. It is a relatively narrow circumstellar ring, a Goldilocks zone, where the distance from the host star is just right, not too hot, not too cold for a planet to have a surface temperature that allows for the stable existence of liquid water. This has been a powerful and very useful guiding principle in our search for potentially habitable, Earth-like planets around other stars. But the icy moons have shown us that this is a far too limited and far too terrestrial-centric view of where life might be able to find a home. A world can be far, far outside of the classical habitable zone, in the cold, dark, and seemingly desolate depths of the outer solar system, and still have a vast and potentially long-lived liquid water ocean. The key is the presence of a strong and reliable internal heat source, a source that can keep the ocean from freezing solid. And for the icy moons, this heat source is the powerful and ever-present phenomenon of tidal heating. This has led to a radical and deeply exciting expansion of our concept of the habitable zone. We now speak of a galactic habitable zone, a region of a galaxy where the conditions are most favorable for life. And we now understand that within any given planetary system, there may be multiple different kinds of habitable zones. There is the classical surface liquid water habitable zone, and there is a new, and perhaps even more common, subsurface liquid water habitable zone, a zone that is not defined by the distance from a star, but by the presence of a strong tidal heat source. This has dramatically expanded the potential real estate for life in our own solar system, and in the countless other planetary systems that are scattered throughout our galaxy. It suggests that rocky, Earth-like planets in the classical habitable zone may not be the only, or even the most common, abodes for life. The icy moons and the super-Earths with their own hidden oceans may be a much more common and much more stable environment for life to arise and to thrive in. The exploration of these new and expanded habitable zones is one of the great and most exciting frontiers of modern planetary science. It is a journey that is forcing us to think more creatively, more expansively, and more humbly about the nature of life, and about the full and wonderfully diverse range of cosmic environments that it might call home. The exploration of extraterrestrial life is not just a scientific and a technological challenge, it is also a profound and deeply complex ethical one. As we stand on the threshold of a new era of astrobiology, an era where the discovery of life beyond Earth seems more plausible than ever before, we are also being forced to confront a host of new and often difficult ethical questions about our own responsibilities as explorers, as scientists, and as a species. The first and most immediate of these is the principle of planetary protection. This is the ethical and practical imperative to avoid the forward contamination of other, potentially habitable, worlds with our own terrestrial microbes, and also to avoid the backward contamination of our own biosphere with any potential extraterrestrial life that we might bring back. The danger of forward contamination is a profound one. If we were to inadvertently introduce a hardy terrestrial microbe to the ocean of Europa, and if that microbe were to find a hospitable niche and to outcompete any nascent native life, we would have, in our carelessness, committed a form of cosmic ecological genocide. We would have destroyed the very thing we had set out to find. This is why our missions to potentially habitable worlds, like Mars and the icy moons, are subject to the most stringent and most expensive sterilization procedures. But the ethical challenges go far beyond just the issue of contamination. What are our responsibilities if we were to discover life, particularly intelligent life, on another world? This is a question that has long been the domain of science fiction, but it is one that we may, one day, have to face as a real and very practical ethical dilemma. Do we have the right to interfere? Do we have the right to colonize an inhabited world? The history of exploration on our own planet is a long and often tragic story of the devastating impact of a technologically advanced culture on a less advanced one. The lessons of this history should instill in us a deep and profound sense of caution and of humility as we begin to contemplate our future as a spacefaring species. The search for extraterrestrial life is also a profoundly human endeavor, and it raises a host of questions about our own societal values. The immense and often public investment that is required for space exploration means that we have a responsibility to be transparent, to be inclusive, and to engage in a broad and often difficult public dialogue about the goals, the risks, and the potential societal implications of our cosmic quest. The discovery of extraterrestrial life would be a discovery that belongs to all of humanity, and the decisions about how to respond to that discovery should not be made by a small group of scientists or politicians in a closed room. They should be the result of a global and deeply democratic conversation. The exploration of the cosmos is not just a journey into the out there, it is also a journey into the in here. It is a journey that forces us to confront our own deepest values, our own greatest hopes, and our own darkest fears. And it is a journey that will require us to be not just clever and not just courageous, but also, and most importantly, to be wise. The question of how to assess the likelihood of life existing in an environment that is completely devoid of sunlight is one of the central and most challenging in all of astrobiology. It requires us to move beyond our familiar photosynthesis-based intuition and to think like a chemoautotroph, a rock-eating microbe that makes its living from the subtle and often hidden chemical energies of its environment. The first, and most fundamental, requirement is the presence of a redox gradient. This is a chemical disequilibrium, a situation where there are both oxidized compounds, molecules that are hungry for electrons, and reduced compounds, molecules that have an excess of electrons. The flow of electrons from the reduced compounds to the oxidized ones is a process that releases energy, and it is this energy that a chemosynthetic organism can harness to power its metabolism. On Earth's deep-sea hydrothermal vents, the reduced compounds, like hydrogen sulfide and molecular hydrogen, are provided by the hot, mineral-rich fluid of the vent itself. The oxidized compounds, like oxygen and sulfate, are present in the cold, surrounding seawater. The vent is a natural chemical battery, and the microbes are the tiny living circuits that have evolved to tap into its power, to assess the habitability of a sunless subsurface ocean on an icy moon. Then is to assess the likelihood that a similar redox gradient exists. As we have seen, the evidence for the production of reduced compounds at the seafloor through the process of serpentinization is very strong, particularly at Enceladus. The bigger question is about the source of the oxidants. On Earth, the oxygen in our oceans is a product of photosynthesis at the surface. But on a world like Europa, the oxidants may have a different and more exotic origin: the intense radiation chemistry that is happening on its surface. The constant bombardment of the surface ice by high-energy particles from Jupiter's magnetosphere can create a host of powerful oxidant molecules. If these surface oxidants can be transported down into the ocean through the cracks and the convective churning of the ice shell, then the ocean would have both a fuel source from below and an oxygen source from above, creating a powerful and planet-scale redox gradient that could, in principle, support a large and a thriving biosphere. The second key factor is the availability of the essential biogenic elements, particularly carbon, nitrogen, and phosphorus. These can be leached from the rocky seafloor by the hydrothermal circulation, or they can be delivered to the ocean from the surface, from the constant influx of comets and carbon-rich asteroids. And finally, there are the physical conditions of the ocean itself: the temperature, the pressure, the salinity, the pH. All of these must be within a range that is conducive to the complex, and often delicate, chemistry of life. The remarkable discovery is that, at least for a world like Enceladus, all of these conditions seem to be met. It appears to have a liquid water ocean, a rich supply of organic molecules and other essential elements, a powerful chemical energy source in the form of hydrothermal vents, and a physical environment that is surprisingly benign. It is a world that seems to be, in almost every respect, a perfect and wonderfully promising cradle for life. The challenge now is to go there and to look. The future of our exploration of the icy moons is a future of incredible technological and scientific promise. It is a future where we will move from the remote and often indirect reconnaissance of the past to a more direct, more detailed, and more astrobiologically focused investigation of these strange, beautiful, and wonderfully promising worlds. The next decade will be dominated by the great orbital flagship missions NASA's Europa Clipper and the European Space Agency's JUICE. These are the missions that will give us our first, truly detailed and global perspective on these worlds. They will map their surfaces with unprecedented resolution. They will probe their internal structures with powerful, ice-penetrating radar. And they will analyze their tenuous atmospheres and their plasma environments with a suite of sophisticated, in-situ instruments. They are the missions that will confirm the existence of the subsurface oceans, that will measure their properties, and that will provide us with the crucial high-resolution maps that we will need to select the landing sites for the even more ambitious missions that will follow. The dream of a future lander mission to Europa is a dream that is now being actively developed in the laboratories of NASA and other space agencies. Such a mission would be one of the most challenging and most scientifically rewarding in the history of planetary exploration. It would have to autonomously navigate its way to a safe landing on the Moon's fractured and potentially treacherous icy surface. And once there, it would use its robotic arm and its suite of scientific instruments to perform the first direct analysis of the surface ice, searching for the preserved chemical and morphological biosignatures of any life that may have been brought up from the ocean below. And for Enceladus, the path to the ocean is even more direct. A future mission, like the proposed Enceladus Orbilander, could first orbit the Moon, flying repeatedly through its plumes to collect and to analyze a large and statistically significant sample of the ocean material. And then, once the most promising and safest landing site has been identified, it could descend to the surface to perform a detailed in situ analysis of the plume deposits that have rained back down onto the south polar terrain. But the ultimate dream, the holy grail of icy moon exploration, is to go one step further, to directly access and to explore the oceans themselves. This will require the development of a new and truly revolutionary class of robotic explorers, the cryobots and the hydrobots. This is a long-term and incredibly ambitious vision, but it is a vision that is now being actively researched and developed. The technologies of autonomous robotics, of artificial intelligence, of miniature instrumentation, of long-duration power systems, all of these are advancing at an incredible and exponential rate. The day when we will see the first ghostly and beautiful images from the dark, hidden, and potentially life-bearing oceans of another world may be closer than we think. It will be a day that will mark a new and perhaps the most profound chapter in the long and beautiful human story of exploration. The discovery of life in a subsurface ocean, if and when it happens, would be a moment of almost unimaginable scientific and cultural significance. It would be a discovery that would fundamentally and irrevocably change our view of the universe and of our own place within it. The first and most profound implication would be the realization that life is not a rare and perhaps unique terrestrial miracle, but is a more common and perhaps even a cosmic imperative. The discovery of a second genesis of life, a life that has an independent origin from our own, in our own solar system, would be a powerful and almost irrefutable argument that the universe is, in a very real sense, bio-friendly. It would suggest that the emergence of life is not a 1 in a trillion fluke, but is a natural and perhaps even an inevitable outcome of the laws of physics and chemistry, playing out on the countless watery worlds that are likely scattered throughout our galaxy. This would have a profound and deeply humbling impact on our human worldview. It would be the final and most definitive of all the Copernican decenterings, but it would also be a source of immense hope, of a deep and profoundly beautiful sense of connection to the cosmos. We would no longer be a lonely cosmic anomaly, but would be a part of a much larger and much more diverse galactic community of life. The scientific implications would be equally profound. The ability to study a truly alien biology, a life that is based on a different and perhaps a radically different biochemistry and genetics, would be a revolution in the life sciences. It would allow us to begin to distinguish the universal and perhaps necessary features of life from the contingent and purely historical accidents of our own terrestrial evolution. It would be the birth of a truly universal biology, a science that is no longer just about the study of life on Earth, but is about the study of life in all its potential forms as a fundamental phenomenon of the cosmos. The discovery would also have a profound impact on the future of our own human exploration of space. It would provide a powerful and deeply compelling new impetus for the development of the technologies that will be needed to explore these distant, and now even more fascinating, worlds. And it would raise a host of new and deeply challenging ethical questions. What are our responsibilities to this new alien life? How do we explore and study these fragile and perhaps unique ecosystems without harming or contaminating them? These are questions that will require a new and more mature kind of cosmic wisdom, a wisdom that is based on a deep sense of respect for the diversity and the preciousness of all life, wherever it may be found. The discovery of life in a subsurface ocean would be more than just a scientific discovery. It would be a moment of profound and deeply human transformation. It would be a moment when we, as a species, would be forced to look up at the night sky and at ourselves with new and wonderfully widened eyes. The challenge of distinguishing a true biological signal from a purely abiotic chemical one is one of the greatest and most subtle in all of astrobiology. The universe is a complex and often surprising chemical laboratory, and it is capable of producing a rich and sometimes a very lifelike array of organic molecules and chemical disequilibria without the need for any biological intervention. The search for biosignatures, therefore, must be a careful, a cautious, and a deeply interdisciplinary endeavor. It is not a search for a single, smoking gun piece of evidence, but is a process of building a cumulative and statistically robust case from multiple, independent lines of evidence. The detection of a single, organic molecule, for example, is not in itself a definitive sign of life, but the detection of a specific and statistically unlikely distribution of organic molecules can be a much more powerful biosignature. Life, as we know it, is very selective. It uses only a small subset of all the possible chemical building blocks. The detection of a similar and highly selective homochirality or isotopic fractionation in an alien sample would be a strong and deeply compelling piece of evidence for a biological origin. The detection of a chemical disequilibrium is another powerful tool. But here, too, we must be cautious. The plumes of Enceladus, for example, contain a mixture of hydrogen, methane, and carbon dioxide. A mixture that is out of chemical equilibrium and that could, in principle, be a source of energy for a methanogenic biosphere. But it is also possible that this disequilibrium is being maintained by purely geological and abiotic processes, like the ongoing serpentinization at the seafloor. To distinguish between these two possibilities, we need to have a much more detailed, quantitative model of the geology and the chemistry of the Moon's interior, a model that can tell us what the background, abiotic state should be. A true biological signal would be a deviation from this abiotic baseline. This is why the search for life is not just a biological quest. It is also a deeply geological and a chemical one. We cannot hope to find the signature of an alien biosphere until we have a deep and detailed understanding of the alien world that it inhabits. And finally, we must always be prepared for the possibility of a life that is truly and profoundly alien. A life that does not use the same biochemistry, the same genetics, or the same metabolic pathways as our own. The search for this kind of agnostic biosignature is one of the great and most exciting frontiers of modern astrobiology. It is a search that is not looking for the specific and perhaps parochial signs of our own terrestrial life. It is a search for the more general and perhaps more universal signatures of complexity, of information, and of a system that is actively and purposefully fighting against the relentless and ever-present tide of the second law of thermodynamics. It is a search for life, not just as we know it, but as we can, and perhaps must, dare to imagine it. The recent discoveries from the icy moons of our outer solar system have not just provided us with new and exciting targets in our search for life. They have also given us a wealth of new and often surprising data that is allowing us to build a much more detailed and much more nuanced picture of the composition and the chemistry of their hidden subsurface oceans. The analysis of the plumes of Enceladus by the Cassini spacecraft has been a particular goldmine of information. We now know that this ocean is salty, with a salinity that is very similar to that of Earth's own oceans. We know that it is rich in a variety of dissolved gases, including carbon dioxide, methane, and molecular hydrogen. We know that it contains a diverse and surprisingly complex suite of organic molecules, from simple hydrocarbons to more complex nitrogen-bearing compounds. And we know that it is in direct and active contact with a rocky silicate core that is powering a network of high-temperature hydrothermal vents. This is a chemical picture that is almost shockingly and beautifully Earth-like. It is a picture of an environment that seems to have all the necessary and well-mixed ingredients for a thriving chemosynthetic biosphere. The picture at Europa is more indirect and more uncertain, but it is no less tantalizing. The spectroscopic analysis of its surface ice has revealed the presence of a variety of salts, particularly magnesium sulfate, and a number of simple organic compounds. These are thought to be the frozen remnants of the ocean water that has been brought to the surface, and they provide a strong, albeit circumstantial, piece of evidence that Europa's ocean is also a salty and organic-bearing environment. And the detection of a thin and transient oxygen atmosphere around Europa, which is thought to be created by the radiation-driven breakdown of the surface water ice, raises the exciting possibility that this powerful and life-sustaining oxidant could be making its way down into the ocean below. The picture at the other, more distant, icy moons is still more speculative, but the discovery of an induced magnetic field at Ganymede strongly suggests that its ocean, too, is a salty and conductive one, and the incredible and almost overwhelming organic richness of the surface and the atmosphere of Titan, combined with the strong evidence for a deep, subsurface water ocean, makes it a world of almost unimaginable astrobiological complexity and potential. The story that is emerging from these new discoveries is a story of a solar system that is far more wet, far more chemically complex, and far more potentially habitable than we ever dared to imagine. It is a story that is transforming the icy moons from cold, dead, and forgotten outposts into some of the most exciting and most scientifically compelling destinations in our entire solar system. And it is a story that is just beginning to be told. The upcoming missions to these worlds, with their powerful, new, and sophisticated instruments, will undoubtedly provide us with even more surprises and will bring us ever closer to answering the deep and beautiful question of whether the spark of life has been ignited in the dark, hidden, and wonderfully promising waters of these distant and alien worlds. The plumes of Enceladus are more than just a beautiful and scientifically fascinating phenomenon. They are a direct and almost miraculous window into a hidden and potentially life-bearing world. The discovery of these dramatic, geyser-like eruptions by the Cassini spacecraft was one of the most unexpected and most profound discoveries in the history of planetary exploration, and they have transformed our understanding of this tiny, icy moon. These plumes are not small, isolated events. They are a series of long, linear, and continuously active curtains of water vapor and ice particles, erupting from a set of parallel fissures. The tiger stripes in the moon's south polar region. They are spewing material out into space at a rate of about 200 kilograms per second, and they are the source of Saturn's faint and beautiful E-ring. The very existence of these plumes is a powerful and definitive piece of evidence for the existence of a large and geologically active subsurface ocean of liquid water. The heat that is required to power these geysers and to keep the ocean from freezing is thought to come from the powerful tidal forces that are exerted on the Moon as it orbits Saturn, and the analysis of the plume's composition, as we have seen, has provided us with a direct and tantalizing taste of the chemistry of this hidden ocean. But the plumes are not just a window into the ocean, they are also a window into the Moon's deep and geologically active interior. The detection of tiny silica nanoparticles in the plumes is a particularly exciting and significant clue. On Earth, these kinds of silica nanoparticles are only known to form in one specific environment, the hot, mineral-rich, and high-pressure water of a deep-sea hydrothermal vent. The discovery of these particles in the plumes of Enceladus is a smoking gun, a direct and powerful piece of evidence for the existence of active, high-temperature hydrothermal vents on the seafloor of its subsurface ocean. This is a discovery of almost unimaginable astrobiological significance. It means that Enceladus has not just one, but two of the essential requirements for life as we know it, a liquid water ocean, and a powerful and long-lived source of chemical energy. The plumes of Enceladus are a gift from the cosmos. They are a natural and beautiful sample return mission, a way for us to directly probe the chemistry and the potential biology of a hidden alien ocean without ever having to face the immense and perhaps insurmountable technological challenge of drilling down through kilometers of solid cryogenic ice. A future mission to Enceladus, one that is specifically designed to fly through these plumes with a suite of sophisticated and life-detecting instruments, is now one of the highest and most exciting priorities in all of planetary science. It is a mission that could, in our own lifetimes, provide us with a definitive and deeply profound answer to one of the oldest and most beautiful of all human questions. The evolutionary pathways that life might take in the isolated and profoundly alien ecosystems of the subsurface oceans would be a story that is both strangely familiar and deeply and beautifully strange. It would be a story that is governed by the same universal principles of Darwinian evolution that have shaped the history of life on our own planet, the principles of variation, of inheritance, and of natural selection. But it would be a story that is playing out on a different and completely independent biological stage, a stage with a different set of actors, a different set of environmental pressures, and a different, and perhaps a radically different, biochemical and genetic script. The isolation of these oceans is a key and deeply significant factor. Each of these oceans would be a separate and completely independent Genesis experiment. The life that might arise on Europa would have a completely different and completely unrelated origin from the life that might arise on Enceladus. This would be a profound and deeply exciting opportunity for a new kind of comparative biology. By studying these two independent examples of life, we could begin to disentangle the universal and perhaps necessary features of life from the contingent and purely historical accidents of our own terrestrial evolution. But the isolation would also have a profound and perhaps a limiting impact on the evolutionary pathways themselves. The life in these oceans would be evolving in a world of relative environmental stability. They would not be subject to the same dramatic and often catastrophic environmental changes that have been a major driver of evolutionary innovation on the surface of the Earth. Changes like asteroid impacts, or ice ages, or the dramatic rise of oxygen in our own atmosphere. The evolution in these oceans might be a much slower, more patient, and more conservative process. A process that is focused on the fine-tuning of a metabolism that is adapted to the specific and relatively unchanging chemical conditions of its own. Local hydrothermal vent. But even in this stable environment, the principles of natural selection would still be at work. There would still be a competition for resources, a constant evolutionary arms race between predators and prey, a co-evolutionary dance between symbiotic partners, and over the billions of years that these oceans have likely existed. It is not impossible to imagine that this slow, patient, and relentless process of evolution could have given rise to a rich and surprisingly complex biosphere. It would be a biosphere that is built on a foundation of chemosynthetic microbes, but one that could have, over time, evolved its own strange and beautiful forms of multicellular life, its own alien equivalent of the worms, the crabs, and the fish that populate our own deep oceans. The exploration of the evolutionary pathways of the life in the subsurface oceans is a journey into a new and completely unknown biological frontier. It is a journey that will require us to be not just clever and not just creative, but also, and most importantly, to be deeply and profoundly humble in the face of the incredible and perhaps the universal creative power of the evolutionary process. The climate models that we use to understand the icy moons are a beautiful and powerful example of the interplay between theory, observation, and computation in modern planetary science. These are not the same as the climate models we use to study the Earth's atmosphere. They are a different, and in many ways, a more complex kind of model. A model that must account for the intricate and often poorly understood physics of ice, of oceans, and of the powerful tidal forces that are at play in these distant and alien worlds. At the heart of these models is a detailed and mathematically sophisticated description of the physical properties of the ice shell itself. The model must account for how the ice deforms and flows under the immense tidal stress, how it conducts heat from the ocean below to the surface above, and how its thickness might vary from place to place. The models also include a description of the ocean itself, its depth, its salinity, its temperature, and the vigorous convective circulation that is likely being driven by the heat from the moon's interior. And finally, the models must include a detailed and accurate description of the tidal heating process, the ultimate engine that is powering the entire dynamic system. These models are not just a static, theoretical construct. They are constantly being tested, refined, and constrained by the observational data from our space missions, the high-resolution images of the surface geology, the precise measurements of the gravity field, the thermal maps of the surface temperature, the data from the induced magnetic field. All of these are fed into the models, helping us to narrow down the range of possibilities and to build a more accurate and more realistic picture of these hidden, watery worlds. These models are not just used to understand the present-day state of these moons. They are also used to explore their past and their future. Evolution. By running the models backwards in time, we can explore how the oceans and the ice shells might have formed and evolved over the history of the solar system. And by running them forwards, we can make predictions about the long-term stability of these oceans and about their ultimate fate. The climate models of the icy moons are a powerful and an essential tool in our search for life. They are what allow us to move beyond a simple and purely qualitative assessment of habitability and to build a more detailed, more quantitative, and more physically grounded understanding of these potential extraterrestrial habitats. They are what allow us to identify the most promising and most scientifically interesting places to look for the signs of life. And they are a beautiful example of how we can use the power of mathematics, of physics, and of computation to explore a world that is hidden from our direct view, a world that is buried beneath kilometers of solid ice, a world that may, one day, provide us with a profound and deeply beautiful. Answer to one of the oldest and most enduring of all human questions. The exploration of the moons of our solar system is a grand and increasingly a global endeavor. It is a quest that is no longer being undertaken by a single nation, but is a rich and wonderfully collaborative tapestry of missions, of instruments, and of scientific expertise from around the world. This spirit of international collaboration is not just a matter of political goodwill, it is a scientific and a practical necessity. The challenges of exploring these distant and often hostile worlds are so great, and the costs are so immense, that it is often only through the pooling of resources, of technology, and of intellectual capital that we can hope to succeed. The Cassini-Huygens mission to Saturn was a beautiful and incredibly successful example of this collaborative spirit. It was a joint mission between NASA, the European Space Agency, and the Italian Space Agency. NASA provided the main orbiting spacecraft. Cassini, ESA provided the Huygens probe, which made the historic and incredibly successful descent and landing on the surface of Titan. And ASI provided the high-gain antenna that was the crucial communication link between the spacecraft and the Earth. The scientific return from this mission was immense, and it was a direct result of this deep and truly international partnership. The upcoming missions to the icy moons of Jupiter are another powerful example of this collaborative model. NASA's Europa Clipper and ESA's JUICE are two separate and largely independent missions, but they have been designed to be highly complementary. They will be in the Jovian system at the same time, and they will be observing the same fascinating set of worlds, but with different instruments and with different scientific priorities. The data from these two missions, when combined, will give us a much richer, much more comprehensive, and much more powerful picture of the Jovian system than either mission could have provided on its own. This collaboration extends beyond the space agencies themselves to the global scientific community. The data from these missions is, for the most part, made publicly available, allowing scientists from all over the world to participate in the process of discovery. This open data policy is a powerful catalyst for innovation, and it ensures that the best minds, regardless of their nationality or their institutional affiliation, are able to contribute to the grand and shared human endeavor of understanding our cosmic home. The exploration of space at its best is a project that can unite us, that can transcend our terrestrial, political, and cultural divisions, and that can remind us of our shared and deeply human curiosity and our shared and profoundly beautiful cosmic destiny. It is a testament to what we can achieve when we choose to work together, not as competing nations, but as a single, global, and spacefaring species. Beneath the surface of our planet, something strange is hiding. It's older than any book, older than anything we've ever written down. Deep in the ground, the Earth keeps secrets we're only starting to uncover. Imagine ancient cities long turned to dust, forests growing over places no one remembers, and rocks holding quiet clues from a forgotten time. Some scientists have found fossils that don't fit the timeline, tools with no clear purpose, and rock layers that hint at events we can't explain. And now there's a new idea, the Silurian hypothesis. It asks a wild question. What if there was a civilization here millions of years before humans? Could it be possible And if it was, what would still be left to find? For as long as humans have gazed at the stars, we have pondered our place in the universe. Are we alone? Is there other intelligent life out there? But a different, equally profound question often goes unasked. Are we alone here on our own planet, in the long sweep of its history? This is the core of the big question. Could another advanced civilization have existed on Earth long before humans ever walked the planet? It is a thought that challenges our conventional understanding of history and our unique position in the story of life. Our current understanding of Earth's story places human civilization as we recognize it today as a very recent development. The first settled agricultural communities appeared perhaps 10,000 to 12,000 years ago. The development of large cities, complex societies, and industrial technology are even more recent. This entire span of human recorded history is a mere flicker when compared to the immense age of Earth itself, which scientists estimate to be approximately 4.54 billion years old. This vast, almost unimaginable timescale leaves immense stretches of time, hundreds of millions of years, during which conditions on Earth might have been suitable for the emergence of advanced life forms and even complex societies long before our species, Homo sapiens, evolved. The idea of a pre-human civilization immediately raises many sub-questions. What would advanced civilization even mean in this context? We tend to define it by our own technological progress, buildings, tools, complex communication, and significant alteration of the environment. Would such a civilization necessarily be carbon-based? Would it have walked on two legs or resembled us in any way? The possibilities are boundless. Perhaps they were an aquatic civilization, or insect-like, or even silicon-based. The crucial aspect for our investigation, however, is whether they reached a level of advancement that would leave behind some form of detectable techno signature, a sign of technology or industrial activity that could endure across geological time. The challenge of finding evidence for such a civilization is immense. Earth is a dynamic planet, constantly recycling its surface through processes like erosion, plate tectonics, and volcanism. Mountains rise and fall, continents drift, and ocean floors are subducted back into the mantle. Any physical structures, no matter how grand, would likely be ground into dust or swallowed by the Earth over tens of millions, let alone hundreds of millions, of years. Imagine trying to find traces of ancient Roman cities if they were 100 million years old, not just 2,000. The task becomes almost impossible for direct artifacts. This leads us to consider what indirect signs might remain. What if an ancient civilization had an industrial revolution similar to our own? Our current industrial activities are leaving clear techno-signatures, increased carbon dioxide in the atmosphere, plastics in ocean sediments, specific pollutants, and altered geological layers. Could such signatures, if produced by a civilization millions of years ago, still be detectable in Earth's geological record today? This line of questioning forms the basis of what is known as the Silurian hypothesis. It is not an assertion that such a civilization definitely existed, but rather a scientific thought experiment. It encourages us to look at existing geological, paleontological, and chemical data with a fresh perspective, instead of dismissing unusual finds or anomalies as natural phenomena. It prompts us to consider if there might be subtle, long-lasting indicators of non-natural processes from deep time. For instance, an unusually high concentration of certain elements in a very old sediment layer, or a sudden spike in atmospheric gases that doesn't align with known natural cycles. The very fact that we haven't found definitive evidence of a prior advanced civilization is often seen as proof that none existed. However, the absence of evidence is not always evidence of absence, especially when dealing with timescales that dwarf human comprehension. The Earth's geological record is incredibly incomplete, and much of it remains unexplored. We have sampled only a tiny fraction of the Earth's crust and ocean floor. Furthermore, Our methods for detecting extremely ancient, subtle technosignatures are still in their infancy. We're only just beginning to understand what long-term signatures our own civilization might leave, let alone what an alien civilization on our own planet might have left behind. The big question forces us to confront our anthropocentric view of Earth's history. We often assume that humanity is the first, and perhaps only the species, to achieve advanced intelligence and widespread technological capability on this planet. But considering the 4.54 billion years of Earth's existence, with countless cycles of life, extinction, and environmental change, it seems almost statistically improbable that no other intelligent species could have arisen and developed some form of civilization, even if it lasted for only a geologically brief period, perhaps a few 100,000 years, before its demise. This thought experiment also has implications for our search for extraterrestrial intelligence. If it is so difficult to find evidence of a past civilization on our own planet, how much harder must it be to find one on a planet light years away? The challenges we face in detecting Earth's hypothetical ancient inhabitants are magnified when searching the vastness of space. Understanding the limitations of our search on Earth can inform and refine our strategies for looking beyond our solar system. Ultimately, the big question is about expanding our scientific imagination. It challenges us to look beyond immediate assumptions and consider the profound possibilities hidden within the deep history of our own world. It is about acknowledging the vastness of time and the dynamism of our planet, and how these factors conspire to hide the secrets of the distant past, whether such a civilization existed or not. The act of asking the question and devising ways to scientifically investigate it pushes the boundaries of our knowledge and encourages us to look at the familiar world around us with new, more curious eyes. It sets the stage for a deeper exploration into the nature of evidence, the processes of planetary change, and the very definition of civilization in a cosmic and geological context. The Silurian hypothesis is a scientific thought experiment that asks a profound question. What if an advanced industrial civilization existed on Earth millions of years before humans? And what evidence of its existence, if any, could we possibly find today? It is not a claim that such a civilization definitely existed, but rather a framework for examining the long-term geological and atmospheric records for subtle signs that might indicate a non-natural, ancient event. The hypothesis was formally proposed in a 2018 paper by Adam Frank, an astrophysicist at the University of Rochester, and Gavin Schmidt, a climate scientist and director of the National Aeronautics and Space Administration Goddard Institute for Space Studies. The intriguing name, Silurian hypothesis, actually comes from popular culture, specifically the classic British science fiction television series Doctor Who. In a 1970s episode, the Doctor encountered a race of intelligent reptilian humanoids called the Silurians. These beings, the story goes, were the dominant intelligent species on Earth millions of years ago, who went into hibernation to escape an impending natural catastrophe, only to awaken in the human era. While the fictional origin provides a catchy name, the scientific paper uses the concept as a springboard for a serious discussion about the potential for undetectable, pre-human technological civilizations on Earth. The name Silurian itself refers to a geological period from about 444 million to 419 million years ago, a time far too ancient for the kind of complex life forms we're discussing. The hypothesis, however, is not restricted to that specific period, but rather encompasses any potential pre-human epoch. The core of the Silurian hypothesis revolves around the idea of technosignatures. When we search for extraterrestrial intelligence, we look for technosignatures, signs of technology on other planets. Frank and Schmidt turned this concept inward, asking what our own industrial civilization's technosignatures would look like in the geological record, millions of years from now. By understanding what traces we are leaving behind, we can better hypothesize what a past civilization on Earth might have left. The key is industrial, because it implies large-scale energy use and material processing, which would inevitably leave detectable marks on the planet. The paper identifies several types of potential technosignatures that an ancient industrial civilization might have produced, and which could theoretically survive for tens or hundreds of millions of years. First, atmospheric composition changes. Our current industrial civilization has dramatically increased carbon dioxide levels in the atmosphere, leading to global warming. An ancient industrial civilization would likely have done the same. While the atmosphere itself recycles, chemical signatures of past atmospheric conditions can be preserved in ice cores and sediment layers. For example, a sudden spike in carbon isotopes or nitrogen oxides that cannot be explained by natural volcanic activity or other geological processes might indicate ancient industrial emissions. Second, sedimentary anomalies. An industrial society uses and produces many synthetic materials and waste products, while direct physical objects like buildings or tools would almost certainly be destroyed by geological processes over millions of years. The chemical components of these materials might persist. This could include stable isotopes of elements, rare metals, or even long-lived synthetic compounds embedded in sediment layers. Even microplastics, a hallmark of our own era, could theoretically leave a subtle chemical trace millions of years later, though this is highly speculative given their degradation rates. Third, long-lived radioactive isotopes and waste. If an ancient civilization developed nuclear power or weapons, they would have produced radioactive waste. While many radioactive isotopes decay relatively quickly, some, like plutonium-244, have extremely long half-lives and could still be detectable today, albeit in minute quantities. The presence of such isotopes in ancient geological strata, particularly in a context that cannot be explained by natural geological or astronomical events, would be a strong, though difficult to verify, indicator. Fourth, geological alterations. Large-scale mining, drilling, or terraforming efforts by an advanced civilization could leave scars on the Earth's crust. While erosion would eventually smooth over surface features, the underlying geological disturbances, such as tunnels or deep mine shafts, might leave persistent structural anomalies or mineralogical changes detectable through advanced geological surveys. However, these are the least likely to survive intact over immense timescales. The purpose of the Silurian hypothesis is not to provide immediate answers or to claim that ancient aliens walked the Earth. Instead, it serves as a crucial lens through which to re-examine existing scientific data. Scientists regularly analyze ice cores that contain atmospheric data going back hundreds of thousands of years, and geological sediment cores that stretch back hundreds of millions of years. These records are typically interpreted through known natural processes like volcanism, asteroid impacts, and biological cycles. The hypothesis urges scientists to consider if any anomalies in these records, which currently lack a conventional explanation, could potentially point to an industrial event of non-natural origin. A key point highlighted by Frank and Schmidt is the concept of a bottleneck in the geological record. If a civilization lasted for only, say, 100,000 years, that is still a mere blip in the 4.54 billion years of Earth's history. The chances of that brief period coinciding with a geological layer that is well preserved, accessible, and thoroughly studied are exceedingly small. Furthermore, such a civilization might not have existed during a period conducive to fossilization or preservation of technosignatures. The Earth's dynamic nature means that vast amounts of its past surface have been destroyed or recycled. To truly grasp the implications of a pre-human civilization, one must first comprehend the immense, almost unfathomable, scale of Earth's history. Our planet is approximately 4.54 billion years old. This number, 4 billion, 540 million years is so vast that it dwarfs any human experience or historical record. To put it into perspective, the entire span of human civilization, from the first settled villages to the digital age, covers a mere 12,000 years, a fraction of a percent of Earth's total existence. This colossal span of time, known as deep time, is the canvas upon which Earth's long story unfolds, a story filled with dramatic changes, the rise and fall of countless life forms, and repeated transformations of the planet itself. Scientists divide Earth's history into vast time segments, much like chapters in an epic book, to help organize and understand its evolution. These primary divisions are called eons. The first eon is the Hadean eon, stretching from Earth's formation about 4.54 billion years ago to roughly 4 billion years ago. During this fiery period, Earth was a molten, inhospitable place, constantly bombarded by asteroids and comets. As it gradually cooled, the first oceans began to form from condensing water vapor. Life as we know it would have been impossible during most of this eon. Next came the Archean eon, from 4 billion to 2.5 billion years ago. This eon saw the stabilization of Earth's crust, the formation of continents, and, crucially, the emergence of the very first life forms. These were simple, single-celled organisms, mostly bacteria and archaea, living in the oceans. Evidence of their existence comes from ancient stromatolites, layered structures built by microbial mats. The atmosphere during this time was very different from today's, lacking significant free oxygen. The Proterozoic eon followed, spanning a massive period from 2.5 billion to 541 million years ago. This was an eon of immense change. Photosynthesis, carried out by cyanobacteria, began to release large amounts of oxygen into the atmosphere, leading to the Great Oxidation Event. This event was actually a major environmental catastrophe for much of the anaerobic life existing at the time, but it paved the way for more complex life. Towards the end of the Proterozoic, the first multicelled organisms appeared, and large, complex organisms like the Ediacaran biota emerged, though they were very different from modern animals, even over this 2 billion-year span. Conditions for a technological civilization were likely not present. Finally, we arrive at the Phanerozoic eon, which began 541 million years ago and continues to the present day. This is the eon of visible life, characterized by the rapid diversification of complex multicellular organisms with hard parts, leading to an abundant fossil record. This eon is further divided into 3 eras. The Paleozoic era began with the Cambrian explosion, an astonishing burst of evolutionary innovation, where most major animal groups appeared in a relatively short geological time. This era saw the evolution of fish, the colonization of land by plants and then animals, and the appearance of amphibians and early reptiles. It ended with the Permian-Triassic extinction event, the largest mass extinction in Earth's history, wiping out over 90% of marine species and 70% of terrestrial vertebrate species. The Mesozoic era is famously known as the Age of Dinosaurs. This era includes the Triassic, Jurassic, and Cretaceous periods. Mammals also evolved during this time, though they remained small and overshadowed by the dominant reptiles. It concluded with the Cretaceous-Paleogene extinction event, caused by a large asteroid impact, which led to the demise of the non-avian dinosaurs and opened up ecological niches for mammals. This era, particularly the late Cretaceous, is often cited as a hypothetical window for the kind of ancient civilization considered by the Silurian hypothesis, as it represents a period of diverse, complex life before the rise of mammals to dominance. The Cenozoic era is the age of mammals. Following the KPG extinction, mammals diversified and grew in size, filling the ecological roles left vacant by the dinosaurs. This era has seen the evolution of primates, the development of grasslands, ice ages, and ultimately, the emergence of our own species. Homo sapiens appeared only about 300,000 years ago, and our earliest ancestors of the genus Homo date back about 2.8 million years. The Industrial Age, which began a mere few hundred years ago, is an almost immeasurable point at the very end of this vast timeline. The profound implication of Earth's long story is the sheer amount of time available for anything to happen. If a civilization existed for even a few 100,000 years, that period would still be a tiny blip on the 4.54 billion year geological clock. The Earth's dynamic nature means that direct evidence of such a civilization would be incredibly difficult to find. Geological processes continuously recycle the planet's surface. Ocean crust is constantly created at mid-ocean ridges and then subducted back into the mantle, meaning no ocean floor today is older than about 200 million years. Continents are eroded by wind and water, and their sediments are deposited elsewhere or carried to the sea. Rocks are subjected to heat and pressure, transforming them. What was once on the surface might be buried miles deep or melted and reformed. This relentless geological activity acts as a grand eraser, obliterating most traces of past events, especially those that are not robust biological fossils or widespread geological formations. Understanding Earth's long story is crucial because it provides the context for the Silurian hypothesis. It shows that there has been ample time, many hundreds of millions of years, for multiple cycles of complex life to emerge, evolve, and potentially reach advanced stages. While we have no definitive proof of a pre-human civilization, the vastness of deep time ensures that the possibility, however remote, cannot be entirely dismissed without thorough investigation of the geological record. It prompts us to consider that our brief moment of technological prominence might not be unique in the incredibly long and eventful history of our own planet. To truly grasp the concept of whether another civilization could have existed on Earth before us, it is essential to understand the immense span of time that the planet has experienced. Human civilization, in its current recognized form, is but a fleeting moment when viewed against the backdrop of Earth's 4.54 billion-year history. Imagine a single calendar year representing Earth's entire existence. On this scale, human civilization would barely occupy the last few seconds of December 31st. This profound disproportion highlights just how recent our appearance is and provides an enormous window for other potential. Ancient developments. Our planet coalesced from dust and gas around 4.54 billion years ago. For the first many hundreds of millions of years, Earth was a violent, hot world, bombarded by asteroids and lacking a stable surface or atmosphere capable of sustaining life as we know it. The conditions were hostile, with widespread volcanism and a primordial atmosphere very different from today's. It was not until around 3.8 billion years ago that the first definitive evidence of life emerged in the form of simple, single-celled organisms. These early life forms, such as bacteria and archaea, began the slow process of transforming Earth's atmosphere, notably by introducing oxygen, a process that unfolded over billions of years. For an astonishingly long period, life remained microscopic. The journey from simple single cells to complex multicellular organisms was gradual and punctuated by significant evolutionary leaps. The Cambrian explosion, which occurred approximately 541 million years ago, marks a pivotal moment. Before this period, life was predominantly soft-bodied and simple. During the Cambrian explosion, there was a rapid diversification of life forms, leading to the appearance of most major animal groups we recognize today, characterized by hard body parts like shells and skeletons. This event signifies the dawn of complex, visible life that could leave a more substantial fossil record. Following the Cambrian period, Earth saw a parade of diverse life forms, adapting and evolving over vast spans. fish, amphibians, and reptiles came and went, dominating various ecosystems. The age of dinosaurs, known as the Mesozoic era, lasted for about 184 million years, from 252 million years ago until 66 million years ago. During this immense stretch of time, enormous creatures roamed the land, and diverse life thrived in the oceans and skies. The sheer duration of the dinosaur era alone exceeds the entire span of time since their extinction to the present day. This era ended dramatically with the Cretaceous-Paleogene extinction event, caused by a massive asteroid impact 66 million years ago, which wiped out 3/4 of all plant and animal species, including most of the dinosaurs. The extinction of the dinosaurs paved the way for the rise of mammals. Over the next 66 million years, mammals diversified and evolved to fill the ecological niches left vacant. This Cenozoic era, often called the Age of Mammals, saw the evolution of various mammalian forms, eventually leading to the emergence of primates. Our own lineage, the hominids, began to diverge from other primates several million years ago. The first members of the genus Homo, our direct ancestors, appeared around 2.8 million years ago in Africa. These early hominids gradually developed tool-making abilities and increasingly complex social structures. The species Homo sapiens, modern humans, only appeared relatively recently, originating in Africa approximately 300,000 years ago. For hundreds of thousands of years, our ancestors lived as hunter-gatherers, spreading across continents. The profound shift that truly marks the beginning of what we call civilization occurred with the agricultural revolution, which began around 10,000 to 12,000 years ago. Before this, humans lived nomadic lives. Agriculture allowed for sedentary settlements, population growth, and the development of surplus food, which in turn led to specialization of labor, the emergence of villages, and eventually, the first urban centers. The first cities, like those in Mesopotamia, appeared around 5,500 years ago. This period saw the invention of writing, complex political systems, and monumental architecture. From this point, human civilization began its accelerating trajectory. The invention of the wheel, metallurgy, and organized religion all contributed to increasingly sophisticated societies. The development of empires, trade networks, and sophisticated legal codes marked further advancement over thousands of years. The pace of change accelerated dramatically with the Industrial Revolution. Beginning in the late 18th century, this period saw fundamental transformations in manufacturing, energy production, and transportation, leading to unprecedented economic growth, urbanization, and technological progress. The last 2 centuries, in particular, have witnessed an explosion of scientific knowledge and technological capability, culminating in the information age and the global interconnectedness we experience today. When we consider these timelines, the recency of human civilization becomes starkly clear. From the first single-celled life to the first complex animals, billions of years passed. From the extinction of the dinosaurs to the first humans, tens of millions of years elapsed. From the first humans to the first cities, hundreds of thousands of years went by. And from the first cities to our current global, industrialized, digital civilization, only about 5,500 years have passed. This mere blink of an eye in Earth's history means that the vast majority of geological time, billions of years, occurred before anything remotely resembling human civilization existed. This immense, empty canvas of time is precisely what fuels the question of whether another intelligent, technological civilization could have risen and fallen, leaving little to no detectable trace, long before our species even came into being. Every form of life, from the simplest bacterium to the most complex civilization, leaves behind evidence of its existence. These marks are imprints on the environment, ranging from subtle chemical alterations to grand physical structures. Understanding these various ways life leaves its signature is crucial when considering the possibility of a past civilization on Earth, as it helps us identify what sorts of traces might persist over geological time scales at the most basic biological level. Life leaves marks through its physical remains, or fossils. When an organism dies, its hard parts like bones, teeth, shells, or wood can be preserved under specific conditions, turning into rock over millions of years. Even soft tissues can sometimes leave impressions or chemical residues. These are the direct biological marks of individual organisms, and by extension, the species that made them. For a civilization, the most straightforward marks would be the fossilized remains of its inhabitants, or perhaps their domesticated animals and cultivated plants, preserved in ancient sediments. Beyond individual organisms, a civilization, by its very nature, significantly alters its environment on a larger scale. One of the most obvious ways is through the creation of physical structures. Buildings, roads, bridges, dams, and cities are monumental constructions that rearrange Earth's surface. Ancient human civilizations left behind pyramids, Roman roads, and vast irrigation systems. These structures are made of durable materials like stone, concrete, or fired brick. If a civilization existed millions of years ago, its large-scale architecture, quarries, or engineered landscapes might, hypothetically, be preserved as distinct geological anomalies or rearranged rock formations. The scale of these modifications, such as the construction of major infrastructure or large-scale terraforming efforts, would leave patterns in the geology that are distinct from natural processes. Waste products are another undeniable mark of civilization. Modern human society generates enormous quantities of waste, much of which is highly durable. Plastics, for instance, are synthetic polymers that degrade very slowly, taking hundreds to thousands of years to break down. Even then, they might persist as microplastics in sediments for much longer. Industrial byproducts, such as slag from metal smelting, ash from burning fossil fuels, or chemically altered soils from industrial processes, represent persistent chemical and material residues. If a past civilization had similar industrial activities, its waste dumps, landfills, or dispersed industrial detritus might form distinct stratigraphic layers in the geological record, containing materials or chemical signatures that do not occur naturally. Furthermore, the very act of extracting resources leaves indelible marks. Mining operations, whether for metals, coal, or other raw materials, create vast pits, tunnels, and spoil heaps. These large-scale disturbances alter the geology and can be detectable as anomalous concentrations of certain minerals or rearranged subsurface structures. The processing of these resources, such as the refining of metals, can leave behind unique elemental ratios or isotopic signatures in the surrounding environment, distinct from natural background levels. For example, the widespread use of fossil fuels by a past civilization would alter the carbon isotope ratios in the atmosphere and oceans, which could potentially be recorded in sedimentary rocks or ice cores formed during that period. A civilization's impact extends to the global environment, particularly its atmosphere and oceans. The burning of fossil fuels or large-scale industrial processes release gases like carbon dioxide, methane, and other pollutants into the atmosphere. Over long periods, significant emissions could alter the planet's climate, leading to warming or cooling trends that leave discernible signatures in geological archives like ice cores, ocean sediments, or ancient soil layers. A past civilization might also have released specific industrial chemicals or radioactive isotopes that would persist in the environment for exceptionally long durations, acting as persistent chemical markers. Beyond direct physical and chemical traces, a civilization can leave trace fossils of its activity. These are not the remains of organisms themselves, but evidence of their behavior. Human footprints, tool marks on stone, or carved symbols in rock are examples of such traces. While individual marks might be lost, widespread patterns of activity, such as extensive agricultural terraces, artificial channels for water management, or even large areas of deforestation followed by specific types of reforestation, could be reflected in soil composition, erosion patterns, or pollen records over long periods. Even the distinctive patterns of settlement, like straight lines or geometric arrangements, might be detectable in ancient geological formations if conditions for preservation were ideal. Finally, the most advanced civilizations might even leave behind unique energy signatures. While radio waves dissipate quickly in space, an extremely powerful, long-lasting energy source or large-scale energy manipulation could, in theory, leave some subtle, indirect geological or chemical trace related to its energy production or consumption. However, these are far more speculative and ephemeral than physical or chemical marks. The key challenge for detecting such ancient marks is that geological processes are relentless. Erosion grinds mountains to dust, plate tectonics subducts crust back into the mantle, and volcanic activity resurfaces vast areas. Over tens of millions or hundreds of millions of years, most surface evidence is obliterated. Therefore, the search for ancient civilizations focuses on what might survive these intense forces, highly durable materials, global-scale environmental changes, or deep subsurface alterations that escape the most destructive surface processes. When considering whether an ancient civilization might have existed on Earth, it becomes critical to distinguish between the natural marks left by geological and biological processes and the potential techno-signatures that would indicate the presence of technology and intelligent activity. The challenge lies in the fact that natural processes can, at times, create patterns or structures that might initially seem anomalous. Therefore, identifying a techno-signature requires looking for evidence that cannot be explained by any known natural phenomenon and that points specifically to intelligent design or industrial activity. Natural geological traces are ubiquitous and form the bedrock of our understanding of Earth's deep history. The most fundamental is stratigraphy, the layering of rocks over millions of years. Each layer, or stratum, represents a period of deposition, containing clues about ancient environments, climates, and life forms. Sedimentation, the process by which particles settle out of water or air, naturally creates distinct layers. Volcanic eruptions leave behind layers of ash and lava. Erosion carves out canyons and shapes landscapes over vast time scales. These processes create immense geological features, such as mountain ranges, fossilized ancient seabeds, and widespread igneous or metamorphic rock formations. These natural marks are the background noise against which any potential techno-signatures must stand out. Fossils, while indicating life, are generally considered natural. Biological traces. They include the preserved remains of plants and animals, ranging from microscopic bacteria to enormous dinosaur skeletons. These fossils tell us about the evolution of life, the types of organisms that existed, and their environments. However, a fossil of a tree or a dinosaur, while an old mark, is not a techno-signature. It is a natural biological mark. The distinction becomes crucial when we consider the remains of intelligent life. A fossilized human skeleton is a biological mark, but a fossilized tool found alongside it might be considered a techno-signature. Techno-signatures, in contrast, are patterns or substances that definitively point to technology or organized, large-scale, intelligent intervention. One potential category of techno-signatures involves direct physical artifacts. These would be the remains of buildings, tools, machinery, or other manufactured objects. However, the preservation of such items over tens or hundreds of millions of years is extremely challenging. Geological forces like erosion, subduction, and metamorphism would likely destroy or dramatically alter most artificial structures. For anything to survive, it would need to be made of exceptionally durable materials and become rapidly buried and protected from these forces, perhaps through rapid sedimentation or burial in stable, non-tectonically active regions. More likely, a civilization might leave behind anthropogenic sedimentary layers. These would be distinct geological strata formed not by natural deposition, but by widespread human activity. Examples could include layers of processed materials like concrete, bricks, or refined metals, massive quantities of non-naturally occurring waste products like plastics or industrial slag, or significantly rearranged natural rock due to large-scale construction, mining, or quarrying. Such layers would appear out of place within the natural geological sequence, exhibiting compositions, textures, or structures inconsistent with natural formation processes. Chemical anomalies represent a particularly promising avenue for detecting ancient technosignatures. A technologically advanced civilization would likely engage in chemical transformations not typically found in nature. One such indicator could be unusual elemental concentrations. Extensive mining and processing of specific elements, such as copper, iron, or rare earth metals, would result in localized or widespread anomalies within geological layers. A strikingly high concentration of a metal in an ancient stratum without a natural explanation could serve as a clue. Additionally, altered isotopic ratios may point to industrial activity, especially if nuclear processes like fission or fusion were involved, leaving behind distinctive isotopic signatures of elements like uranium and plutonium. Even non-nuclear industries could subtly shift isotopic balances. Lastly, the presence of synthetic compounds, such as plastics, persistent organic pollutants, or unique alloys, offers another line of evidence. While many degrade over time, some are remarkably stable and could survive for millions of years in protected environments like deep-sea sediments or polar ice. Atmospheric and climate alterations also constitute potential technosignatures. A civilization engaging in large-scale burning of fossil fuels or industrial processes would significantly alter the composition of Earth's atmosphere, particularly levels of greenhouse gases like carbon dioxide and methane. These changes could be recorded in ice cores, ocean sediments, or ancient soil layers, while natural climate cycles cause fluctuations, a prolonged, intense, and distinct perturbation in these gas levels, combined with other chemical evidence, might hint at non-natural causes. For example, a sharp, sustained spike in carbon-13 or carbon-14 isotopes in ancient sediments, distinct from natural volcanic or biological carbon cycles, could suggest the burning of fossil fuels. Large-scale geological modification goes beyond building structures. This includes evidence of deliberate planetary engineering or terraforming, such as the creation of vast artificial lakes, major river diversions, or even subtle changes to plate tectonics or volcanic activity. If the civilization possessed such advanced capabilities, these changes would be visible as grand geological anomalies not explainable by natural forces. The primary challenge in identifying these technosignatures lies in distinguishing them from natural processes. For instance, naturally occurring mineral veins can resemble artificial structures. Some geological formations, like columnar jointing in basalt, can appear surprisingly uniform and ordered. Biological processes, too, can concentrate elements or create unique chemical environments. The key is to look for patterns that are highly improbable or impossible under natural conditions and that exhibit characteristics of intelligent design. Industrial scale or specific, non-natural chemical reactions. This often requires multiple lines of evidence converging on the same conclusion, ruling out all natural explanations before even tentatively considering an ancient civilization. The quest to find traces of a civilization millions of years old on Earth faces immense challenges, primarily due to the relentless and powerful natural processes that constantly reshape our planet. Unlike archaeological digs that uncover evidence from thousands of years ago, searching for signs from tens or hundreds of millions of years in the past requires understanding how Earth's dynamic systems erase or bury evidence over vast geological timescales. The forces of erosion, weathering, and plate tectonics are particularly effective at obliterating surface features and even deep-seated anomalies. Erosion is a primary destroyer of surface evidence. Wind, water, and ice constantly wear down mountains, transport sediment, and scour landscapes. A city built of stone or metal, if left exposed for millions of years, would be slowly but surely ground into dust and washed away. Rivers carry sediment to the oceans, glaciers carve valleys, and winds abrade rock surfaces. Over geological time, even the most massive structures would succumb to these forces. Imagine the Grand Canyon, a testament to millions of years of river erosion. Any structures built in that region during its formation would have been utterly removed. The materials from these eroded structures would then be incorporated into new sediments, losing their distinct, artificial form and becoming indistinguishable from natural rock particles. Closely related to erosion is weathering, the process by which rocks and artificial materials break down in place. Physical weathering, such as freeze-thaw cycles or root growth, cracks and fragments materials. Chemical weathering, like oxidation or dissolution by acidic rain, transforms the chemical composition of materials. Metals corrode, concrete degrades, and even durable plastics can slowly break down into microparticles. Over millions of years, these processes would reduce most manufactured objects to their constituent elements, dispersed and mixed with natural geological materials, making them virtually impossible to identify as artificial. Perhaps the most profound challenge comes from plate tectonics, the movement of Earth's massive crustal plates. Earth's surface is not static. It is a dynamic mosaic of plates that constantly move, collide, and separate. This movement has several destructive implications for ancient evidence. When oceanic plates collide with continental plates, one plate is often forced beneath the other in a process called subduction. Any surface features or shallow crustal evidence on the subducting plate is carried deep into the Earth's mantle, where it is melted and recycled. This means that vast swathes of Earth's crust, and anything on or in it, are periodically erased from the surface record. Plate collisions also lead to mountain building. As continents collide, immense pressure and heat are generated, deforming and metamorphosing existing rocks. Original structures are folded, fractured, and chemically altered, often to the point where their original form is unrecognizable. A city caught in such a collision would be crushed, melted, and transformed into new, metamorphic rock. Its artificial geometry obliterated. Even if some material survived, it would be deeply buried and incredibly difficult to access or interpret. Volcanic activity, another consequence of plate tectonics, also plays a dual role. While volcanic ash can sometimes preserve delicate structures by burying them rapidly, widespread volcanism can also destroy existing landscapes by covering them with thick layers of lava or ash, or by causing massive eruptions that reshape entire regions. Over millions of years, repeated volcanic events would bury and rebury, or simply obliterate, any surface evidence. Beyond destruction, the process of sedimentation and lithification also makes finding old marks difficult. While rapid burial can protect artifacts from immediate erosion, it also makes them inaccessible. Over geological time, layers of sediment accumulate, burying older layers deeper and deeper. As these layers are buried, they are subjected to increasing pressure and temperature, which compacts them and transforms them into solid rock. This process, diagenesis, can further alter or destroy the original structure of buried artifacts. Finding a specific, small, artificial object within miles of solid rock is akin to finding a needle in a planetary haystack. Even if an artifact were perfectly preserved within rock, the rock itself might undergo metamorphism. If buried deeply enough or subjected to tectonic forces, sedimentary rocks can be transformed into metamorphic rocks, like marble or slate. This process involves intense heat and pressure, which recrystallizes the minerals within the rock, completely obliterating any original textures or structures, including those of embedded artifacts. A metal tool, for instance, might be reduced to a few dispersed atoms within a new mineral matrix. The sheer passage of time itself is a formidable foe. Millions of years provide ample opportunity for these destructive processes to act repeatedly and cumulatively. What might survive a few thousand years will almost certainly not survive tens of millions. The geological record is inherently incomplete, biased towards the preservation of certain types of materials and environments. Soft-bodied organisms rarely fossilize, and similarly, many manufactured materials are not designed for geological longevity. Therefore, the search for very old marks shifts from looking for intact structures to searching for more subtle, persistent anomalies. This includes widespread chemical signatures, unusual isotopic ratios, or distinct geological layers that could only be explained by large-scale industrial activity. Even these, however, would have to withstand the constant churning and recycling of Earth's crust. The immense difficulty of finding such ancient traces is why the Silurian hypothesis remains firmly in the realm of speculation, requiring us to consider what minimal, yet undeniable, evidence could possibly persist through such vast and destructive spans of time. Speculating on the possible nature and appearance of a pre-human civilization requires a departure from our human-centric view. Considering the vast diversity of life that has evolved on Earth and the myriad paths intelligence might take. Such a civilization would not necessarily be humanoid, nor would its technology necessarily resemble ours. Their form, environment, and evolutionary history would profoundly shape their civilization and the types of marks they might leave behind. One of the most fundamental considerations is their physical form. Life on Earth has explored countless body plans. If intelligence arose in, for example, a cephalopod-like creature, their civilization might be entirely aquatic. Their technology would be adapted to a watery environment, perhaps utilizing hydrodynamics, bioluminescence, or pressure-resistant materials. Their structures might be built on the seafloor, carved into underwater rock formations, or even be biological in nature. Using genetically engineered organisms for construction, the marks they leave would be primarily in deep ocean sediments, potentially preserved from surface erosion, but incredibly difficult for us to access and interpret. Alternatively, intelligence could have evolved in an insect-like species, leading to a highly communal, hive-based civilization. Their structures might resemble vast, intricate mounds or underground networks, built with biological secretions, modified earth, or even advanced forms of chitin-based materials. Their technology might focus on chemical communication, bioengineering, or microscale manipulation. The traces left could be extensive subterranean complexes or uniquely altered soil compositions over wide areas. Consider also the possibility of a reptilian or avian intelligence. A reptilian civilization might be adapted to hot, arid environments, building with durable rock or ceramics, perhaps utilizing geothermal energy. An avian civilization might build structures in high places, or develop lightweight, aerodynamic technologies, potentially leaving aerial or high-altitude signatures that are less prone to surface erosion, but still subject to atmospheric processes. Their impact on the planet might be less about heavy industry and more about atmospheric manipulation or resource extraction from specific, elevated locations. The size of the intelligent beings also matters. If they were microscopic, their civilization might be a vast network of engineered microorganisms, altering the planet on a cellular or molecular level, leaving only subtle chemical or genetic traces. If they were gigantic, their structures and resource extraction would be on an immense scale, potentially leaving very large, distinct geological scars. However, larger creatures generally require more resources and are more susceptible to environmental changes, potentially limiting their longevity. Their sensory perception would also influence their technology. If they relied on echolocation, their technology might involve advanced acoustics or sonic manipulation. If they had highly developed chemosensory abilities, their technology might be based on complex chemical synthesis and detection. This would lead to different priorities in their scientific and technological development, and thus different types of waste products or energy signatures. For example, a civilization that primarily uses sound for communication and navigation might develop sophisticated sonic emitters or receivers, leaving behind unique material compositions or energy traces related to sound production. The nature of their technology would be profoundly shaped by their biology and environment. They might not use fire or electricity in the same way humans do. Their energy sources could be entirely different: geothermal, biological, tidal, or even harnessing exotic physical phenomena. Their material science might be based on principles we don't yet understand, creating substances that are incredibly durable or that degrade into unique, non-natural forms. For instance, if their planet lacked abundant metals, they might develop advanced ceramics, bioplastics, or composite materials that leave different types of geological traces. The longevity and scale of their civilization are also critical. A short-lived civilization, even if technologically advanced, would leave fewer and more ephemeral marks. A civilization that lasted for millions of years, like some of Earth's dominant biological forms, would have a much greater chance of leaving detectable, widespread signatures, even if they are subtle. The extent of their global impact, whether they were confined to a single continent or spread across the entire planet, would also determine the scale and distribution of their potential techno-signatures. Finally, their social structure and goals could influence their physical legacy. A highly cooperative, unified civilization might undertake massive, coordinated planetary engineering projects. A fragmented, warring civilization might leave behind evidence of widespread destruction or defensive structures. If their ultimate goal was to leave Earth, they might have developed advanced space travel, potentially leaving behind launch sites or orbital debris, though these would be exceedingly difficult to find after millions of years. If they retreated underground or into the oceans, their marks would be hidden from easy detection. In essence, a pre-human civilization might look radically different from anything we imagine. Their cities might be vast, fungal networks. Their tools might be bioengineered organisms, and their waste might be unique chemical compounds. The challenge for us is to broaden our search beyond human-like expectations and consider the full spectrum of possibilities that Earth's long evolutionary history might have produced, looking for anomalies that defy natural explanation, regardless of their form. To understand the vastness of Earth's history before the emergence of Homo sapiens, it is essential to briefly review the dominant life forms and major geological eras that preceded us. Our planet has been teeming with life for billions of years, undergoing profound transformations, with different groups of organisms rising to prominence, diversifying, and sometimes facing mass extinction, long before anything resembling a human walked the Earth. The earliest and longest chapter of Earth's biological history is the Precambrian Eon, which spans from Earth's formation about 4.54 billion years ago until the start of the Cambrian period, approximately 541 million years ago. For the first 2 billion years or so, Earth's surface was likely too hot and unstable for life. The earliest definitive evidence of life in the form of simple, single-celled organisms like bacteria and archaea appears around 3.8 billion years ago. These microscopic life forms were the sole inhabitants of Earth for an incredibly long time. A major turning point in the Precambrian was the Great Oxidation Event, which began around 2.4 billion years ago. Photosynthetic bacteria, particularly cyanobacteria, began producing oxygen as a byproduct, slowly accumulating it in the atmosphere and oceans. This was a monumental environmental change, leading to the extinction of many anaerobic life forms, but paving the way for the evolution of oxygen-breathing organisms. Towards the end of the Precambrian, in the Ediacaran period, the first complex, multicellular life forms appeared. These were soft-bodied, often disc-shaped or frond-like organisms, quite unlike modern animals. And their fossil record is sparse. The Paleozoic era followed, beginning with the Cambrian period 541 million years ago. This period is famous for the Cambrian explosion, a relatively rapid diversification of animal life. Within a few tens of millions of years, most major animal phyla, including ancestors of arthropods, mollusks, and chordates, appeared in the fossil record. Many of these new life forms developed hard parts, like shells and exoskeletons, which greatly improved their chances of fossilization. The oceans were dominated by trilobites, brachiopods, and early forms of mollusks. The Ordovician period saw the diversification of marine invertebrates, including corals and crinoids, and the appearance of the first jawless fish. Towards the end of the Ordovician, the first plants began to colonize land. This period ended with a major ice age and mass extinction event. During the Silurian period, jawed fish diversified, and vascular plants, with specialized tissues for transporting water and nutrients, became more widespread on land. This allowed plants to grow larger and colonize drier areas. The Devonian period is often called the Age of Fish, as diverse fish species, including armored placoderms and lobe-finned fish, thrived in the oceans. On land, forests of primitive trees emerged, and the first amphibians evolved from lobe-finned fish. Taking their first steps onto land, insects also appeared during this time. The Carboniferous period was characterized by vast, swampy forests that covered much of the land. These forests, composed of giant ferns and club mosses, eventually formed the immense coal deposits we mine today. Amphibians were abundant, and the first reptiles, which could lay eggs on land, evolved, marking a significant step towards fully terrestrial life. The Permian period saw the formation of the supercontinent Pangaea. Reptiles diversified and became the dominant land animals, including early mammal-like reptiles. This era ended with the most severe mass extinction event in Earth's history, the Great Dying, which wiped out an estimated 96% of marine species and 70% of terrestrial vertebrate species. This event was likely caused by massive volcanic eruptions in Siberia, leading to extreme global warming and ocean acidification. The Mesozoic era, often known as the Age of Dinosaurs, began after the Permian extinction and lasted from 252 to 66 million years ago. It is divided into three periods. The Triassic period saw the recovery of life after the Permian extinction. Dinosaurs first appeared during this time, evolving from earlier reptiles, and began to diversify. The first mammals also evolved. Though they remained small and nocturnal, the Jurassic period was the golden age of giant dinosaurs, such as the long-necked sauropods and formidable predators like Allosaurus. The first birds evolved from small, feathered dinosaurs. Pangaea began to break apart, leading to new oceans and climates. The Cretaceous period saw the continued dominance of dinosaurs, including Tyrannosaurus rex and Triceratops. Flowering plants evolved and rapidly diversified, changing terrestrial ecosystems. This era, and the Age of Dinosaurs, ended abruptly 66 million years ago with the Cretaceous Paleogene extinction event caused by a large asteroid impact near the Yucatan Peninsula. This catastrophic event led to widespread fires, tsunamis, and a prolonged impact winter that decimated 3/4 of all plant and animal species, including all non-avian dinosaurs. The Cenozoic era began 66 million years ago and continues to the present day. This is often called the Age of Mammals. With the ecological niches left vacant by the dinosaurs, mammals rapidly diversified and evolved into a vast array of forms, including large herbivores, carnivores, and marine mammals like whales. Early primates also emerged during this time. Over tens of millions of years, the continents drifted into their current positions, and Earth's climate experienced significant shifts, including periods of global warming and cooling. The Neogene period saw the evolution of apes and the divergence of early hominids from other primates. The Quaternary period, beginning 2.6 million years ago, is characterized by repeated ice ages and the emergence of our own species. It is within this immense and dynamic tapestry of life, spanning billions of years and numerous dominant species and ecosystems, that the question of a pre-human civilization arises. The vast stretches of time before the rise of humans provided ample opportunity for complex life to evolve, and potentially for intelligence to emerge and develop technology, only to be erased by the very geological and biological forces that shaped Earth's long story. Mass extinction events are periods in Earth's history characterized by a rapid and widespread decrease in the diversity of life on the planet. These are not merely slow declines, but catastrophic losses across many different groups of organisms, leading to a dramatic reduction in biodiversity. Over the last 540 million years, since the Cambrian explosion that saw a great diversification of complex life, scientists have identified 5 major extinction events, often called the Big Five, each leaving an indelible mark on the course of evolution and reshaping the living world. Such events have the profound capacity to reset life on Earth, wiping out dominant groups and opening up ecological niches for new forms of life to flourish. For an ancient civilization, such an event would pose an existential threat, potentially erasing all physical and cultural traces. One of the most famous and well-studied of these events is the Cretaceous-Paleogene, or KPG extinction, which occurred approximately 66 million years ago. This cataclysmic event is most famously associated with the demise of the non-avian dinosaurs, but it also wiped out about 3/4 of all plant and animal species on Earth, including many marine reptiles, ammonites, and significant portions of plant life. The primary cause for the KPG extinction is widely accepted to be the impact of a massive asteroid, estimated to be about 10 to 15 kilometers wide near the Yucatan Peninsula in what is now Mexico. This impact created the Chicxulub crater, a feature about 180 kilometers in diameter. The immediate aftermath of such an impact would have been devastating. Upon hitting Earth, the asteroid would have created an enormous explosion, far more powerful than any nuclear weapon. This would have generated an immediate fireball, vaporizing everything within a wide radius and triggering widespread wildfires across continents due to immense heat pulses. A massive tsunami, hundreds of meters high, would have radiated across the Gulf of Mexico, devastating coastal areas thousands of kilometers away. Simultaneously, billions of tons of dust, soot, and vaporized rock would have been ejected into the atmosphere, blocking out the sun globally. This impact winter would have plunged the planet into darkness for months or even years, causing global temperatures to plummet and halting photosynthesis. Without sunlight, plants would die, collapsing the base of the food web. Herbivores would starve, followed by carnivores. Beyond the immediate impact, longer-term effects would have continued the devastation. Sulfates released from the vaporized rock would have caused severe acid rain, acidifying oceans and destroying terrestrial vegetation. The massive amount of carbon dioxide released by the impact, along with subsequent volcanism, could have eventually led to global warming after the initial cooling period, further stressing surviving ecosystems. While the asteroid impact is the leading theory, some scientists suggest that prolonged volcanic activity in the Deccan Traps in India, which released massive amounts of greenhouse gases and aerosols, also contributed to the environmental stress leading up to or during the KPG extinction. Regardless of the exact interplay of factors, the result was a planet undergoing a profound and rapid environmental collapse. The KPG extinction demonstrates a powerful reset mechanism. The dominant terrestrial life forms for 184 million years, the large dinosaurs, were largely annihilated. Species that could survive in darkness, cold, and with limited food sources, such as small, burrowing mammals, birds, and some reptiles were more likely to persist. The vacuum left by the dinosaurs allowed for the rapid diversification and ascendancy of mammals, which had previously been relegated to smaller, more nocturnal niches. Over the subsequent 66 million years, mammals evolved to fill nearly every ecological role, leading to the diverse mammalian life we see today, including our own lineage, another, even more devastating. Extinction event was the Permian-Triassic extinction, which occurred about 252 million years ago, often referred to as the Great Dying. This event was the most severe known extinction in Earth's history, wiping out an estimated 96% of all marine species and 70% of terrestrial vertebrate species. The primary cause for this catastrophe is believed to be massive volcanic eruptions in the Siberian Traps, a large igneous province in what is now Russia. These eruptions released enormous volumes of lava, but more critically, they also discharged vast quantities of greenhouse gases like carbon dioxide and methane, as well as sulfur dioxide, into the atmosphere over hundreds of thousands of years. The environmental consequences were catastrophic. The massive release of greenhouse gases led to extreme global warming, causing temperatures to rise significantly, both on land and in the oceans. This warming led to widespread anoxia in the oceans, meaning a severe depletion of oxygen, which suffocated marine life across vast areas. Ocean acidification, caused by the absorption of excess carbon dioxide, further crippled marine ecosystems, particularly those with calcium carbonate shells or skeletons. On land, acid rain destroyed forests, and climate shifts led to widespread desertification. The combination of these stresses created a truly uninhabitable planet for most life forms. The recovery from the Permian-Triassic extinction was agonizingly slow, taking many millions of years, fundamentally reshaping ecosystems and paving the way for the rise of the dinosaurs in the subsequent Triassic period. For a hypothetical ancient civilization, a mass extinction event would be an apocalyptic scenario. Direct physical destruction from asteroid impacts, massive volcanic eruptions, tsunamis, or widespread fires would obliterate cities and infrastructure. Even if some structures survived the initial shock, the ensuing global environmental collapse would render the planet uninhabitable for a complex, technologically dependent society. Agricultural systems would fail due to prolonged darkness, extreme temperatures, or acid rain, leading to mass starvation. Water source would become contaminated. The collapse of the ecosystem would mean the loss of all resources necessary for survival, even if a small fraction of the population survived. The societal structures, technological knowledge, and cultural heritage of such a civilization would likely be lost entirely. Furthermore, the geological aftermath of such events would bury or destroy any remaining archaeological evidence. Vast layers of ash, impact ejecta, or sediments deposited by tsunamis and altered river systems would quickly entomb or obliterate surface features over millions of years. Subsequent geological processes like erosion, burial by new layers of rock, and the constant movement of Earth's tectonic plates would further ensure that any potential traces of a past civilization are either ground into unrecognizable dust, melted deep within the Earth, or buried under kilometers of subsequent geological material, effectively erasing their existence from the observable record. These Big Five extinction events truly represent a powerful natural reset button for life, and any civilizations that might have existed. The fossil record, while an invaluable chronicle of life on Earth, is inherently incomplete. This incompleteness poses significant challenges for paleontologists seeking to understand ancient life, and even greater difficulties for anyone searching for the subtle, possibly non-biological, traces of an ancient civilization. The process of fossilization is a rare and precarious one, requiring a very specific set of circumstances to occur, which means that only a tiny fraction of all organisms that have ever lived are preserved as fossils. First and foremost, for an organism to become a fossil, it must be rapidly buried soon after death. If a dead plant or animal is left exposed to the elements, it will quickly decompose, be scavenged by other organisms, or be broken down by bacteria. Burial protects the remains from these destructive forces, creating an anaerobic environment that slows decay. This is why marine environments, where sedimentation rates are often high and oxygen levels can be low in bottom waters, tend to yield a richer fossil record than terrestrial environments. On land, rapid burial by sediment from floods, volcanic ash, or sand dunes is less common. Another critical factor is the presence of hard parts, bones, teeth, shells, and wood are far more likely to fossilize than soft tissues like muscles, skin, or internal organs. These hard parts are more resistant to decay and can be replaced by minerals over time, turning into stone. Soft-bodied organisms, despite being incredibly abundant throughout Earth's history, are exceedingly rare in the fossil record. Exceptional fossil sites, like the Burgess Shale in Canada or the Ediacaran biota in Australia, provide glimpses into soft-bodied life, but these are rare exceptions caused by extraordinary preservation conditions. If an ancient civilization predominantly utilized materials that were soft, biodegradable, or highly corrosive, its traces would be even less likely to endure. Even if an organism or an object is successfully fossilized, it must then survive the relentless march of geological time. The Earth's crust is dynamic, constantly being shaped by forces that can destroy or conceal fossils. Erosion, caused by wind, water, and ice, can wear away rock layers, exposing fossils to the elements, where they can disintegrate. Conversely, continued sedimentation can bury fossils deeper and deeper, making them inaccessible for millions of years. Heat and pressure from deep burial or tectonic activity can transform sedimentary rocks into metamorphic rocks, a process that often obliterates any organic material or delicate structures, turning them into unrecognizable mineral grains. Subduction, where one tectonic plate slides beneath another, carries vast volumes of rock, including any contained fossils, deep into the Earth's mantle, where they are melted and recycled. Furthermore, the fossil record suffers from significant sampling biases. Marine environments are overrepresented due to more favorable sedimentation conditions. Organisms with robust hard parts are more frequently found than delicate ones. Certain geological periods or environments that were particularly conducive to fossilization might appear to have had a greater diversity of life simply because their record is better preserved. This means that vast swaths of Earth's ancient biodiversity remain completely unknown to us because the conditions for their preservation were never met, or their fossils have long since been destroyed. When it comes to the specific challenge of finding non-biological traces, or technofossils, of an ancient civilization, the difficulties are compounded. Manufactured items, while sometimes made of durable materials like stone or ceramic, often lack the biological structure that facilitates traditional fossilization. Metals corrode, plastics degrade, and complex machinery might simply crumble into unrecognizable fragments over geological timescales. To be preserved, such items would need extremely rapid and gentle burial in a stable environment. Consider the challenge of microtraces. Even tiny biological fossils, known as microfossils, require specialized techniques to find and identify. These include pollen grains, spores, and microscopic organisms. If an ancient civilization left behind microscale technosignatures, such as ancient microplastics, microscopic industrial byproducts, or minute remnants of advanced materials, detecting them would be incredibly difficult. These traces might be dispersed thinly throughout vast volumes of ancient sediment, making their identification like searching for a specific needle in a haystack of planetary proportions. Distinguishing these from naturally occurring mineral grains or biological microfossils would require sophisticated analytical methods and a precise understanding of natural geochemistry. Moreover, the sheer vastness of Earth's surface and the depth of its geological layers present immense logistical hurdles. Most of Earth's ancient rock record remains buried kilometers deep, inaccessible to direct observation. Even exposed ancient rock formations represent only a fraction of the planet's past. Paleontologists rely on natural exposures, such as river cuts or mountain uplifts, or expensive drilling projects to access these deep layers. The probability of randomly stumbling upon a perfectly preserved, recognizable artifact from a civilization tens or hundreds of millions of years ago is astronomically small, especially given the destructive forces of geology. Finally, there is the problem of interpretation. Even if an anomalous structure or chemical signature is found, distinguishing a true artifact from a naturally occurring oddity is immensely challenging. Geological processes can create surprisingly regular or seemingly designed formations, like concretions that resemble tools or rock structures that look like walls. Without clear, undeniable evidence of intelligent design and an understanding of the material's origin, such finds are often, and rightly, attributed to natural geological or biological processes, preventing out-of-place artifacts from gaining widespread scientific acceptance. The incomplete and biased nature of the fossil record, combined with the destructive forces of geology and the difficulty of finding and interpreting subtle traces, means that much of Earth's ancient past, including any potential civilizations, may remain forever lost to our direct observation. Earth is not a static planet. Its outermost layer, the lithosphere, is in constant, albeit slow, motion. This dynamic process is known as plate tectonics, and it profoundly shapes our world, from creating mountains and volcanoes to recycling the very crust beneath our feet. This continuous geological activity acts as a relentless eraser, burying or destroying ancient evidence, including any potential traces of past civilizations. Understanding this fundamental process is key to appreciating why signs of an ancient civilization from millions or hundreds of millions of years ago would be so incredibly difficult, if not impossible, to find. Earth's lithosphere, which includes the crust and the rigid, uppermost part of the mantle, is broken into several large pieces called tectonic plates. These plates float and move across the semi-fluid layer beneath them, known as the asthenosphere. The movement is driven by heat from Earth's interior, causing convection currents within the mantle. The plates typically move at speeds of a few centimeters per year, roughly the same rate at which fingernails grow. While this movement seems slow on a human timescale, over millions of years, it results in monumental geological transformations. One of the most significant consequences of plate tectonics is the process of subduction. This occurs at convergent plate boundaries, where one tectonic plate slides beneath another, descending into the Earth's mantle. Typically, denser oceanic crust subducts beneath lighter continental crust or beneath another oceanic plate. As the oceanic plate descends, it carries with it not only vast amounts of rock and sediment, but also any surface features, including ancient landforms, oceanic crust, and any artificial structures or waste that might have settled on the seafloor or been carried along on the plate. As the subducting plate plunges deeper into the mantle, it is subjected to immense heat and pressure. The temperatures rise to thousands of degrees, and the pressures become enormous. Under these extreme conditions, the rocks and any materials within them undergo significant physical and chemical changes. They can melt, forming magma that may rise to create volcanoes on the overriding plate. Or they can be metamorphosed, transformed into entirely new rock types. In either case, the original structures, compositions, and organization of any ancient artifacts or industrial waste would be completely obliterated, homogenized, and integrated into the Earth's deeper geological cycles. This continuous subduction means that oceanic crust is relatively young. Very little of it is older than 200 million years, because older crust is constantly being recycled. Any trace of a civilization that resided on or near oceanic plates millions of years ago would have long since been carried down into the Earth's interior. Another type of plate boundary is a continental collision zone, where two continental plates, both relatively buoyant, collide. Instead of one subducting, they buckle, fold, and thrust against each other, creating massive mountain ranges like the Himalayas. In these zones, rocks are subjected to incredible compressional forces, intense heat, and deep burial. Original surface features, including any ancient cities or modified landscapes, would be crushed, fractured, uplifted, and then subjected to intense erosion. The material is so heavily deformed and metamorphosed that any delicate or recognizable structures would be utterly destroyed and transformed into unrecognizable components of mountain rock. At rift zones, plates pull apart, creating new crust. In oceanic rift zones, magma wells up from the mantle to form new oceanic crust, often along mid-ocean ridges. Any evidence of a civilization on or near such a spreading ridge would be rapidly buried by successive lava flows or pulled apart and subjected to immense heat. On continents, rifting can lead to the formation of grabens or massive basaltic flood eruptions, burying landscapes under vast sheets of volcanic rock. Beyond the direct destructive forces at plate boundaries, the general processes of erosion and sedimentation also contribute to the erasure or burial of ancient evidence. Weathering breaks down rocks into smaller particles. Wind, water, and ice then transport these sediments, sculpting landscapes and carrying material from high elevations to low-lying basins. While sedimentation can preserve, it also buries existing landscapes under thousands of meters of new material. Over geological timescales, vast plains can be covered by sediments from eroded mountain ranges, effectively entombing everything beneath them. Conversely, areas that were once deeply buried can be uplifted by tectonic forces, only to be exposed to intense erosion that then wears away their surface, carrying away any ancient evidence. The cumulative effect of these processes is that Earth's surface is constantly being renewed and recycled. Very little of the exposed Earth's crust is extremely old. Most of the rocks we see on the surface date back only hundreds of millions of years, not billions. The oldest surviving rocks are found in stable areas called cratons, which are ancient, relatively undeformed parts of continental crust. Even these cratons have experienced billions of years of erosion and deposition, meaning that while the rock itself is old, any direct surface evidence from billions of years ago would likely have been eroded away long ago or deeply buried under more recent sediments. Therefore, for any hypothetical ancient civilization that existed millions or hundreds of millions of years ago, the chances of its physical structures surviving are infinitesimally small. Earth's moving skin systematically destroys and recycles its surface features. Any cities, roads, or industrial complexes would be subjected to crushing pressures, intense heat, melting, or grinding erosion. Even if deep drilling were to penetrate ancient layers, what might be found would likely be unrecognizable fragments, chemically altered traces, or highly deformed layers, rather than intact or easily interpretable artifacts of a sophisticated society. The Earth's geology is a powerful, persistent force that acts to erase the memory of its deep past, making the search for ancient civilizations a formidable scientific challenge. The search for ancient, lost civilizations on Earth often conjures images of buried cities or monumental ruins. However, the immense power of geological processes over vast timescales means that such physical structures are exceedingly unlikely to survive for millions of years. Instead, a more subtle, yet potentially enduring, form of evidence lies in the chemical signatures left behind by industrial activities. A technologically advanced civilization fundamentally alters the chemistry of its environment, producing elements, compounds, and isotopic ratios that are distinct from natural processes. These chemical clues could persist in the geological record long after any physical structures have crumbled into dust. One primary way a civilization leaves chemical traces is through the widespread concentration of elements. Natural geological processes distribute elements according to their geochemical properties, forming mineral deposits over eons. However, industrial activity involves the deliberate extraction, refinement, and concentration of specific elements far beyond their natural background levels. For example, the smelting of metals like iron, copper, aluminum, or lead involves taking widely dispersed ores and concentrating the desired metal. This process creates unique deposits of refined metals or their byproducts, such as slag, which have chemical compositions and forms not found in nature. If an ancient civilization engaged in metallurgy on a large scale, we might find layers in the geological record with anomalous concentrations of these industrial metals or their related waste products, indicating widespread mining and processing. The presence of such concentrations in strata millions of years old, especially if co-located with other unusual findings, could be a compelling chemical clue. Furthermore, the demand for modern technologies, particularly electronics, has led to a significant increase in the use of rare earth elements. These elements, such as neodymium, europium, and dysprosium, are crucial for components like magnets, batteries, and display screens. While naturally occurring, their widespread extraction and industrial use would create a distinct geochemical footprint. Detecting an unusually high, localized concentration of a specific suite of rare earth elements in an ancient sedimentary layer, especially without a natural geological explanation like a specific ore deposit, could point towards the existence of advanced technology that utilize these elements. Beyond elemental concentrations, a more sophisticated chemical clue lies in the isotopic ratios of elements. Isotopes are atoms of the same element that have different numbers of neutrons. While natural processes can cause slight variations in isotopic ratios, certain industrial or technological activities can produce highly anomalous and distinctive isotopic signatures. One of the most studied examples relates to carbon isotopes. Living organisms preferentially take up carbon-12 over the heavier carbon-13. When ancient organic matter is formed and then later burned by a civilization, it releases carbon dioxide into the atmosphere and oceans with a relatively low proportion of carbon-13 compared to the general atmospheric carbon dioxide produced by volcanic activity or natural decay. This light carbon signature can then be incorporated into sediments, ancient carbonates, and even the fossilized remains of marine organisms or plant life from that period. From that, a significant, sustained, and global shift in the carbon-13 to carbon-12 ratio in the geological record that cannot be explained by natural biological or volcanic cycles could be a strong indicator of an ancient industrial age. Similarly, nitrogen isotopes can provide clues. Natural processes like nitrogen fixation by bacteria establish certain isotopic ratios in soils. However, the large-scale production and use of synthetic nitrogen fertilizers, a hallmark of modern agriculture, can alter these ratios. If an ancient civilization practiced intensive agriculture using artificial fertilizers, these altered nitrogen isotopic signatures might be detectable in ancient soil horizons or sedimentary layers, particularly in regions that would have supported agriculture. Moreover, the processing of metals or other materials can subtly alter the isotopic ratios of those elements. For instance, some metallurgical processes or the refinement of specific industrial chemicals might fractionate isotopes in ways that do not occur naturally. While these shifts might be subtle, advanced analytical techniques could potentially detect them. The most dramatic isotopic shifts, however, are associated with nuclear activity, which is discussed in greater detail in another section. The distinct isotopic fingerprint left by nuclear fission, including altered uranium and plutonium ratios and the creation of unique fission products, is perhaps the clearest and longest-lasting chemical techno signature. Finally, The deliberate synthesis of new chemical compounds that do not exist naturally on Earth provides another category of chemical clues. Modern society has created a vast array of synthetic organic compounds, such as plastics, pharmaceuticals, and persistent organic pollutants like polychlorinated biphenyls or dichlorodiphenyltrichloroethane. Many of these compounds are highly stable and resist natural degradation processes. If an ancient civilization developed advanced organic chemistry, its waste products could include such synthetic, long-lived molecules. Finding a layer in ancient sediments containing complex organic molecules with structures that defy natural biological or geological formation would be a very strong chemical indicator of an advanced civilization. The challenge in interpreting these chemical clues lies in the immense time frame and the powerful natural processes that can dilute, disperse, or alter chemical signatures, volcanic eruptions, natural weathering, and fluid migration within the Earth's crust can all create localized chemical anomalies. Therefore, any potential chemical techno-signature would need to be widespread, persistent, and distinctly anomalous compared to the background variations caused by natural processes. Furthermore, the anomaly would ideally need to be corroborated by multiple, independent lines of chemical evidence, or even better, by other forms of potential techno-signatures, to build a compelling case for an ancient technological civilization. Human civilization, especially in its current industrial and post-industrial phases, produces an astonishing amount and variety of waste. Much of this waste is made of materials specifically engineered for durability and longevity. When considering the possibility of an ancient, pre-human civilization, these incredibly long-lasting waste products become critical. Potential techno-signatures, physical evidence of advanced technology that could survive for millions of years within the geological record. Unlike fragile organic matter that quickly decays, these materials are designed to resist natural degradation processes, making them prime candidates for deep time preservation. Plastics are perhaps the most iconic example of modern, long-lasting waste. These synthetic polymers are derived from hydrocarbons, primarily petroleum, and are characterized by very strong carbon-carbon bonds in their molecular structures. This molecular stability makes them remarkably resistant to chemical and biological decomposition. While plastics do break down, the process is extremely slow. Exposure to ultraviolet light, oxygen, and certain microbial activity can cause them to fragment into smaller pieces, eventually leading to microplastics and nanoplastics. However, even these tiny particles retain their fundamental chemical composition and can persist in the environment for hundreds to thousands of years. The longevity of plastics increases significantly in environments where degradation factors are limited. In deep ocean sediments, buried terrestrial landfills, or anoxic environments, plastics can remain largely intact for much longer periods, potentially stretching into millions of years if conditions are stable and geological forces do not obliterate them. Researchers have already found plastics embedded in geological formations of the modern era, creating plastiglomerates, new types of rock formed when plastic debris melts and fuses with natural materials like sand, pebbles, and shell fragments. If an ancient civilization used similar, durable synthetic polymers, such ancient plastiglomerates or widespread microplastic layers in ancient sediments could be a unique and unmistakable techno-signature. The distinctive molecular structure of synthetic polymers, unlike anything found in natural biological or geological processes, would serve as a clear indicator of artificial origin. Beyond plastics, industrial byproducts like slag, fly ash, and concrete represent vast quantities of highly durable waste materials. Slag is the glassy or crystalline waste product left over from the smelting of metals such as iron, copper, or lead. It consists of molten impurities separated from the desired metal, Depending on its composition, slag can be extremely stable and resistant to weathering and chemical attack. Ancient slag heaps from early human metallurgy still exist after thousands of years. If an ancient civilization performed large-scale metal production, massive quantities of slag, with their unique mineralogy and elemental composition, could form distinct geological deposits. Unlike naturally occurring rocks, slag often has a vitrified, often bubbly, texture and specific elemental ratios that would be anomalous in a natural rock sequence. Fly ash and bottom ash are residues produced from the combustion of coal and other fossil fuels in power plants and industrial facilities. Fly ash consists of fine, powdery particles, while bottom ash is heavier and coarser. Both contain concentrated heavy metals and unique mineral phases that are direct products of high-temperature combustion of complex organic matter. These materials can be dispersed widely through the atmosphere or deposited in landfills. Over millions of years, widespread dispersal of these ashes could create thin but chemically distinct layers in sedimentary rock, serving as a global marker of a civilization that relied on large-scale fossil fuel burning. The presence of specific trace elements or unique mineral phases within these layers would distinguish them from natural volcanic ash or other natural deposits. Concrete and brick are fundamental building materials of human civilization, essentially artificial rocks. Concrete, invented by the Romans, though refined and industrialized more recently, consists of aggregates bound together by a cement paste. Modern concrete is incredibly strong and durable, designed to last for centuries. Bricks, made from fired clay, are similarly resistant to degradation. The sheer volume of these materials used in construction means that a technologically advanced civilization would leave vast amounts of them. If buried under specific geological conditions, layers of ancient concrete or brick rubble could be preserved as unique, anthropogenically formed sedimentary deposits, characterized by their distinct composition, texture, and often geometric shapes not found in natural rock formations. Finally, ceramics and glass are also extremely durable. Ceramics, made by firing clay at high temperatures, and glass, produced by cooling molten silica, are chemically inert and highly resistant to natural weathering and microbial degradation. While they can break into fragments, the material itself persists for geological timescales. Archaeological finds of ancient pottery shards and glass fragments dating back thousands of years attest to their longevity. Widespread use and subsequent disposal by an ancient civilization could lead to the preservation of fragments of these materials in ancient sediment layers, identifiable by their unique amorphous structure or specific crystalline phases and elemental composition. The challenge for identifying these long-lasting waste products lies in their dispersal and the immense power of geological forces. While materials like plastics or concrete are durable, they can still be eroded, subducted, or metamorphosed over millions of years. However, if conditions for preservation are ideal, such as rapid burial in stable sedimentary basins or deposition in deep-sea environments, these unique artificial materials could endure as compelling evidence, representing a distinct and undeniable techno-signature of a past, advanced society. Their very existence, with chemical and structural properties alien to natural geology, would stand as a testament to intelligent design and industrial activity. Among the most compelling and potentially enduring techno-signatures that a past, advanced civilization might leave behind is its nuclear waste. Nuclear power and nuclear weapons production generate radioactive byproducts that are extraordinarily long-lived, far surpassing the lifespan of most other human-made materials. The unique isotopic fingerprints of these materials, combined with their extreme durability, could serve as a very long-term indicator of a sophisticated society that harnessed atomic energy. Nuclear waste arises primarily from the process of nuclear fission, where the nuclei of heavy atoms are split to release energy. This splitting produces a wide array of lighter atoms called fission products, many of which are radioactive. Additionally, some of the original fuel atoms or other heavy atoms within the reactor can absorb neutrons and transform into heavier, unstable elements known as actinides, like plutonium, americium, and curium. Both fission products and actinides are highly radioactive and decay over time, emitting radiation and transforming into more stable elements. The key characteristic that makes nuclear waste a potent long-term technosignature is the half-life of its constituent radionuclides. A half-life is the time it takes for half of the radioactive atoms in a sample to decay. While some radionuclides have short half-lives, many have half-lives extending for thousands, millions, or even billions of years. For example, plutonium-239, a key component of nuclear waste and weapons, has a half-life of approximately 24,100 years. Technetium-99, a significant fission product, has a half-life of 212,000 years. Iodine-129 has a half-life of 15.7 million years. Cesium-135 has a half-life of 2.3 million years. Perhaps most significantly, uranium-238. The most common isotope of uranium has a half-life of 4.468 billion years, which is roughly the age of the Earth itself. The presence of these specific, long-lived radionuclides, especially in ratios that cannot be explained by natural geological processes or cosmic ray interactions, would be a strong indicator of nuclear activity. One of the most striking aspects of nuclear waste is its unique isotopic composition. Natural uranium deposits contain a specific ratio of uranium isotopes, primarily uranium-238 and a much smaller amount of fissile uranium-235. When uranium is used in a nuclear reactor, the uranium-235 is consumed, leading to its depletion. Simultaneously, new short-lived fission products are created, along with longer-lived ones like iodine-129 and technetium-99 and transuranic elements like plutonium-239 that are exceedingly rare or non-existent in natural terrestrial environments. Therefore, detecting ancient geological layers that contain depleted uranium alongside an anomalous presence of long-lived fission products and specific transuranic elements would provide compelling evidence of artificial nuclear fission. A concrete, factual example of how nuclear fission products can be preserved in the geological record comes from the Oklo Natural Nuclear Reactor in Gabon, West Africa, approximately 1.7 billion years ago. A unique set of geological and geochemical conditions allowed natural uranium deposits to undergo sustained nuclear fission, operating like a rudimentary nuclear reactor for hundreds of thousands of years. The distinctive isotopic signatures of the fission products, such as neodymium and ruthenium, found within the Oklo ore bodies provide undeniable evidence of this ancient nuclear activity. The fact that these isotopic anomalies have persisted for nearly 2 billion years demonstrates the extraordinary longevity of nuclear signatures in suitable geological environments. Modern strategies for managing high-level nuclear waste involve deep geological repositories. These facilities are designed to isolate radioactive waste from the biosphere for hundreds of thousands to millions of years by burying it deep within stable rock formations, such as granite, salt, or clay. The very design principle behind these repositories, that they can safely contain waste for geological timescales, underscores the potential for nuclear waste to become a very long-term technosignature. If an ancient civilization also developed and utilized nuclear technology, it might have similarly disposed of its waste in geologically stable, deep formations, inadvertently creating a lasting marker of its existence. The detection of these nuclear waste signs in the ancient geological record would involve searching for highly localized concentrations of specific radioactive isotopes or their stable decay products, especially in ratios that defy natural explanation. For instance, an unusually high concentration of iodine-238 129 or technetium-99, or the presence of plutonium-239 that has since decayed into its daughter products but left a unique isotopic legacy, would be powerful clues. The presence of these elements, distinct from naturally occurring background levels and in patterns inconsistent with natural decay chains of primordial radionuclides, would strongly suggest an artificial origin. Furthermore, evidence of localized radiation damage to the surrounding rock or minerals, appearing as specific crystal lattice defects or altered mineral phases, could corroborate the presence of ancient nuclear materials. The definitive identification of such a signature would require rigorous analysis to rule out all natural explanations, but the unique nature of nuclear fission products makes them uniquely compelling as potential indicators of a very ancient, advanced society. Civilizations, by their very nature, are transformative forces on a planet's surface and even beneath it. The scale of their activities, particularly in resource extraction and construction, leaves distinctive scars on the geological record. These marks, if large and persistent enough, could theoretically endure for millions of years, offering tantalizing clues to an ancient, pre-human civilization. Understanding the nature of these marks is key to knowing what to look for when considering the Silurian hypothesis. One of the most profound ways a civilization impacts the Earth is through mining. Modern mining operations, for example, create immense open-pit mines that are visible from space, resembling vast, terraced bowls carved into the landscape. The Bingham Canyon Mine in Utah, for instance, is over 4 kilometers wide and over 1.2 kilometers deep. These excavations displace billions of tons of rock and ore. Underground mines, while less visible from the surface, involve extensive networks of tunnels and shafts that can extend for hundreds of miles and reach depths of thousands of feet. For example, the deepest mines can reach more than 3 kilometers into the Earth's crust. Both open pit and underground mining fundamentally alter the local geology. They expose rock layers that would otherwise be buried, create new topographical features, and leave behind enormous spoil heaps or tailings ponds. Piles of waste rock and processed materials that contain unique chemical signatures from the ore extraction process. These spoil heaps, often rich in specific elements or processing chemicals not naturally found in such concentrations, represent distinct human-made geological deposits. Even after millions of years of erosion, the footprint of such massive excavations might remain as anomalous depressions or unusual patterns in bedrock, while the associated waste deposits could form distinct, chemically unusual layers within sedimentary rock. The presence of specific processed minerals or unusual concentrations of heavy metals within these layers would be a clear indicator of industrial activity. Beyond extracting metals, the mining of fossil fuels, coal, oil, and natural gas also leaves deep and lasting marks. Coal mining creates vast underground voids or surface strip mines that reshape the land. Oil and natural gas extraction involves drilling wells that penetrate deep into geological formations, altering subsurface pressure regimes and leaving behind a network of boreholes. While the wells themselves might collapse or fill in over geological timescales, the pervasive extraction of these carbon-rich resources would lead to a depletion of specific carbon reserves in certain geological strata. Detecting vast areas where coal seams are missing or where expected oil and gas deposits have vanished in ancient rocks could be an indirect sign of extensive past consumption by a civilization. The resulting voids could also lead to long-term subsidence of the land surface, creating subtle but persistent depressions. Construction activities are another major way civilizations reshape the planet. Cities, roads, bridges, and dams involve moving immense quantities of earth and rock, quarrying materials, and producing new ones like concrete and brick. Modern concrete production alone consumes billions of tons of raw materials annually. A large city, over time, creates an urban geology, a distinct layer of human-made artifacts, debris, and altered natural materials that is different from surrounding natural sediments. This layer, sometimes referred to as the archaeological layer or urban stratum, would contain fragmented building materials, waste products, and rearranged geological deposits. For an ancient civilization, vast urban centers or extensive road networks, even if eroded to their foundations, could appear as anomalous linear or geometric patterns in ancient bedrock or sedimentary layers. The materials used, such as artificially fired clay bricks or unique forms of concrete, if preserved, would be highly distinctive. The sheer volume of material moved for major infrastructure projects, like the ancient Roman roads, which stretched for tens of thousands of kilometers and involved massive cuts and fills, would leave behind long-term erosion patterns or distinct, compacted subsurface layers. Dams and water management systems further demonstrate geological impact. The construction of massive dams creates artificial lakes, fundamentally altering hydrological cycles and sedimentation patterns in rivers. Over geological time, these artificial reservoirs would fill with sediment, creating distinct, unusually deep or rapid sediment deposits compared to natural riverine environments. Ancient canals, like those built in Mesopotamia or by the Mayans, involve significant earth moving to channel water. Even if filled in, their linear depressions or distinct sediment fills might be detectable in ancient landscapes. The cumulative effect of these activities can be seen in changes to global sediment cycles, extensive deforestation for timber or agriculture, often linked to civilization, accelerates soil erosion. This leads to increased sediment loads in rivers, which then deposit more sediment in deltas and coastal areas. Over millions of years, this could translate to unusually thick or rapidly deposited sedimentary layers in specific geological periods, indicating widespread land disturbance. While natural events like volcanic eruptions or ice ages also impact sedimentation, the pattern and material composition of civilization-induced sedimentation would likely be distinct. For these digging and building marks to persist over deep time, they must be either incredibly robust or deeply buried. The forces of plate tectonics, erosion, and metamorphism are relentless. Surface structures are quickly worn away. However, deep mines or large-scale constructions that become quickly buried by sediment stand a better chance. For example, a vast ancient mine that collapsed and filled with unique sediment could form a distinct anomaly in a geological cross-section. Similarly, a mega-city built on a stable continental craton, subsequently buried by millions of years of sediment, might leave a discernible, non-natural layer of material in drill cores or exposed rock formations. The key is scale, durability of materials, and favorable burial conditions. The distinctness of these geological scars, particularly their non-natural geometry. Chemical composition or unusual depositional patterns would be the primary indicators of a past technological civilization. A technologically advanced civilization, by its very existence, profoundly alters its planet's environment and climate. These alterations, if significant and sustained, could leave behind geological or atmospheric fingerprints visible over millions of years, serving as potential techno-signatures of a pre-human society. The scale of modern human impact provides a powerful analogy for considering what such ancient modifications might look like. One of the most impactful ways a civilization changes its planet is by altering the composition of the atmosphere, particularly through the release of greenhouse gases. The burning of fossil fuels, coal, oil, and natural gas for energy, transportation, and industry releases vast quantities of carbon dioxide into the atmosphere. This gas traps heat, leading to a warming of the global climate. For instance, since the Industrial Revolution in the late 18th century, human activities have increased atmospheric carbon dioxide concentrations by more than 50%. Such a large and rapid increase, especially if sustained over thousands of years by an ancient civilization, would leave a distinct signature in the geological record. This signature could be detected in ice cores, which trap ancient air bubbles, revealing past atmospheric compositions. It could also be found in ocean sediments, where changes in ocean chemistry, such as acidification, would be recorded in the shells of marine organisms. Even in ancient soil layers, the isotopic ratios of carbon could reveal a period of widespread burning of biologically derived carbon, which is distinct from natural carbon cycles such as volcanic outgassing. Beyond carbon dioxide, other industrial gases could also leave their mark. Methane, a potent greenhouse gas, is released from agriculture, waste, and fossil fuel extraction. Nitrous oxide, another greenhouse gas, comes from industrial processes and agriculture. A sophisticated civilization might also produce novel, synthetic chemicals like chlorofluorocarbons or other long-lived industrial compounds that do not naturally occur. If released in sufficient quantities, these compounds or their breakdown products could persist in geological deposits or leave distinct chemical residues that are anomalous in the natural record. The presence of such unique chemical signatures would be a strong indicator of non-natural industrial processes. Changes to ocean chemistry are another significant planetary alteration. As atmospheric carbon dioxide increases, more of it dissolves into the ocean, forming carbonic acid. This process, known as ocean acidification, lowers the pH of seawater, making it more acidic. Ocean acidification impacts marine life, especially organisms that build shells or skeletons from calcium carbonate, such as corals and many plankton species. Evidence of widespread ocean acidification in the geological past, perhaps indicated by layers of poorly formed or dissolved calcium carbonate shells in marine sediments, could suggest an ancient period of intense atmospheric carbon dioxide levels caused by a prior civilization. Furthermore, industrial runoff and waste disposal directly into oceans could lead to elevated concentrations of heavy metals, persistent organic pollutants, or unique isotopes in deep-sea sediments, forming distinct pollution layers. On the land surface, civilization causes dramatic changes that can affect global climate. Large-scale deforestation, for example, alters the Earth's albedo and hydrological cycles. Forests are dark and absorb sunlight, while cleared land can be lighter and reflect more. Loss of forests also reduces evapotranspiration, impacting regional rainfall patterns. Evidence of widespread, rapid deforestation in the geological past might be found in fossil pollen records, which would show an abrupt shift from forest species to grass or scrub species. Increased soil erosion following deforestation would also lead to distinct layers of sediment accumulation in river deltas and coastal regions. Conversely, large-scale irrigation or the creation of vast artificial lakes could significantly alter regional moisture levels and temperatures, influencing local climate for extended periods. The sedimentary deposits of such artificial water bodies would look distinct from naturally formed lakes. A civilization's activities might even trigger or exacerbate large-scale biological events. Intensive agriculture or resource extraction could lead to widespread habitat destruction, potentially driving numerous species to extinction. While mass extinctions have occurred naturally throughout Earth's history, one caused by a civilization would likely have a distinct pattern, perhaps affecting a specific range of taxa or occurring at an unusually rapid rate. Such an event would be recorded in the fossil record as a sharp decline in biodiversity or the disappearance of certain fossil groups, potentially correlated with unusual chemical or atmospheric anomalies. The widespread introduction of non-native species through global transportation, a common feature of human civilization, could also leave a discernible imprint in ancient ecosystems if those introduced species flourished and were preserved in the fossil record far from their natural range. For any of these planetary changes to be detectable over geological time scales, they would need to be both intense and sustained. Natural processes, such as volcanic eruptions or variations in Earth's orbit, also cause significant climate fluctuations. Therefore, a civilization's fingerprint would need to be uniquely strong, rapid, or exhibit chemical characteristics that are unmistakably artificial. The detection would likely rely on finding multiple lines of evidence, atmospheric gas anomalies, ocean chemistry shifts, and land surface alterations that all point to a concerted, non-natural influence on the planet. The duration of this impact would also be critical. Transient events would be easily erased, but a sustained planet-altering presence lasting for thousands or even tens of thousands of years would have a far greater chance of leaving a long-term detectable geological or atmospheric imprint. The Great Filter is a concept that directly addresses one of the most profound questions in science. Where is everybody? This question, famously posed by the physicist Enrico Fermi, refers to the apparent contradiction between the high probability of extraterrestrial intelligent life existing in the vast universe and the lack of any observable evidence for it. The universe contains billions of galaxies, each with hundreds of billions of stars, many of which are known to host planets, including Earth-like worlds. Given these immense numbers, it seems statistically probable that life, and even intelligent life, should be common. Yet, we have detected no signals, no artifacts, and no signs of other civilizations. The Great Filter attempts to explain this silence. It proposes that there is some significant barrier, or bottleneck, in the evolutionary path from the very beginning of life to a widespread, observable, spacefaring civilization. This barrier prevents most, if not all, life from reaching that advanced stage, making intelligent, technological civilizations extremely rare. The filter could be a single, incredibly difficult step, or it could be a series of very challenging steps that cumulatively make the journey almost impossible. Scientists and thinkers have speculated about where this filter might lie along the long path from abiogenesis to interstellar colonization. The possibilities can broadly be categorized into filters that lie in our past, meaning humanity has already passed them, and filters that lie in our future, meaning they are challenges we have yet to face. Filters in our past suggest that the development of intelligent, technological life is far rarer than we might intuitively think. One such early filter could be the sheer difficulty of life originating from non-life at all. Abiogenesis remains one of the greatest unsolved mysteries in science, requiring complex chemical reactions under very specific conditions. If this step is exceedingly rare, it would mean that even on billions of planets, life itself might be an infrequent occurrence. Another potential early filter is the evolution of complex eukaryotic cells from simpler prokaryotic cells. This was a monumental leap in biological complexity that occurred only once in Earth's history, approximately 2 billion years ago. If this transition is highly unlikely, then most planets with simple life might never develop multicellular organisms. The evolution of multicellular life from eukaryotic cells, the Cambrian explosion 541 million years ago, leading to diverse, complex animals, or even the sustained stability of a planet's environment over billions of years needed for a complex life to evolve, are all considered potential past filters. If any of these steps are incredibly difficult, then humanity has, by luck or unique circumstance, already overcome them. Conversely, the Great Filter might lie in our future. This would be a more sobering prospect, implying that most civilizations, once they reach a certain level of technological advancement, inevitably encounter a barrier they cannot overcome, leading to their demise or stagnation before they can become observable across interstellar distances. One common, proposed future filter is self-destruction. This could manifest as global nuclear war, an ecological catastrophe caused by pollution or climate change, the uncontrollable development of artificial intelligence, or widespread biological warfare. The idea here is that the very technology that allows a civilization to advance also provides the means for its own destruction. Another potential future filter is resource depletion. A civilization might deplete its planetary resources to such an extent that it cannot sustain its technological growth or achieve space travel. Other future filters could include technological stagnation, where a civilization simply stops advancing, or the inability to overcome planetary crises such as asteroid impacts, supervolcano eruptions, or runaway climate change. Finally, the filter might be the inherent difficulty of interstellar travel itself, meaning that even if civilizations don't destroy themselves, they may simply be unable to spread beyond their home star system in a detectable way. The Silurian hypothesis, which suggests the possibility of a prior technological civilization on Earth, directly interacts with the Great Filter concept. If the Silurian hypothesis were proven true, meaning a sophisticated civilization rose and fell millions of years before humanity, it would place the Great Filter squarely in our past. This scenario would imply that the evolution of technological civilizations is not as rare as the Fermi paradox suggests, but rather that their long-term survival is the difficult part. The ancient civilization on Earth would have encountered and succumbed to a filter event. This could have been a catastrophic climate change, resource collapse, a cataclysmic natural disaster, or even self-destruction through warfare or unchecked technology. If this is the case, then humanity itself might be approaching the same filter that extinguished our ancient predecessors. The Silurian civilization would serve as a chilling warning, demonstrating a common pathway to extinction for advanced technological societies. Alternatively, if an ancient Earth civilization merely left the planet or transformed into a non-detectable form, then the Silurian hypothesis would not necessarily represent a filter in the destructive sense. Instead, it might suggest alternative trajectories for advanced civilizations, where they simply vanish from planetary detectability, perhaps ascending to higher planes of existence or colonizing other star systems without leaving behind observable physical traces. However, the more commonly discussed implication of the Silurian hypothesis within the Great Filter framework is that of a past, devastating bottleneck. The concept of the Great Filter forces us to confront the fragility of intelligent life and the potential challenges that lie ahead. If the filter is indeed behind us, humanity is extraordinarily rare, and perhaps unique. If it is in our future, then our current technological trajectory might be leading us to a common, unavoidable doom. The Silurian hypothesis offers a unique opportunity to search for evidence of such a filter within our own planet's deep history, potentially shedding light on the ultimate fate of intelligent life in the cosmos. When we ponder the existence of a pre-human civilization on Earth, our minds often jump to images mirroring our own technological advancements, towering cities, intricate machinery, vast communication networks, and evidence of industrial might. This perspective, however, is deeply rooted in our human-centric understanding of civilization and progress. It is entirely possible that a truly ancient civilization might have developed along paths so fundamentally different from our own that their traces would be subtle, integrated, and easily mistaken for natural phenomena, thus escaping our current methods of detection. This challenges us to consider what a simple civilization might entail, not simple in terms of intelligence, but in terms of its technological signature. Our current civilization is defined by its ability to harness vast amounts of energy and manipulate matter on a grand scale. We build with steel and concrete, power our lives with fossil fuels and nuclear fission, and communicate across continents with electromagnetic waves. These activities leave distinct techno-signatures in the geological record layers of plastic, concrete, refined metals, altered atmospheric chemistry, and specific isotopic anomalies from industrial processes. We are, in essence, creating a unique geological epoch, the Anthropocene, characterized by our technological impact. But what if a civilization did not follow this trajectory, or only did so for a relatively brief period? Imagine a civilization that focused its intelligence not on manipulating brute, physical forces, but on understanding and controlling biological and ecological systems. Instead of building metal cities, they might have cultivated vast, living architectural structures using genetically engineered plants and fungi. Their infrastructure could have been entirely biological, perhaps evolving living transportation networks, self-repairing organic dwellings, or bioluminescent communication systems. Such a civilization would possess an extremely sophisticated understanding of biology, chemistry, genetics, and ecology, far beyond our current capabilities. Their technology would be biological engineering on a planetary scale. The traces left by such a biological civilization would be profoundly different from our industrial output. Instead of persistent plastics, we might find unusual fossilized megaflora or megafauna that exhibit non-natural design patterns, indicative of deliberate genetic modification over millions of years. Perhaps entire ecosystems would show signs of intelligent management, with species exhibiting symbiotic relationships or highly efficient resource cycling not found in natural evolution. The chemical signatures left behind might involve unique organic compounds, specific metabolic byproducts, or altered isotopic ratios related to biological rather than industrial processes. For instance, they might have perfected carbon sequestration through bioengineering, leaving a peculiar carbon signature in ancient sediments. Detecting these would require a shift in our scientific focus, moving beyond purely mechanical signatures to look for sophisticated biological anomalies. Furthermore, a pre-human civilization might have developed in environments that inherently limit certain types of technological expansion. Consider a civilization that evolved entirely within the Earth's oceans or deep underground. An aquatic civilization, for instance, might never discover fire or metallurgy in the way surface-dwelling beings do. Their technology would be based on pressure, acoustics, bioluminescence, and the unique properties of water. They might construct vast cities from biomineralized structures, use complex forms of sonar for communication and sensing, or develop advanced methods of cultivating marine life for food and resources. Their waste would be organic and would likely be recycled by the ocean's ecosystems, leaving minimal, non-biodegradable traces. Any physical structures would need to withstand immense pressures and corrosive environments, making their detection challenging even if they were durable. Signs might include unusual patterns of seismic activity caused by deep-sea engineering, or very specific chemical alterations in deep ocean sediments. Similarly, a subterranean civilization might focus on geological engineering, adapting to life within caves or constructing vast underground networks. Their technology might involve advanced forms of geothermal energy, specialized drilling techniques, or unique methods of resource extraction that leave minimal surface impact. Their architecture might blend seamlessly with natural rock formations, carved and shaped rather than built from separate components. Detection would require deep drilling, advanced seismic imaging, or the discovery of unusual mineral veins or geological anomalies far beneath the surface, not attributable to natural tectonic or volcanic activity. The concept of a simple civilization also forces us to consider the time frame of their impact. Perhaps a civilization reached a technological peak that was brief, existing for only a few thousand or tens of thousands of years, a mere blink in geological time. Our own industrial age is barely 300 years old, yet its global impact is profound. If an ancient civilization had a similar brief burst of intense technological activity, followed by a decline or self-destruction, its most distinctive techno-signatures might be confined to very thin, specific geological layers. These layers could easily be missed, eroded, or subducted over millions of years, leaving behind only the most resilient or widely dispersed traces. Even if an ancient civilization had some level of technology, they might have achieved a sustainable or steady-state existence, where their impact on the planet was minimized. Perhaps they learned to live in harmony with Earth's natural cycles, reducing waste, recycling materials efficiently, and drawing energy from renewable sources without significant environmental disruption. Such a civilization, having overcome the initial resource-intensive phases of development, might leave behind fewer detectable, Anthropocene-like markers. Their long-term presence might be marked by subtle, persistent anomalies rather than dramatic, easily recognized changes. The challenge, therefore, is not just to look for signs of technology as we understand it, but to broaden our definition of what constitutes a civilization's mark. We must develop new ways to interpret geological, chemical, and biological data, searching for patterns that are too complex, too ordered, or too anomalous to be explained by natural processes, yet do not fit our preconceived notions of industrial or mechanical technology. This requires an open mind and a willingness to explore possibilities beyond our own limited historical experience. The Fermi paradox is one of the most compelling and perplexing questions in science. If the universe is so vast and potentially teeming with life, where is everybody? The cosmos contains billions of galaxies, each with hundreds of billions of stars, many of which are known to host planets, including Earth-sized worlds in habitable zones. Given that life arose relatively early on Earth and evolved into intelligence, it seems statistically plausible that other intelligent technological civilizations should be common and long-lived enough to have either visited us, left behind detectable signals, or constructed vast engineering projects visible across interstellar distances. Yet, we observe a profound silence. This glaring contradiction between the high probability of extraterrestrial intelligence and the lack of observational evidence is the essence of the Fermi paradox. Many proposed resolutions to the Fermi paradox exist, often categorized by what is known as the Great Filter. The Great Filter suggests there is some extremely difficult step in the evolution of life from its simplest forms to a civilization capable of interstellar communication or travel. This filter could be in our past, meaning intelligence or complex life is exceedingly rare, or it could be in our future, meaning advanced civilizations tend to destroy themselves or face insurmountable barriers to expansion. The Silurian hypothesis offers a unique and intriguing twist to this paradox, proposing a resolution that is both local and deeply temporal. Perhaps they were here, but long before us, right on Earth. The core of the Silurian hypothesis is the idea that a technologically advanced civilization could have arisen on Earth hundreds of millions of years ago, flourished, and then vanished, leaving behind few, if any, discernible traces that we currently recognize. If such a civilization existed, its physical structures would have been obliterated by the relentless geological processes of plate tectonics, erosion, and volcanism over immense timescales. Its radio signals would have long dissipated into the cosmic background. Its most durable waste products might be buried deep beneath subducted crust or so chemically altered as to be unrecognizable. This concept provides a compelling local answer to the Fermi paradox. Instead of searching across light years for distant signals or evidence of alien megastructures, the Silurian hypothesis suggests we might simply be looking in the wrong direction, or rather, the wrong time. If a civilization on Earth rose and fell, say, 60 million years ago, its existence would offer a powerful explanation for the cosmic silence from this specific planet. We would not detect it today because it is gone, and its marks are nearly erased. This shifts the focus from "why haven't they come here" to "what if they already were here, just not in our time?" The implications of the Silurian hypothesis for the Great Filter concept are profound. If a technological civilization did indeed exist on Earth in the deep past, it means that the filter allowing life to evolve to intelligence and technology has already been passed on this planet. This is a crucial point. If the filter is in our past, then it suggests that either the conditions for complex life are incredibly rare, or the step from simple life to intelligence, or from intelligence to technology, is extremely improbable. However, If a Silurian-like civilization indeed existed, it would imply that these steps are not insurmountably difficult on Earth-like planets. Instead, the filter might then lie in the longevity of such civilizations, or their ability to leave detectable, long-lasting marks. Perhaps technological civilizations, once they arise, tend to be short-lived due to self-destruction, or they develop in ways that minimize their long-term geological footprint. If the Silurian civilization destroyed itself, or simply faded away without leaving indelible techno signatures, it suggests that the longevity of technological species might be a significant barrier to their widespread detectability across the universe. This would be a pessimistic outlook for our own future. Alternatively, the Silurian hypothesis might imply that technological civilizations inherently manage to limit their long-term environmental impact. If they achieve true sustainability or transition to non-physical forms of existence, their detectable traces might diminish over time. This would suggest that the reason we don't see evidence of other civilizations is not necessarily because they self-destruct, but because they become invisible or less impactful on their planetary environments over geological timescales. Such a scenario would mean that the Great Filter is about the detectability of advanced civilizations, rather than their sheer existence. While the Silurian hypothesis offers a compelling local resolution to the Fermi paradox, it does not fully explain why we don't see evidence of other civilizations in the rest of the galaxy. If Earth could host one ancient civilization, it stands to reason that countless other planets in the Milky Way could have done the same. The lack of galactic-scale techno-signatures, like Dyson spheres or interstellar probes, still remains an unanswered question. However, the Silurian hypothesis encourages us to consider that our search for extraterrestrial intelligence might be too narrow. Focusing solely on contemporaneous, outward-looking signals, it nudges us to consider that intelligent life might rise and fall, leaving behind only the most subtle whispers in the deep time of its home planet. A reminder that the universe's answers might be found closer than we think, but hidden by the relentless march of geological time. The paradox remains, but the Silurian hypothesis offers one fascinating, Earth-bound possibility for its resolution, making the Great Silence a little less mysterious for our own planet's history. The Earth's crust is a vast archive, a layered record of billions of years of geological and biological history. Within these ancient rock formations, scientists meticulously search for clues about past environments, climate changes, and the evolution of life. When pondering the existence of a pre-human civilization, the challenge lies in identifying anomalies within this natural record that might hint at intelligent activity rather than mere geological or biological processes. Most of what we find in rocks is entirely natural, but understanding these natural formations is crucial to recognizing anything that is genuinely out of place. Natural rock formations can sometimes deceive the casual observer, appearing almost artificial. For example, columnar jointing, a common feature in volcanic rocks, occurs when lava cools and contracts, forming geometric columns that can look like enormous, perfectly fitted paving stones. Famous examples include the Giant's Causeway in Ireland or Devil's Tower in Wyoming. Similarly, concretions are hard, compact masses of sedimentary rock that form inside existing layers. They can take on remarkably spherical, disc-like, or even anthropomorphic shapes, often mistaken for ancient artifacts, such as the Klerksdorp spheres found in South Africa, which are merely natural iron concretions. The key differentiator is that these forms arise from predictable physical and chemical processes, lacking any true complexity, function, or material composition inconsistent with their natural formation. To find genuine clues in rocks suggesting a past civilization, we would need to look for features that cannot be explained by known natural processes and instead point towards deliberate, intelligent manipulation. One such category would be unusual geometrical patterns on a large scale. While crystals naturally form geometric shapes, And erosion can create intriguing patterns, a vast, systematic arrangement of perfectly straight lines, precise circles, squares, or complex fractal patterns embedded within ancient rock strata that defy geological explanation could be a compelling clue. Imagine finding evidence of immense, highly regular excavations or foundational structures extending for many kilometers, at angles and with a precision unachievable by natural forces. Another significant category involves layering anomalies and unusual material compositions. Geological layers typically follow predictable patterns of sedimentation, compaction, and diagenesis. An anomaly would be a distinct stratum that contains materials or chemicals profoundly out of place within the natural sequence. This might include a layer comprised largely of refined metals or alloys that are not formed through natural processes. The discovery of a widespread, consistent layer of highly processed industrial waste, such as specific types of glass, ceramics, or synthetic polymers, embedded in rock strata millions of years old, would be a strong indicator. These materials would have compositions and structures that are definitively not found in natural geological formations. Fossilized technology would be an undeniable clue. Though incredibly rare due to the fragility of most manufactured goods compared to the immense pressures and transformations rocks undergo, this would involve finding actual imprints or petrified remains of complex, non-biological, technologically manufactured items within ancient rock. For instance, a clear, fossilized impression of a gear, a circuit board, or an engine part, complete with intricate internal structures and precise symmetries that could only be artificial, would be a profound discovery. The challenge is that organic components degrade and metals corrode. What might survive are impressions in fine sediments that later hardened into rock or highly durable, non-corroding synthetic materials that could persist for eons. The Koso artifact, an alleged spark plug found within a geode, is a popular example of such a claim, though it has largely been explained as a modern artifact that fell into a geological crack. The key to verification would be irrefutable evidence of its direct incorporation during the formation of the ancient rock, not later. Accidental inclusion. Chemical and isotopic anomalies offer a more subtle but potentially robust line of evidence for detecting ancient techno-signatures. A technologically advanced civilization would likely leave behind a distinct chemical imprint in its environment. This might appear as elevated concentrations of certain elements, such as rare earth metals or platinum group elements in ancient rock layers where natural geological processes cannot explain their presence. Additionally, unique isotopic ratios could signal past industrial activity, especially from nuclear energy or fossil fuel combustion, leaving behind altered signatures in uranium, plutonium, xenon, strontium, or carbon isotopes, preserved in ancient sediments. Finally, large-scale geological modifications that are too systematic and vast to be natural could also serve as clues. This might include evidence of immense, ancient mining operations, vast, precise excavations, or even subtle, persistent changes in the Earth's magnetic field or seismic patterns. If a civilization engaged in deep subsurface engineering, while natural processes create features like canyons or river deltas, the discovery of highly regular, non-random patterns of earth-moving or underground structures, particularly those exhibiting signs of complex engineering principles over vast distances, would be truly anomalous. The search for these clues in rocks requires both an understanding of the Earth's natural processes and an open mind to patterns that deviate from them in ways that only intelligence could create. The Earth's crust is a complex tapestry of elements, distributed in specific concentrations and ratios determined by billions of years of natural geological and astrophysical processes from the formation of the planet to volcanic activity, sedimentation, and the slow dance of plate tectonics. Elements are constantly recycled and rearranged, Understanding these natural patterns is the baseline for discerning any unusual concentrations or ratios of elements in ancient rock layers that might hint at an industrial past not linked to known human activity. When a civilization engages in large-scale technological processes, it fundamentally alters these natural elemental balances, potentially leaving a detectable chemical fingerprint. One of the most direct ways a technologically advanced society impacts elemental distribution is through mining and smelting. Earth's crust contains elements in varying abundances. Some elements, like iron, aluminum, and silicon, are very common. Others, like gold, platinum, or rare earth elements, are scarce and naturally occur in concentrated deposits only under specific geological conditions. A civilization requires these elements for tools, structures, and technology. The act of mining extracts these elements from their natural geological context, concentrating them in specific locations or distributing them broadly as waste. Smelting, the process of extracting a metal from its ore using heat, involves chemical reactions that often release other elements as byproducts into the atmosphere, soil, or water. For example, ancient smelting of copper or lead could release arsenic, antimony, or other heavy metals, which might then settle in nearby sediments or be carried by winds and waters to distant locations, forming anomalous concentrations in layers of rock that correspond to the period of that activity. If an ancient civilization engaged in such practices on a significant scale, layers of rock or sediment from that era might show unnaturally high levels of these specific industrial byproducts, far exceeding natural background levels. Fossil fuel combustion is another major source of elemental anomalies. Coal and oil, formed over millions of years from ancient organic matter, contain not only carbon and hydrogen, but also trace amounts of various other elements, including sulfur, mercury, lead, arsenic, vanadium, and nickel. When these fuels are burned for energy, these trace elements are released into the atmosphere as gases or fine particulate matter. They can then be dispersed globally by atmospheric currents and eventually settle out, becoming incorporated into accumulating sediments, ice cores, or even tree rings. For example, scientists have detected spikes in lead concentrations in Arctic ice cores dating back to the Roman Empire, attributed to lead smelting activities during that era, and much larger spikes from the 20th century's widespread use of leaded gasoline. If a pre-human civilization engaged in industrial-scale burning of fossil fuels, similarly distinctive layers of trace elements could be preserved in geological archives, representing a persistent signature of their energy consumption. Chemical manufacturing processes introduce another type of elemental clue: the production of various industrial chemicals, such as fertilizers, plastics, dyes, or specialized alloys, often involves the manipulation of specific elements in ways not found in nature. For example, large-scale production of nitrogen-based fertilizers could alter nitrogen isotope ratios in a way that is distinct from natural biological cycles. The widespread creation of synthetic compounds, even if they degrade over long periods, might leave behind persistent residues or unique chemical breakdown products that are not naturally occurring. Even the simple enrichment or depletion of common elements in specific layers, when linked to highly complex, non-natural chemical forms, could be a sign of advanced industrial activity. Perhaps the most definitive elemental signature of an advanced technological civilization would come from nuclear activities, nuclear fission. The process of splitting atomic nuclei results in the creation of unique, unstable isotopes that are not found in significant quantities in nature. Elements like cesium-137 or strontium-90, while decaying over specific half-lives, could leave behind distinct isotopic ratios of their stable decay products or direct traces if the half-life is long enough for the geological period in question. More fundamentally, the widespread use of uranium or other radioactive elements in nuclear reactors would alter the natural isotopic ratios of these elements, creating a fingerprint of nuclear fuel processing. For instance, the ratio of uranium-235 to uranium-238 would be measurably different from natural ore. Such anomalies, if detected in ancient rock layers, would be exceedingly difficult to explain by natural geological processes and would strongly point towards intelligent manipulation of atomic nuclei. Finally, the increasing reliance of modern technology on rare earth elements could also leave a future signature. These elements, such as neodymium, dysprosium, and europium, are crucial components in electronics, magnets, and green technologies. Their widespread extraction and processing could lead to their anomalous concentration in specific geological or sedimentary layers, marking a period of intense technological activity. The detection of these elemental clues in ancient rock layers would require sophisticated analytical techniques, such as mass spectrometry, X-ray fluorescence, and neutron activation analysis, applied to geological samples obtained from boreholes, deep ocean sediment cores, or exposed rock faces. The key is to look for concentrations, combinations, or isotopic ratios that deviate significantly from what is expected from known natural processes. The challenge remains immense, as natural geological events like meteor impacts, hydrothermal vents, or unique mineralization processes can also cause localized elemental anomalies. Therefore, any alleged techno-signature in elements would need to be robust, widespread, and unequivocally inexplicable by any natural means, ideally supported by multiple independent lines of chemical and geological evidence to stand as a credible indicator of a long-lost civilization. Throughout history, and especially since the rise of modern archaeology and geology, there have been numerous reports of out-of-place artifacts, or OPARTs. These are objects or structures discovered in geological or archaeological contexts that seem to contradict the established timeline of human evolution or technological development. The term implies that these finds appear to be too advanced or sophisticated for the period from which they are thought to originate, leading to questions about their true age or the conventional understanding of Earth's history. While these finds often capture the public imagination and fuel speculation about ancient, lost civilizations or even extraterrestrial visitors, they are almost universally explained by mainstream science through more conventional means. One of the most frequently cited examples of an OOP art is the Kozo artifact, discovered in 1961 by a team of rockhounders in California. It was found encased within what appeared to be a geode. The object inside bore a striking resemblance to a modern spark plug, complete with a ceramic insulator and a metallic core. The surrounding geode was estimated by some proponents to be around 500,000 years old, a time long before humans were thought to have developed such technology. This perceived discrepancy made the Kozo artifact a popular item in discussions about ancient technology. Another famous case is the Dorchester pot. In 1852, during blasting operations in Dorchester, Massachusetts, a metallic pot was reportedly found embedded in solid rock that was supposedly hundreds of millions of years old, described as pre-Adamic in an account from the Scientific American Journal of that time. The bell-shaped pot, reportedly made of an unknown metal alloy, had intricate floral designs. Its alleged age, dating to a period before complex life forms, made its existence seem impossible according to conventional understanding. The King Goody hammer is another well-known example, discovered in 1844 by quarry workers in Scotland. This hammer, with its wooden handle, was reportedly found encased within solid Carboniferous-era sandstone, estimated to be around 300 million years old. The apparent modernity of the hammer, combined with the extreme age of the rock, made it seem like a clear indication of advanced technology existing far before humans. In China, The Baigong pipes have gained notoriety. Discovered in 2002 near Mount Baigong in Qinghai province. These pipes are said to be metallic and arranged in intricate patterns within a cave system. Some of the pipes reportedly extend into a salt lake. Geologists estimate the age of the surrounding rock formations to be hundreds of millions of years old. The seemingly manufactured nature of the pipes in such an ancient context has led to speculation about an ancient, unknown civilization. More historical examples include discoveries from the 19th century that puzzled observers. The South African grooved spheres, found in pyrophyllite deposits near Ottosdal, South Africa, are small, metallic-looking spheres, often described as having precisely cut grooves around their circumference. These deposits are estimated to be incredibly ancient, around 2.8 billion years old. Their uniformity and apparent design have led some to suggest an artificial origin. There are also instances from archaeological sites where items, while clearly ancient, appear to have characteristics that some observers found strangely modern. Heinrich Schliemann, the discoverer of ancient Troy in the late 19th century, found a peculiar ceramic jar with what he described as an owl-faced design. While certainly ancient, some interpretations have stretched its resemblance to suggest a kind of proto-industrial aesthetic, though this remains an outlier view among archaeologists. The existence of alleged Venezuelan gold thread found in 250 million year old coal has also been reported, implying highly advanced metallurgical skills in a vastly ancient period. These finds, whether a supposed spark plug in ancient rock, a metallic pot from the distant past, or a hammer embedded in 300 million year old stone, are strange because they appear to defy the well-established scientific understanding of Earth's chronology and the evolutionary timeline of life and intelligence. They present a perceived challenge to the conventional narrative that humans, as we know them, and our technology, are relatively very recent developments in the planet's history. This apparent conflict makes them inherently intriguing and compelling to those who seek evidence for alternative histories or forgotten civilizations, fueling widespread popular discussion and speculation. The very idea of an object that should not exist in a particular time frame is what gives these parts their enduring fascination and their role in the popular imagination. The fascination surrounding out-of-place artifacts, or parts, stems from their apparent contradiction with established scientific timelines. However, when these claims are subjected to rigorous scientific scrutiny, they almost invariably find conventional explanations that do not require rethinking the history of Earth or human civilization. The debate around parts highlights fundamental differences in how evidence is gathered, analyzed, and accepted in scientific communities versus how it is often presented in popular culture. Central to the scientific rejection of most part claims is the principle of the scientific method and the requirement for verifiable evidence. For any extraordinary claim, extraordinary evidence is needed, and that evidence must be gathered and presented in a way that allows for independent verification and peer review. This typically involves proper archaeological excavation, meticulous geological dating of the surrounding context, and detailed analysis of the artifact itself by experts in relevant fields. Most art claims fall short of these standards. Often, the objects are found by amateurs without careful documentation of their exact stratigraphic position. This lack of reliable provenance makes it impossible to confirm the true age or context of the find. One of the most common explanations for alleged arts is the misidentification or misinterpretation of natural geological formations. Nature can create remarkably intricate and symmetrical forms that might appear artificial to an untrained eye. For example, concretions are hard, compact masses of rock formed by the precipitation of mineral cement within sediment. They can sometimes assume highly regular or even spherical shapes with distinct lines or grooves, leading to their misidentification as manufactured objects. The South African grooved spheres, described in the previous section as small, metallic spheres with grooves, are widely accepted by geologists as natural concretions, specifically limonite concretions formed through geological processes where the grooves are a natural pattern of deposition or erosion, not machine tooling. Similarly, the Coso artifact, the spark plug-like object, was thoroughly examined by geologists and researchers who concluded that it was a modern spark plug from the 1920s, encased not in a geode, but in a concretion of rapidly hardening clay and iron oxides. The formation process could have created the hard casing around the spark plug relatively quickly, leading to the mistaken impression of extreme antiquity. Another frequent explanation for OOP arts is contamination or intrusion. This occurs when a modern object finds its way into an older geological layer through natural processes like erosion, cracks in rock, animal burrowing, or human activities like mining, drilling, or grave digging. For instance, the King Goody hammer, reportedly found in Carboniferous rock, is often explained as a modern hammer that fell into an old mining fissure. Mineral-rich water then seeped into the fissure, solidifying around the hammer over a relatively short geological time frame, creating the impression that it was originally embedded in ancient, solid rock. The wood of the handle, if it were truly 300 million years old, would have turned to coal or been entirely mineralized, which was not the case with the hammer found. Hoaxes and frauds also account for a small but significant number of OOP art claims. While less common in modern times due to increased scientific scrutiny, historical examples exist where objects were deliberately fabricated or misrepresented to deceive. Even without outright fraud, a lack of scientific rigor in initial reports can lead to persistent misconceptions. The Dorchester pot is a case where the original report lacked the kind of detailed geological analysis that would be expected today, and subsequent attempts to locate and properly study the object have been unsuccessful. Its story largely rests on a 19th century anecdote, the phenomenon of pareidolia, the human tendency to perceive meaningful images or patterns in random or ambiguous visual stimuli, also plays a role. People might see faces in clouds or shapes in abstract art. Similarly, natural rock formations, erosion patterns, or mineral deposits can, to the eager observer, appear to be tools, carvings, or even complex machinery. The Baigong pipes in China, while intriguing, have been largely interpreted by geologists as natural formations, possibly related to geological fractures or fossilized tree roots where mineral deposition has created pipe-like structures. The presence of natural iron-rich minerals in the area supports this natural explanation. The scientific consensus regarding OOP arts is overwhelmingly skeptical. Mainstream geologists, archaeologists, and paleontologists acknowledge the possibility of unique discoveries, but require strict adherence to scientific methodology. The overwhelming body of evidence from millions of verified archaeological sites and geological formations consistently supports the established timelines for the evolution of life and the development of human technology. No OOP art has ever been subjected to multiple, independent, peer-reviewed studies that confirm an unequivocally anomalous origin that defies natural explanation. The vast number of non-anomalous findings constantly reinforces the current scientific understanding. The debate persists not due to strong scientific counter-evidence from OOP arts, but often because of public fascination with mystery, a desire to challenge established narratives, and sometimes a misunderstanding of geological processes or the nature of scientific proof. While the Silurian hypothesis is a scientific thought experiment about what kinds of evidence might theoretically survive from an ancient civilization, OOP arts are specific, alleged findings that almost always have natural or prosaic explanations upon closer examination. They serve as cautionary tales about the importance of rigorous scientific methodology and critical thinking when faced with extraordinary claims. To ponder the possibility of an ancient civilization existing on Earth long before our own, one must first confront the truly immense scale of geological time. Our planet is approximately 4.54 billion years old, a number so vast it challenges human comprehension. To put this into perspective, if the entire history of the Earth were condensed into a single calendar year, with the Big Bang occurring on January 1st, modern humans would appear only in the last few minutes of December 31st, and all of recorded human history would occupy just the final seconds. This profound depth of time means that there have been billions of years, vast stretches of planetary evolution, during which the conditions for complex life, and potentially even intelligent civilizations, could have arisen and vanished long before the emergence of Homo sapiens. The age of Earth is not a guess, it is determined through precise scientific methods, primarily radiometric dating. Scientists analyze meteorites, which are remnants from the early solar system, and the oldest rocks on Earth, such as zircons found in Western Australia. These analyses reveal that the materials forming our planet solidified about 4.54 billion years ago, the very first eon of Earth's history. The Hadean spans from its formation until roughly 4 billion years ago. During this fiery period, the planet was a molten ball, frequently bombarded by asteroids and comets. The Moon is believed to have formed during this eon, possibly from a giant impact. The atmosphere was a toxic mix, and the surface was too hot and unstable for water to exist in liquid form for long periods. Life as we know it would have been impossible during the Hadean. Following the Hadean came the Archean, lasting from 4 billion to 2.5 billion years ago. As the Earth began to cool, water vapor condensed to form the first oceans, and primitive continental crust started to emerge. Crucially, it was during this eon, around 3.8 billion years ago, that the earliest definitive evidence of life appeared. These were simple, single-celled organisms, prokaryotes like bacteria and archaea, living in the oceans. Their existence was profoundly important, as some of these early life forms began the process of photosynthesis, releasing oxygen into the atmosphere. However, for well over a billion years, life remained microscopic and relatively simple, characterized by microbial mats and bacterial colonies. This was a long stretch where life was present, but not in forms we associate with advanced civilization. The Proterozoic eon extended from 2.5 billion to 541 million years ago. This eon witnessed several pivotal changes. The oxygen produced by early life forms slowly accumulated in the atmosphere, leading to the Great Oxidation Event around 2.4 billion years ago. This event fundamentally changed Earth's chemistry and paved the way for more complex life. Eukaryotic cells, which have a nucleus and other specialized structures, evolved around 2 billion years ago. Later in the Proterozoic, around 600 million years ago, the first true multicellular organisms appeared, known as the Ediacaran biota. These were soft-bodied, often disc-shaped or frond-like creatures. While multicellular, they lacked complex organs, mobility, and hard parts, making them fundamentally different from the complex animals that would follow. Despite these advances, the vast majority of the Proterozoic eon, spanning nearly 2 billion years, was dominated by relatively simple life forms, leaving ample time for evolutionary paths that might have led to other outcomes. The Phanerozoic eon, meaning visible life, began 541 million years ago and continues to the present day. This eon is characterized by the explosion of complex, diverse life forms that left extensive fossil records. It is divided into 3 major eras: the Paleozoic, Mesozoic, and Cenozoic. Each of these eras spans tens to hundreds of millions of years, providing immense stretches of time during which life underwent profound changes, including periods of flourishing and devastating mass extinctions. The Paleozoic era began with the Cambrian explosion, a period of rapid diversification of animal life. This was followed by the emergence of fish, land plants, insects, amphibians, and eventually reptiles. Life colonized the land, and vast forests covered the continent. Towards the end of the Paleozoic, the supercontinent Pangaea formed, and the era culminated in the Permian-Triassic extinction event, the most severe mass extinction in Earth's history, which wiped out over 90% of marine species and 70% of terrestrial vertebrate species. Despite this cataclysm, this era alone lasted for nearly 300 million years, a time frame so vast it could easily contain multiple cycles of a civilization's rise and fall. The Mesozoic era, often called the Age of Dinosaurs, stretched from 252 to 66 million years ago. This was the era when dinosaurs dominated terrestrial ecosystems for over 180 million years. Early mammals and birds also appeared during this time, though they remained relatively small and inconspicuous compared to the towering dinosaurs. The continents continued to drift apart. This era concluded with the Cretaceous Paleogene extinction event, caused by a massive asteroid impact, which led to the demise of the non-avian dinosaurs and many other life forms. Again, this era spanned a colossal 186 million years, providing an enormous temporal canvas. Finally, the Cenozoic era began 66 million years ago and continues to the present. This is the age of mammals. With the dinosaurs gone, mammals diversified rapidly, filling the vacant ecological niches. Primates evolved, and within the last few million years, our own hominid ancestors emerged. Homo sapiens, modern humans, appeared around 300,000 years ago. The agricultural revolution, which marks the transition from nomadic hunter-gatherer societies to settled communities, began only about 10,000 to 12,000 years ago. The first cities arose around 5,500 years ago, and the Industrial Revolution, which truly transformed our global civilization, occurred in the late 18th century, barely 250 years ago. The sheer brevity of human civilization, measured in mere thousands of years, when juxtaposed against the 4.54 billion-year history of Earth, is staggering. There are multiple intervals of tens, hundreds, and even billions of years where complex life existed and evolved. Between the Permian-Triassic extinction and the KPG extinction, there was a gap of approximately 186 million years. Between the KPG extinction and the rise of humans, there was a span of roughly 65 million years. Each of these immense periods provided ample time for evolutionary pathways to unfold, for intelligent species to potentially emerge, develop technology, flourish, and then disappear, perhaps without leaving definitive, readily detectable traces for our current geological and archaeological methods. The vastness of Earth's age implies that our civilization is not necessarily the first, but merely the latest to occupy this planet. The story of life on Earth is one of gradual progression, but it also features moments of astonishing acceleration. One such pivotal moment is the Cambrian explosion, a period approximately 541 million years ago when the diversity of complex animal life on Earth dramatically increased over a relatively short geological time span. Understanding this event is crucial when considering the possibility of earlier, advanced life forms, as it demonstrates that Earth is capable of fostering rapid evolution leading to sophisticated organisms. Before the Cambrian explosion, for billions of years, life on Earth was predominantly simple. For the vast majority of the Archean and Proterozoic eons, microbial life ruled. The earliest undisputed evidence of life dates back about 3.8 billion years, consisting of single-celled prokaryotes like bacteria and archaea. These microscopic organisms slowly transformed Earth's atmosphere and oceans, gradually accumulating oxygen. Later, around 2 billion years ago, eukaryotic cells evolved, possessing a nucleus and other internal structures which allowed for greater complexity. Around 600 million years ago, during the late Proterozoic, the Ediacaran biota appeared. These were the earliest known multicellular organisms, generally soft-bodied, sessile, and often shaped like fronds, discs, or quilts. While they represent a significant step towards multicellularity, they lack the complex organs, active mobility, and hard parts characteristic of most later animals. The world of the Ediacaran period was largely quiet, dominated by these peculiar, often enigmatic forms of life. Then, about 541 million years ago, something profound happened over a period of perhaps only 10 to 20 million years. Most of the major animal phyla, the fundamental blueprints for animal body plans, suddenly appeared in the fossil record. This rapid diversification of complex organisms is what scientists call the Cambrian explosion. Before this event, the fossil record was sparse and dominated by simple forms. After it, the oceans teemed with a bewildering variety of creatures, many of which had bilateral symmetry, distinct heads and tails, specialized organs, and, crucially, hard exoskeletons or shells. Key players in the Cambrian explosion include creatures like trilobites, which were segmented arthropods with hard exoskeletons that crawled on the seafloor. They are one of the most recognizable groups from this period and are abundant in the fossil record. Other remarkable organisms include Anomalocaris, a large, predatory arthropod-like creature with grasping appendages and a circular mouth, and Wiwaxia, a slug-like animal covered in spines and scales. There was also Picaia, a small, worm-like creature that is considered one of the earliest known chordates. A group that eventually includes vertebrates like fish, amphibians, reptiles, birds, and mammals. The variety of body forms and ecological roles that emerged during this short period was astonishing. Scientists propose several contributing factors that likely fueled the Cambrian explosion. One major hypothesis involves a significant increase in atmospheric oxygen levels, which reached a threshold necessary to support the metabolic demands of larger, more active, and more complex animals. This oxygenation allowed for the development of more efficient respiratory systems and larger body sizes. Another factor might have been the evolution of specific genetic tools, such as the Hox genes. These are master control genes that regulate the development of body plans in animals. The duplication and diversification of Hox genes could have provided the genetic flexibility needed for rapid evolutionary experimentation and the creation of diverse body forms. Changes in ocean chemistry also played a role. An increase in the availability of calcium in seawater, possibly due to increased erosion or volcanic activity, might have facilitated the secretion of calcium carbonate for shells and skeletons. The development of hard parts was a revolutionary adaptation. It provided protection against predators, support for larger bodies, and anchor points for muscles, enabling more complex movement. The emergence of shells and other protective coverings likely spurred an arms race between predators and prey, driving further diversification and specialization. As predators evolved better ways to catch prey, prey evolved better defenses, creating a continuous cycle of evolutionary innovation. Furthermore, the end of the snowball Earth glaciations, a series of severe ice ages that covered much of the planet in ice sheets just before the Cambrian, might have cleared ecological niches and spurred evolutionary recovery and diversification once warmer conditions returned. The breaking up of supercontinents, which led to new coastlines and diverse habitats, could also have provided new opportunities for species to diverge and adapt. The Cambrian explosion is profound because it demonstrates Earth's capacity for rapid biological innovation. It shows that, given the right environmental conditions and evolutionary pressures, complex life can emerge and diversify at an astonishing rate. While the life forms of the Cambrian were not intelligent in the human sense, their sudden appearance established the fundamental building blocks of animal life, paving the way for all subsequent evolutionary developments, including those that eventually led to intelligence. If such a rapid burst of complexity could occur 541 million years ago, it suggests that similar windows of opportunity for advanced life to emerge could have opened and closed at other points in Earth's 4.54 billion-year history, well before Homo sapiens ever walked the planet. The fossil record of the Cambrian period, characterized by the emergence of hard-bodied creatures, is significantly richer than that of previous periods, indicating how the physical traits of life directly influence what is preserved, and thus what we can detect of past biological epochs.